If you have questions, you've come to the right place. Why? Because O'Reilly is really all about one thing: answers. That's right, answers. Think about it. You came here to get the answers you need to solve tough business and technical challenges, right?
Do you see how, over time, this could become a tool?
But when the conference is over, your access to answers is just beginning. Because every attendee gets a 90-day unlimited pass to O'Reilly Online Learning. Free. Your membership includes videos that capture the conference keynotes and sessions, plus access to every O'Reilly book, expert-led, hands-on, live online training courses, and customizable learning paths that guide you through tough topics fast. Find out why over 5,000 companies count on O'Reilly for in-the-moment answers and lifelong learning that keeps their teams a step ahead of the competition every day. Sign up at the O'Reilly booth in the Expo Hall now and experience 90 days of free answers to your toughest challenges. Live online training courses and customizable learning paths that guide you through tough topics fast. Find out why over 5,000 companies count on O'Reilly for in-the-moment answers.
What I'm excited the most about machine learning is that it enabled us to solve problems that up to 10, 15 years ago we thought unsolvable.
There's more extreme rainfall, heavy flooding, forest fires.
Diagnosis is difficult in this part of the world because access to medical equipment is very expensive.
The Vatican archive, it will take centuries to be deciphered.
We are engineering students and we strive to do something for social good.
Using TensorFlow, we can tackle things we never thought that we could tackle, right? That's like incredible.
If you like how Airbnb operates today, the reason was because of machine learning.
I just think solving problems is fun. It's a game against myself.
TensorFlow World, a week-long conference dedicated to open source collaboration.
TensorFlow has grown to a full ecosystem.
The main point of doing something like this is to connect all the amazing users and everyone with experience to share.
We don't think you should have to choose between a simple API and a scalable API. We're constantly pushing the limits of what is possible on device.
What we're really trying to do here is lift TensorFlow to entirely new heights.
And now, please welcome TensorFlow World Program Chairs Ben Lorica and Ed Wilder-James.
Morning. So welcome to day one of keynotes and sessions here at TensorFlow World 2019. The O'Reilly and TensorFlow teams are excited to co-present our first ever TensorFlow World here in Santa Clara. And we also welcome our Livestream audience who are joining us from all over the world.
Welcome, everybody. It's great to have you here as part of the TensorFlow community. Now, before we start, I wanted to take a moment to recognize all those who are affected by the wildfires in Northern California at the moment. Many at this event have been impacted, including the conference team and speakers, and I wanted to say thank you to them for working at this difficult time, and to recognize the speedy way in which the team has bounced back from some challenging circumstances. Our thoughts are with you. So, we've already had a few terrific days of trainings and tutorials here at TensorFlow World, along with the TensorFlow Contributor Summit, a fun Ignite event, and some lively poster sessions last night. For those of you who joined us, we hope you learned something new and had a great time. And kudos to the early risers who joined us, what, at 6:30 this morning for the 5K fun run and speed networking events. Thanks.
And we'd like to thank our diamond sponsor, Google Cloud, our elite sponsors, IBM and NVIDIA, and our gold sponsor, Databricks, for their generous support of TensorFlow World. Their participation is very much appreciated and helps to make this conference a truly great event.
So if you're tweeting or blogging about the conference, the official conference hashtag is TFWorld. I know there's plenty of people on the live stream, so send us a tweet so we know where you're watching from. We invite you to join that Twitter stream and really help tell the story of the conference to those who can't be here.
We're live streaming and live captioning our keynotes today, and we'll also be streaming all the sessions from the core technology track today and tomorrow. So please share the live stream link.
Our opening keynote speaker this morning is Jeff Dean. Jeff's a senior fellow in Google's research group, where he co-founded and leads the Google Brain team. He and his collaborators are working on systems for speech recognition, computer vision, language understanding, and various other machine learning tasks. Jeff co-designed and implemented many generations of Google's crawling, indexing, and query-serving systems, major pieces of Google's initial advertising and AdSense for content systems, and Google's distributed computing infrastructure, including the MapReduce, Bigtable, and Spanner systems, protocol buffers, LevelDB, and systems infrastructure for statistical machine translation. But most importantly for us this week, Jeff led the development and open sourcing of TensorFlow, with the intent that the whole world have access to machine learning at scale. Please welcome Jeff Dean.
Thank you. I'm really excited to be here. I think it was almost 4 years ago to the day that we were about 20 people sitting in a small conference room in one of the Google buildings. We've woken up early because we wanted to kind of time this for an early East Coast launch where we were turning on the TensorFlow.org website and releasing the first version of TensorFlow as an open source project. And I'm really, really excited to see what it's become. It's just remarkable to see the growth and all the different kinds of ways in which people have used this system for all kinds of interesting things around the world. So one thing that's interesting is the growth in the use of TensorFlow also kind of mirrors the growth in interest in machine learning and machine learning research generally around the world. So this is a graph showing the number of machine learning archive papers that have been posted over the last sort of 10 years or so. And you can see it's growing quite rapidly, much more quickly than you might expect. And that lower red line is kind of the nice doubling every couple of years growth rate, exponential growth rate we got used to in computing power due to Moore's law for so many years. That's now kind of slowed down. But you can see that the machine learning research community is generating research ideas at faster than that rate, which is pretty remarkable. We've replaced computational growth with growth of ideas, and we'll see those both together will be important. And really, the excitement about machine learning is because we can now do things we couldn't do before, right? As little as 5 or 6 years ago, computers really couldn't see that well. And starting in about 2012, 2013, we started to have people use deep neural networks to try to tackle computer vision problems, image classification, object detection, things like that. And so now, using deep learning and deep neural networks, you can feed in the raw pixels of an image and fairly reliably get a prediction of what kind of object is in that image. Feed in the pixels there, red, green, and blue values in a bunch of different coordinates, and you get out the prediction leopard. This works for speech as well. You can feed in audio waveforms, and by training on lots of audio waveforms and transcripts of what's being said in those waveforms, we can actually take a completely new recording and tell you what is being said, emit a transcript. Bonjour, comment allez-vous? You can even combine these ideas and have models that take in pixels, and instead of just predicting classifications of what is in the object, can actually write a short sentence, a short caption that a human might write about the image. A cheetah lying on top of a car. That's one of my vacation photos, which was kind of cool. And so just to show the progress in computer vision, in 2011, Stanford hosts an ImageNet contest every year to see how well computer vision systems can predict one of 1,000 categories in a full-color image. And you get about 1 million images to train on, and then you get a bunch of test images your model has never seen before, and you need to make a prediction. In 2011, the winning entrant got 26% error, right? So you can kind of make out what that is, but it's pretty hard to tell. We know from a human experiment that human error of a well-trained human, someone who's practiced at this particular task and really understands the 1,000 categories, gets about 5% error. So it's not a trivial task. And in 2016, the winning entrant got 3% error. So just look at that tremendous progress in the ability of computers to resolve and understand computer imagery and have computer vision that actually works. This is remarkably important in the world because now we have systems that can perceive the world around us and we can do all kinds of really interesting things with that. We've seen similar progress in speech recognition and language translation, things like that. So for the rest of the talk, I'd like to kind of structure it around this nice list of 14 challenges that the US National Academy of Engineering put out and felt like these were important things for the science and engineering communities to work on for the next 100 years. They put this out in 2008 and came up with this list of 14 things after some deliberation. And I think you'll agree that these are sort of pretty good, large, challenging problems that if we actually make progress on them, that we'll actually have a lot of progress in the world. We'll be healthier, we'll be able to learn things better, we'll be able to develop better medicines, we'll have all kinds of interesting energy solutions. So I'm going to talk about a few of these. And the first one I'll talk about is restoring and improving urban infrastructure. So we're on the cusp of the sort of widespread commercialization of a really interesting new technology that's going to really change how we think about transportation. And that is autonomous vehicles. And this is a problem that has been worked on for quite a while, but it's now starting to look like it's actually completely possible and commercially viable to produce these things. And a lot of the reason is that we now have computer vision and machine learning techniques that can take in sort of raw forms of data that the sensors on these cars collect. So they have like the spinning LiDARs on the top that give them 3D point cloud data. They have cameras in lots of different directions. They have radar in the front bumper and the rear bumper. And they can really take all this raw information in and with a deep neural network, fuse it all together to build a high-level understanding of what is going on around the car. Or is it like another car to my side? There's a pedestrian up here to the left. There's a light post over there. I don't really need to worry about that moving. And really help to understand the environment in which they're operating, and then what actions can they take in the world that are both legal, safe, obey all the traffic laws, and get them from A to B. And this is not some distant, far-off dream. Alphabet's Waymo subsidiary has actually been running tests in Phoenix, Arizona. Normally when they run tests, they have a safety driver in the front seat ready to take over if the car does something kind of unexpected. But for the last year or so, they've been running tests in Phoenix with real passengers in the back seat and no safety drivers in the front seat, running around suburban Phoenix. So suburban Phoenix is a slightly easier training ground than, say, downtown Manhattan or San Francisco, but it's still something that is like not really far off. It's something that's actually happening. And this is really possible because of things like machine learning and the use of TensorFlow in these systems. Another one that I'm really, really excited about is advanced health informatics. This is a really broad area, and I think there's lots and lots of ways that machine learning and the use of healthcare data can be used to make better healthcare decisions for people. So I'll talk about one of them. And really, I think the potential here is that we can use machine learning to bring the wisdom of experts through a machine learning model anywhere in the world. And that's really a huge, huge opportunity. So let's look at this through one problem we've been working on for a while, which is diabetic retinopathy. So diabetic retinopathy is the fastest growing cause of preventable blindness in the world. And screening every year, if you're at risk for this, and if you have diabetes or early sort of symptoms that make it likely you might develop diabetes, you should really get screened every year. So there's 400 million people around the world that should be screened every year. But the screening is really specialized. Doctors can't do it. You really need an ophthalmologist level of training in order to do this effectively. And the impact of this shortage is significant. So in India, for example, there's a shortage of 127,000 eye doctors to do this sort of screening. And as a result, 45% of patients who are diagnosed with this disease actually have suffered either full or partial vision loss before they're actually diagnosed and then treated. And this is completely tragic because this disease, if you catch it in time, is completely treatable. There's a very simple 99% effective treatment that we just need to make sure that the right people get treated at the right time. So what can you do? So it turns out diabetic retinopathy screening is also a computer vision problem. And the progress we've made on general computer vision problems, where you want to take a picture and tell if that's a leopard or an aircraft carrier or a car, actually also works for diabetic retinopathy. So you can take a retinal image, which is what the screening camera, sort of the raw data that comes off the screening camera, and try to feed that into a model that predicts 1, 2, 3, 4, or 5. That's how these things are graded. 1 being no diabetic retinopathy, 5 being proliferative, and the other numbers being in between. So it turns out you can get a collection of data of retinal images and have ophthalmologists label them. Turns out if you ask 2 ophthalmologists to label the same image, they agree with each other 60% of the time on the number 1, 2, 3, 4, or 5. But perhaps slightly scarier, if you ask the same ophthalmologist to grade the same image a few hours apart, they agree with themselves 65% of the time. But you can fix this by actually getting each image labeled by a lot of ophthalmologists. So you get it labeled by 7 ophthalmologists. If 5 of them say it's a 2 and 2 of them say it's a 3, it's probably more like a 2 than a 3. Eventually, you have a nice high-quality data set you can train on. Like many machine learning problems, high-quality data is the right raw ingredient. But then you can apply basically an off-the-shelf computer vision model trained on this data set. And now you can get a model that is on par or perhaps slightly better than the average board-certified ophthalmologist in the US, which is pretty amazing. It turns out you can actually do better than that. And if you get the data labeled by retinal specialists, people who have more training in retinal disease, and change the protocol by which you label things. You get 3 retinal specialists to look at an image, discuss it amongst themselves, and come up with what's called a sort of coordinated assessment and one number. Then you can train a model and now be on par with retinal specialists, which is kind of the gold standard of care in this area. And that's something you can now take and distribute widely around the world. So one issue particularly with healthcare kinds of problems is you want explainable models. You want to be able to explain to a clinician, why is this person, why do we think this person has moderate diabetic retinopathy? And so you can take a retinal image like this, and one of the things that really helps is if you can show in the model's assessment why this is a 2 and not a 3. And by highlighting parts of the input data, you can actually make this more understandable for clinicians and enable them to sort of really get behind the assessment that the model is making. And we've seen this in other areas as well. There's been a lot of work on explainability, so I think the notion that deep neural networks are sort of complete black boxes is a bit overdone. There's actually a bunch of good techniques that are being developed and more all the time that will improve this. So a bunch of advances depend on being able to understand text. And we've had a lot of really good improvements in the last few years on language understanding. So this is a bit of a story of research and how research builds on other research. So in 2017, a collection of Google researchers and interns came up with a new kind of model for text called the transformer model. So unlike recurrent models where you have kind of a sequential process where you absorb one word or one token at a time and update some internal state and then go on to the next token, the transformer model enables you to process a whole bunch of text all at once in parallel, making it much more computationally efficient, and then to use attention on previous text to really focus on, if I'm trying to predict what the next word is, what are other parts of the context to the left that are relevant to predicting that. So that paper was quite successful and showed really good results on language translation tasks with a lot less compute. So the blue score there in the first 2 columns for English to German and English to French, higher is better. And then the compute cost of these models shows that this is getting sort of state-of-the-art results at that time with 10 to 100x less compute than other approaches. Then in 2018, another team of Google researchers built on the idea of transformers. So everything you see there in a blue oval is a transformer module. And they came up with this approach called bidirectional encoding representations from transformers, or BERT. It's a little bit shorter and more catchy. So BERT has this really nice property that in addition to using context to the left, it uses context all around the language, the surrounding text, in order to make predictions about text. And the way it works is you start with a self-supervised objective. So the one really nice thing about this is there's lots and lots of text in the world. So if you can figure out a way to use that text to train a model to be able to understand text better, that would be great. So we're going to take this text, and in the BERT training objective, to make it self-supervised, we're going to drop about 15% of the words. And this is actually pretty hard, but the model is then going to try to fill in the blanks, essentially. Try to predict what are the missing words that were dropped. And because we actually have the original words, we now know, if the model is correct in its guesses about what goes in the blanks. And by processing trillions of words of text like this, you actually get a very good understanding of contextual cues in language and how to actually fill in the blanks in a really intelligent way. And so that's essentially the training objective for BERT. You take text, you drop 15% of it, and then you try to predict those missing words. And one key thing that works really well is that's step 1. You can pre-train a model on lots and lots of text using this fill-in-the-blanks self-supervised objective function. And then step 2, you can then take a language task you really care about. Like maybe you want to predict, is this a 5-star review or a 1-star review for some hotel? But you don't have very much labeled text for that actual task. You might have 10,000 reviews and know the star count of each review. But you can then fine-tune the model, starting with the model trained in step 1 on trillions of words of text, and now use your paltry 10,000 examples for the text task you really care about. And that works extremely well. So in particular, BERT gave state-of-the-art results across a broad range of different text understanding benchmarks in this GLUE benchmark suite, which was pretty cool. And people have been using BERT now in this way to improve all kinds of different things all across the language understanding and NLP space. So one of the grand challenges was engineer the tools of scientific discovery. And I think it's pretty clear machine learning is actually going to be an important component of making advances in a lot of these other grand challenge areas, things like autonomous vehicles or other kinds of things. And it's been really satisfying to see what we'd hoped would happen when we released TensorFlow as an open source project has actually kind of come to pass as we were hoping, in that lots of people would sort of pick up TensorFlow, use it for all kinds of things. People would improve the core system. They would use it for tasks we would never imagine. And that's been quite satisfying. So people have done all kinds of things. Some of these are uses inside of Google. Some are outside in academic institutions. Some are scientists working on conserving whales or understanding like ancient scripts. Many kinds of things, which is pretty neat. The breadth of uses is really amazing. These are the 20 winners of the Google.org AI Impact Challenge, where people could submit proposals for how they might use machine learning and AI to really tackle a local challenge they saw in their communities. And they have all kinds of things, ranging from like trying to predict better ambulance dispatching to identifying illegal logging using speech recognition or audio processing. Pretty neat. And many of them are using TensorFlow. So one of the things we're pretty excited about is AutoML, which is this idea of automating some of the process by which machine learning experts sit down and sort of make decisions to solve machine learning problems. So currently, you have a machine learning expert sit down, they take data, they have computation, they run a bunch of experiments, they kind of stir it all together, and eventually you get a solution to a problem you actually care about. One of the things we'd like to be able to do, though, is see if we could eliminate a lot of the need for the human machine learning expert to run these experiments and instead automate the experimental process by which a machine learning expert comes by a high-quality solution for a problem you care about. So one of the, lots and lots of organizations around the world have machine learning problems, but many of them don't even realize they have a machine learning problem, let alone have people in their organization that can tackle the problem. So one of the earliest pieces of work our researchers did in this space was something called neural architecture search. So when you sit down and design a neural network to tackle a particular task, you make a lot of decisions about, shapes of this or that, and like, should it be use 3x3 filters at layer 17 or 5x5, all kinds of things like this. It turns out you can automate this process by having a model generating model and train the model generating model based on feedback about how well the models that it generates work on the problem you care about. So the way this will work, we're going to generate a bunch of models. Those are just descriptions of different neural network architectures. We're going to train each of those for a few hours, and then we're going to see how well they work, and then use the accuracy of those models as a reinforcement learning signal for the model generating model to steer it away from models that didn't work very well and towards models that worked better. And we're going to repeat many times. And over time, we're going to get better and better by steering the search to the parts of the space of models that worked well. And so it comes up with models that look a little strange, admittedly. A human probably would not sit down and wire up a sort of machine learning computer vision model exactly that way, but they're pretty effective. So if you look at this graph, this shows kind of the best human machine learning experts, computer vision experts, machine learning researchers in the world producing a whole bunch of different kinds of models in the last 4 or 5 years, things like ResNet 50, DenseNet 201, Inception ResNet, all kinds of things. That black dotted line is kind of the frontier of human machine learning expert model quality on the y-axis and computational cost on the x-axis. So what you see is as you go out the x-axis, you tend to get more accuracy because you're applying more computational cost. But what you see is the blue dotted line is AutoML-based solutions, systems where we've done this automated experimentation instead of pre-designing any particular architecture. And you see that it's better both at the high end, where you care about the most accurate model you can get, regardless of computational cost, but it's also accurate at the low end, where you care about a really lightweight model that might run on a phone or something like that. And in 2019, we've actually been able to improve that significantly. This is a set of models called EfficientNet, and has it's kind of a slider about you can trade off computational cost and accuracy. But they're all way better than human sort of guided experimentation on the black dotted line there. And this is true for image recognition, for classification. It's true for object detection. So the red line there is AutoML. The other things are not. It's true for language translation. So the black line there is various kinds of transformers. The red line is we've gave the basic components of transformers to an AutoML system and allowed it to fiddle with it and come up with something better. It's true for computer vision models used in autonomous vehicles. So this is a collaboration between Waymo and Google Research. We were able to come up with models that are significantly lower latency for the same quality, or they could trade it off and get significantly lower error rate at the same latency. It actually works for tabular data. So if you have lots of customer records and you want to predict which customers are going to be spending $1,000 with your business next month, you can use AutoML to come up with a high-quality model for that kind of problem. OK, so what do we want? I think we want the following properties in a machine learning model. So one is we tend to train separate models for each different problem we care about. And I think this is a bit misguided. Really, we want one model that does a lot of things so that it can build on the knowledge in how it does thousands or millions of different things, so that when the 1,000,001st thing comes along, it can actually use its expertise from all the other things it knows how to do to know how to get into a good state for the new problem with relatively little data and relatively little computational cost. So these are some nice properties. I have kind of a cartoon diagram of something I think might make sense. So imagine we have a model like this, where it's very sparsely activated. So different pieces of the model have different kinds of expertise, and they're called upon when it makes sense, but they're mostly idle. So it's relatively computationally even power efficient, but it can do many things. And now, each component here is some piece of a machine learning model with different kinds of state, parameters in the model, and different operations. And a new task comes along. Now, you can imagine something like neural architecture search becoming squint at it just right and now turn it into neural pathway search. We're going to look for components that are really good for this new task we care about. And maybe we'll search and find that this path through the model actually gets us into a pretty good state for this new task, because maybe it goes through components that are trained on related tasks already. And now maybe we want that model to be more accurate for the purple task. So we can add a bit more computational capacity, add a new component, start to use that component for this new task, continue training it, and now that new component can also be used for solving other related tasks. And each component itself might be running some sort of interesting architectural search inside it. So I think something like that is the direction we should be exploring as a community. It's not what we're doing today, but I think it could be a pretty interesting direction. OK, and finally, I'd like to touch on thoughtful use of AI in society. As we've seen more and more uses of machine learning in our products and around the world, it's really, really important to be thinking carefully about how we want to apply these technologies. Like any technology, these systems can be used for amazing things or things we might find a little sort of detrimental in various ways. And so we've come up with a set of principles by which we think about applying sort of machine learning and AI to our products. And we've made these public about 1.5 years ago as a way of sort of sharing our thought process with the rest of the world. And I particularly like these. I'll point out many of these are sort of areas of research that are not fully understood yet, but we aim to apply the best in the state-of-the-art methods for example, for reducing bias in machine learning models, but also continue to do research and advance the state-of-the-art in these areas. And so this is just kind of a taste of different kinds of work we're doing in this area. How do we do machine learning with more privacy using things like federated learning? How do we make models more interpretable so the clinician can understand the predictions it's making on diabetic retinopathy sort of examples? How do we make machine learning more fair? OK, and with that, I hope I've convinced you that deep neural nets and machine learning, you're already here, so maybe you're already convinced of this, but are helping make sort of significant advances in a lot of hard computer science problems. Computer vision, speech recognition, language understanding, general use of machine learning is going to push the world forward. So thank you very much, and I appreciate you all being here.
Thank you, Jeff, for such a great tour of the applications that are being built and sketching out what future neural architectures may look like. Now, an important component of any conference is networking. So for the next 2 days, this is your TensorFlow community. We have many great speakers, not just from Google, Google's core TensorFlow team, but from many different companies. But also, your fellow attendees might be sources of inspiration as well. So some of the things that Jeff described may be built by people who are in attendance at this conference. So if you missed out on speed networking before keynotes today, there's another chance tomorrow morning from 8 to 8:30 a.m. So speed networking will take place right outside here at keynotes in the Mission City Ballroom foyer. Also, please check out our code of conduct, which is linked on the conference homepage. It's an important part of the conference experience, so we invite everyone to help make this a welcoming and respectful environment for everyone here this week. So our next speaker is Ted Summey. He is the head of product for Cortex, which is Twitter's central machine learning organization. His team of product managers works across applied research, ML services, and their machine learning platform. Please welcome Ted Summey of Twitter.
Hi, I'm Ted Summey. I'm from Twitter. Before I get started with my conversation today, I want to do a quick plug for Twitter. What's great about events like this is you get to hear people like Jeff Dean talk. And you also get to hear from colleagues and people in the industry that are facing similar challenges as you and have conversations around developments in data science and machine learning. But what's great is that's actually available every day on Twitter. Twitter is phenomenal for conversation on data science and machine learning. People like Jeff Dean and other thought leaders are constantly sharing their thoughts and their developments. And you can follow that conversation and engage in it. And not only that, but you can bring that conversation back to your workplace and come off looking like a hero. Just something to consider. So without that shameless plug, my name's Ted Summey. I lead product for Cortex. Cortex is Twitter's central machine learning organization. If you have any questions for me or the team, feel free to connect with me on Twitter. We can follow up later. So before we get into how we're accelerating ML at Twitter, let's talk a little bit about how we're even using ML at Twitter. Twitter is largely organized against 3 customer needs, the first of which is our health initiative. That might be a little bit confusing to you. You might think of it as user safety, but we think about it as improving the health of conversations on Twitter. And machine learning is already at use here. We use it to detect spam. We can algorithmically and at scale detect spam and protect our users from it. Similarly, in the abuse space, we can proactively flag content as potentially abuse, toss it up for human reviews, and act on it before our users even get impacted by it. A third space where we're using machine learning here is something called NSFW, not safe for work. I think you're all familiar with the acronym. So how can we, at scale, identify this content and handle it accordingly? Another use of machine learning in this space. There's more that we want to do here, and there's more that we're already doing. Similarly, the consumer organization, this is largely what you think of, the big blue app of Twitter. And here, the customer job that we're serving is helping connect our customers with the conversations on Twitter that they're interested in. And one of the primary veins in which we do this is our timeline. Our timeline today is ranked. So if you're not familiar, users follow accounts. Content and tweets associated with those accounts get funneled into a central feed. And we rank that based on your past engagement and interest to make sure we bring to forth the most development and most relevant conversations for you. Now, there's lots of conversations on Twitter, and you're not following everyone. And so there's also a job that we have to serve about bringing forth all the conversations that you're not proactively following, but are still relevant to you. This is surfaced in our recommendations product, which uses machine learning to scan the corpus of content on Twitter and identify what conversations would be most interesting to you and push it to you in a notification. The inverse of that is when you know what the topics you want to explore are, but you're looking for the conversations around that. That's where we use Twitter search. This is another surface area in the big blue app that we're using machine learning. The third job to be done for our customers is helping connect brands with their customers. You might think of this as the ads product, and this is actually the OG of machine learning at Twitter, the first team that implemented it. And here we use it for what you might expect, ads ranking. That's kind of like the timeline ranking, but instead of tweets, it's ads, and identifying the most relevant ads for our users. And as signals to go into that, we also do user targeting to understand your past engagement in ads, understand which ads are in your interest space. And the third, that's really good. And the third is brand safety. You might not think about this when you think about machine learning and advertising, but if you're a company like United and you want to advertise on Twitter, you want to make sure that your ad never shows up next to a tweet about a plane crash. So how do we, at scale, protect our brands from those off-brand conversations? We use machine learning for this as well. So as you can tell, machine learning is a big part of all of these organizations today. And where we have shared interests and shared investment, we want to make sure we have a shared organization that serves that. And that's the need for Cortex. Cortex is Twitter's central machine learning team, and our purpose is really quite simple: to enable Twitter with ethical and advanced AI. And to serve that purpose, we've organized in 3 ways. The first is our applied research group. This group applies the most advanced ML techniques from industry and research to our most important surface areas, whether they be new initiatives or existing places. This team you can kind of think of as like an internal task force or consultancy that we can redeploy against the company's top initiatives. The second is signals. When using machine learning, having shared data assets that are broadly useful can provide us more leverage. Examples of this would be our language understanding team that looks at tweets and identifies named entities inside them. Those can then be offered up as features for other teams to consume in their own applications of machine learning. Similarly, our media understanding team looks at images and can create a fingerprint of any image, and therefore we can identify every use of that image across the platform. These are examples of shared signals that we're producing that can be used for machine learning at scale inside the company. And the third organization is our platform team. And this is really the origins of Cortex. Here, we provide tools and infrastructure to accelerate ML development at Twitter, increase the velocity of our ML practitioners. And this is really the focus of the conversation today. When we set out to build this ML platform, we decided we wanted a shared ML platform across all of Twitter. And why is that important that it be shared across all of Twitter? Well, we want transferability. We want the great work being done in the ads team to be, where possible, transferable to benefit the health initiative, where that's relevant. And similarly, if we have great talent in the consumer team that's interested in moving to the ads team, if they're on the same platform, they can transfer without friction and be able to ramp up quickly. So we set out with this goal of having a shared ML platform across all of Twitter. And when we did that, we looked at a couple product requirements. First, it needs to be scalable. It needs to be able to operate at Twitter scale. The second, it needs to be adaptable. This space is developing quickly, so we need a platform that can evolve with data science and machine learning developments. Third is the talent pool. We want to make sure that we have a development environment at Twitter that appeals to the ML researchers and engineers that we're hiring and developing. Fourth is the ecosystem. We want to be able to lean on the partners that are developing industry-leading tools so we can focus on technologies that are Twitter-specific. Fourth is documentation. I think you all understand that. We want to be able to quickly unblock our practitioners as they hit issues, which is inevitable in any platform. And finally, usability. We want to remove friction and frustration from the lives of our team so that they can focus on delivering value for our end customers. So, considering these product requirements, let's see how TensorFlow has done against them. First is scalability. We validated this by putting TensorFlow, by way of our implementation we call DeepBird, against timeline ranking. So every tweet that's ranked in the timeline today runs through TensorFlow. So we can consider that test validated. Second is adaptability. The novel architectures that TensorFlow can support, as well as the custom loss functions, allows us to react to the latest research and employ that inside the company. An example that we published on this publicly is our use of a split net architecture in ads ranking. So TensorFlow has been very adaptable for us. Third is the talent pool. And we think about the talent pool in kind of two types. There's the ML engineer and the ML researcher. And as a proxy of these audiences, we looked at the GitHub data on these. And clearly, TensorFlow is widely adopted amongst ML engineers. And similarly, the archive community shows strong evidence of wide adoption in the academic community. On top of this proxy data, we've also have anecdotal evidence of the speed of ramp up for ML researchers and ML engineers inside the company. And the fourth is the ecosystem, whether it's TensorBoard, TF data validation, TF model analysis, TF Metastore, TF Hub, TFX pipelines. There's a slew of these products out there, and they're phenomenal. They allow us to focus on developing tools and infrastructure that is specific to Twitter's needs and lead on the great work of others. So we're really grateful for this, and TensorFlow does great here. Fifth being documentation. Now, this is what you would go to when you go to TensorFlow, and you see that phenomenal documentation as well as great education resources. But what you might not appreciate, and what we've come to really appreciate, is the value of the user-generated content. What Stack Overflow and other platforms can provide in terms of user-generated content is almost as valuable as anything TensorFlow itself can create. And so TensorFlow, given its widespread adoption and its great TensorFlow website, has provided phenomenal documentation for ML practitioners. Finally, usability. And this is why we're really excited about TensorFlow 2.0. The orientation around the Keras API makes it more user-friendly. It also still continues to allow for flexibility for more advanced users. The eager execution enables more rapid and intuitive debugging, and it closes the gap between ML engineers and modelers. So clearly, from this checklist, we're pretty happy with our engagement with TensorFlow. And we're excited about continuing to develop the platform with them and push the limits on what it can do. Gratitude to the community for their participation and involvement in the product, and appreciate their conversation on Twitter as we advance it. So if you have any questions for me, as I said before, you can connect with me, but I'm not alone here today. A bunch of my colleagues are here as well, so if you see them roaming the halls, feel free to engage with them. Or, as I shared before, you can continue the conversation on Twitter. Here are their handles. Thank you for your time. Cheers.
Thanks, Ted. Thank you so much. It's great to have you with us. Now, I mentioned at the beginning to check in wherever you're watching from, so I'm happy to say hi to our friends in Ghana and Lebanon and all kinds of places that have wished us well over Twitter this morning, so please keep that coming. It's great to know that TensorFlow World is truly going around the world. So after the keynotes, please join us for this morning's break. That'll be served in the expo hall next to registration. Our thanks to NVIDIA for sponsoring the break this morning. It's really important to us to get feedback on how this conference is going, so please share your feedback by rating today's sessions. You can rate the sessions on any session detail page on the website and leave feedback or questions in the comments. Now, we have a lot of great activities happening in and around the conference space over the next 2 days. Please come to the expo hall, see the latest from TensorFlow at 5 really awesome demo booths, and come and talk with the sponsors who are contributing to the whole growing TensorFlow ecosystem. Now, our next speaker this morning is Fred Rice. Fred's the chief architect at the IBM Center for Open Source Data and AI Technologies in San Francisco, and he's personally a long-standing contributor to TensorFlow itself. So please join me in welcoming Fred Rice.
All right, thanks, Ed, for the great introduction. Hello, everyone. I'm Fred Rice. I work for IBM. I've been working for IBM since 2006, and I've been contributing to TensorFlow Core since 2017. But my primary job at IBM is to serve as tech lead for Codate. That's the Center for Open Source Data and AI Technologies. We are an open source lab located in downtown San Francisco, and we work on open source technologies that are foundational to AI. And we have on staff 44 full-time developers who work only on open source software. Now that's a lot of developers, a lot of open source developers. Or is it? Well, if you look across IBM at all of the IBMers who are active contributors to open source in that they have committed code to GitHub in the last 30 days, you'll find that there are almost 1,200 IBMers in that category. So our 44 developers are actually a very small slice of a very large pie. Oh, and those numbers, they don't include Red Hat. When we closed that acquisition earlier this year, we more than doubled our number of active contributors to open source. So you can see that IBM is really big in open source. And more, the bulk of our contributions in the open are going towards the foundations of AI. And when I say AI, I mean AI in production. I mean AI at scale. AI at scale is not an algorithm, it's not a tool, it's a process. It's a process that starts with data, and then that data turns into features, and those features train models, and those models get deployed in applications, and those applications produce more data, and the whole thing starts all over again. And at the core of this process is an ecosystem of open source software. And at the core of this ecosystem is TensorFlow, which is why I'm here on behalf of IBM Open Source to welcome you to TensorFlow World. Now, throughout this conference, you're going to see talks that speak to all of the different stages of this AI lifecycle. But I think you're going to see a special emphasis on this part, moving models into production. And one of the most important aspects of moving models into production is that when your model gets deployed in a real-world application, it's going to start having effects on the real world. And it becomes important to ensure that those effects are positive and that they're fair to your clients, to your users. Now, at IBM, here's a hypothetical example that our researchers put together about a little over a year ago. They took some real medical records data, and they produced a model that predicts which patients are more likely to get sick and therefore should get additional screening. And they showed that if you naively train this model, you end up with a model that has significant racial bias, but that by deploying state-of-the-art techniques to adjust the data set and the process of making the model, they could substantially reduce this model to produce a model, reduce this bias to produce a model that is much more fair. You can see a Jupyter notebook with the entire scenario from end to end, including code and equations and results at the URL down here. Again, I need to emphasize this was a hypothetical example. We built a flawed model deliberately so we could show how to make it better. But no patients were harmed in this exercise. However, last Friday, I sat down with my morning coffee and I opened up the Wall Street Journal and I saw this article at the bottom of page 3 describing a scenario eerily similar to our hypothetical. You know, when your hypotheticals start showing up as newspapers' headlines, that's kind of scary. And I think it is incumbent upon us as an industry to move forward the process, the technology of trust in AI, trust and transparency in AI, which is why IBM and IBM Research have released our toolkits of state-of-the-art algorithms in this space as open source under AI Fairness 360, AI Explainability 360, and Adversarial Robustness 360. It is also why IBM is working with other members of the Linux Foundation AI Trusted AI Committee to move forward open standards in this area so that we can all move more quickly to trusted AI. Now, if you'd like to hear more on this topic, my colleague on open source demos at the IBM booth. That's booth 201. Also check out our websites, developer.ibm.com and codate.org. On behalf of IBM, I'd like to welcome you all to TensorFlow World. Enjoy the conference. Thank you.
Thank you, Fred. I encourage you to visit the Codate website. They are really pushing out a lot of really useful and practical open source projects and developer resources. Please join us for lunch today in the expo hall. Some of the tables at lunch will have signs with industries and topics for discussion, so feel free to join one of the lunchtime topic tables. And our thanks to Google Cloud for sponsoring today's lunch. Also, please check out the Inclusion Lounge in the expo hall for career coaching from senior Google engineers, ally skills advice, and learning more about supporting partner organizations that are increasing diversity in the tech community. Our next speaker is Megan Cacholia. She is VP of Engineering within Google's research organization. Her team's work spans machine learning in research as well as in production, including products such as TensorFlow. She had a long tenure in the Google Ads organization, where she ran the serving system for Google's display ads business. Please welcome Megan Cacholia.
Hey everyone, good morning. Just want to say, first of all, welcome. Today, I want to talk a little bit about TensorFlow 2.0 and some of the new updates that we have that are going to make your experience with TensorFlow even better. But before I dive into a lot of those details, I want to start off by thanking you, everyone here, everyone on the live stream, everyone who's been contributing to TensorFlow, all of you who make up the community. TensorFlow was open source to help accelerate the AI field for everyone. You've used it in your experiments, you've deployed it in your businesses, you've made some amazing different applications that we're so excited to showcase and talk about, some that we get to see a bit here today, which is one of my favorite parts about conferences like this. And you've done so much more. And all of this has helped make TensorFlow what it is today. It's the most popular ML ecosystem in the world. And honestly, that would not happen without the community being excited and embracing and using this and giving back. So on behalf of the entire TensorFlow team, I really just first want to say thank you, because it's so amazing to see how TensorFlow is used. That's one of the greatest things I get to see about my job, is the applications and the way folks are using TensorFlow. I want to take a step back and talk a little bit about some of the different user groups and how we see them making use of TensorFlow. TensorFlow is being used across a wide range of experiments and applications. So here calling out researchers, data scientists, and developers. And there's other groups kind of in between as well. Researchers use it because it's flexible. It's flexible enough to experiment with and push the state of the art in deep learning. You heard this even just a few minutes ago with folks from Twitter talking about how they're able to use TensorFlow and expand on top of it in order to do some of the amazing things that they want to make use of on their own platform. And at Google, we see examples of this when researchers are creating advanced models like XLNet and some of the other things that Jeff referenced in his talk earlier. Taking a step forward, looking at data scientists and enterprise engineers have said they rely on TensorFlow for performance and scale in training and production environments. That's one of the big things about TensorFlow that we've always emphasized and looked at from the beginning. How can we make sure this can scale to large production use cases? For example, Quantify and BlackRock use TensorFlow to test and deploy BERT in real-world NLP instances, such as text tokenization as well as classification. Hopping one step forward, looking a bit at application developers. Application developers use TensorFlow because it's easy to learn ML on the platforms that they care about. Arduino wants to make ML simple on microcontrollers, so they rely on TensorFlow pre-trained models and TensorFlow Lite Micro for deployment. Each of these groups is a critical part of the TensorFlow ecosystem. And this is why we really wanted to make sure that TensorFlow 2.0 works for everyone. We announced the alpha at our Dev Summit earlier this year, and over the past few months, the team has been working very hard to incorporate early feedback. Again, thank you to the community for giving us that early feedback so we can make sure we're developing something that works well for you. And we've been working to resolve bugs and issues and things like that. And just last month, in September, we were excited to announce the final general release for TensorFlow 2.0. You might be familiar with TensorFlow's architecture, which has always supported the ML lifecycle from training through deployment. Again, one of the things we've emphasized since the beginning when TensorFlow was initially open sourced a few years ago. But I want to emphasize how TensorFlow 2.0 makes this workflow even easier and more intuitive. First, we invested in Keras and using an easy-to-use package in TensorFlow, making it the default high-level API. Many developers love Keras because it's easy to use and understand. Again, you heard this already mentioned a little bit earlier, and hopefully we'll hear more about it throughout the next few days. By tightly integrating Keras into 2.0, we can make Keras work even better with primitives like TF data. We can do performance optimizations behind the scenes and run distributed training. Again, we really wanted 2.0 to focus on usability. How can we make it easier for developers? How can we make it easier for users to get what they need out of TensorFlow? For instance, Lose It, a customized weight loss app, said they used tf.keras for designing their network. By leveraging mirrored strategy distribution in 2.0, they were able to utilize the full power of their GPUs. It's feedback like this that we love to hear, and again, it's very important for us to know how the community is making use of things, how the community is using 2.0, the things they want to see, so that we can make sure we're developing the right framework, and also make sure you can contribute back. When you need a bit more control to create advanced algorithms, 2.0 comes fully loaded with eager execution, making it familiar for Python developers. This is especially useful when you're stepping through, doing debugging, making sure you can really understand step by step what's happening. This also means there's less coding required when training your model, all without having to use session.run. Again, usability is a focus. To demonstrate the power of training models with 2.0, I'll show you how you can train a state-of-the-art NLP model in 10 lines of code using the Transformers NLP library by Hugging Face. Again, a community contribution. This popular package hosts some of the most advanced NLP models available today, like BERT, GPT, Transformer XL, XLNet, and now supports TensorFlow 2.0. So let's take a look. Here, kind of just looking through the code, you can see how you can use 2.0 to train Hugging Face's DistillBERT model for text classification. You can see you just simply load the tokenizer, model, and the dataset. Then prepare the dataset and use tf.keras compile and fit APIs. And with a few lines of code, I can now train my model. And with just a few more lines, we can use the trained model for tasks such as text classification using eager execution. Again, it's examples like this where we can see how the community takes something and is able to do something very exciting and amazing by making use of the platform and the ecosystem that TensorFlow is providing. But building and training a model is only one part of TensorFlow 2.0. You need the performance to match. That's why we've worked hard to continue to improve performance with TensorFlow 2.0. It delivers up to 3x faster training performance using mixed precision on NVIDIA Volta and Turing GPUs in a few lines of code with models like ResNet 50 and BERT. As we continue to double down on 2.0 in the future, performance will remain a focus with more models and with hardware accelerators. For example, in 2.1, so the next upcoming TensorFlow release, you can expect TPU and TPU pod support along with mixed precision for GPUs. So performance is something that we're keeping a focus on as well, while also making sure usability really stands to the forefront. But there's a lot more to the ecosystem. So beyond model building and performance, there are many other pieces that help round out the TensorFlow ecosystem. Add-ons and extensions are a very important piece here, which is why we wanted to make sure that they're also compatible with TensorFlow 2.0. So you can use popular libraries like some of the ones called out here, whether it's TensorFlow Probability, TF Agents, or TF Text. We've also introduced a host of new libraries to help researchers and ML practitioners in more useful ways. So for example, neural structure learning helps to train neural networks with structured signals, and the new Fairness Indicators add-on enables regular computation and visualization of fairness metrics. And these are just the types of things that you can see kind of as part of the TensorFlow ecosystem. These add-ons that, again, can help you make sure you're able to do the things you need to do, not with your models, but kind of beyond just that. Another valuable aspect of the TensorFlow ecosystem is being able to analyze your ML experiments in detail. So this is showing TensorBoard. TensorBoard is TensorFlow's visualization toolkit, which is what helps you accomplish this. It's a popular tool among researchers and ML practitioners for tracking metrics, visualizing model graphs and parameters, and much more. It's very interesting that we've seen users enjoy TensorBoard so much, so they'll even take screenshots of their experiments and then use those screenshots to be able to share with others what they're doing with TensorFlow. This type of sharing and collaboration in the ML community is something we really want to encourage with TensorFlow. Again, there's so much that can happen by enabling the community to do good things. That's why I'm excited to share the preview of TensorBoard.dev, a new, free, managed TensorBoard experience that lets you upload and share your ML experiment results with anyone. You'll now be able to host and track your ML experiments and share them publicly. No setup required. Simply upload your logs, and then share the URL so that others can see the experiments and see the things that you are doing with TensorFlow. As a preview, we're starting off with the Scalars dashboard, but over time, we'll be adding a lot more functionality to make the sharing experience even better. But if you're not looking to build models from scratch and want to reduce some computational cost, TensorFlow has always made pre-trained models available through TensorFlow Hub. And today, we're excited to share an improved experience of TensorFlow Hub that's much more intuitive, where you can find a comprehensive repository of pre-trained models in the TensorFlow ecosystem. This means you can find models like BERT and others related to image, text, video, and more that are ready to use with TensorFlow Lite and TensorFlow.js. Again, we wanted to make sure the experience here was vastly improved to make it easier for you to find what you need in order to more quickly get to the task at hand. And since TensorFlow is driven by all of you, TensorFlow Hub is hosting more pre-trained models from the community. You'll be able to find curated models by DeepMind, Google, Microsoft's AI for Earth, and NVIDIA ready to use today, with many more to come. We want to make sure that TensorFlow Hub is a great place to find some of these excellent pre-trained models. And again, there's so much the community is doing. We want to be able to showcase those models as well. TensorFlow 2.0 also highlights TensorFlow's core strengths and areas of focus, which is being able to go from model building and experimentation through to production, no matter what platform you work on. You can deploy end-to-end ML pipelines with TensorFlow Extended, or TFX. You can use your models on mobile and embedded devices with TensorFlow Lite for on-device inference. and you can train and run models in the browser or Node.js with TensorFlow.js. You'll learn more about what's new in TensorFlow in production during the keynote sessions tomorrow. You can learn more about these updates by going to tensorflow.org, where you'll also find the latest documentation, examples, and tutorials for 2.0. Again, we want to make sure it's easy for the community to see what's happening, what's new, and enable you to just do what you need to do with TensorFlow. We've been thrilled to see the positive response to 2.0, and we hope you continue to share your feedback. Thank you, and I hope you enjoy the rest of TF World.
Thank you, Megan. Thank you. Thanks so much, Megan. That was amazing. And I really want to echo, my day-to-day is working with the TensorFlow contributor community, and it really makes it worth coming to work every day. It's always the people, it's always the community, it's always that connection and the way we work together that makes this project so exciting to me. So thank you if you're a part of the community and a contributor to TensorFlow. So everyone is welcome to join the Better Together Diversity Lunch today. That's be in the Magnolia Room, which is in the Hyatt Hotel side of this facility. We'll be networking, and we'll be hearing ideas for supporting diversity in tech. Now, there's so much great content here at the conference. We have like 5, 6 multiple rooms of sessions going on at the same time. And short of further advances, no one can possibly catch it all in person at the same time. So the good news is that all of the keynotes, all of the sessions here at TensorFlow World will be available after the conference. We'll be posting them on the TensorFlow YouTube channel. They'll also be available on O'Reilly Learning. Now, our next speaker this morning is Craig Wiley. Craig's the Director of Product for Google Cloud's AI platform, which is a code-based development environment for ML developers and data scientists taking projects from ideation to deployment. Craig previously spent 9 years at Amazon, most recently as the general manager of Amazon SageMaker. So please help me and welcome Craig Wiley.
Thank you, Ed. Thanks. I just want to begin by saying I've been dabbling in cloud AI and cloud machine learning for a while. And during that time, it never occurred to me that we'd be able to come out with something like we did today, because this is only possible because Google Cloud and TensorFlow can collaborate unbelievably closely together within Google. So to begin, let's talk a little bit about TensorFlow. 46 million downloads. TensorFlow has been massive growth the last few years. It's expanded from the forefront of research, which we've seen earlier this morning, to businesses taking it on as a dependency for their business to operate on a day-in, day-out basis. It's a super exciting piece. As someone who spends most all of their time thinking about how we can bring AI and machine learning into businesses, seeing TensorFlow's commitment and focus on deploying actual ML in production is super exciting to me. With this growth, though, comes growing pains. And part of that is things like support, right? When my model doesn't do what I expected it to, or my training job fails, what options do I have? And, how well does your boss respond when you say, hey, yes, I don't know why my model's not training, but not to worry, I've put a question on Slack and hopefully someone will get back to me. We understand that businesses who are taking a bet on TensorFlow as a critical piece of their hardware architecture, their stack, need more than this. Second, it can be a challenge to unlock the scale and performance of cloud. For those of you who, like me, have gone through this journey over the last couple of years, for me it started on my laptop, right? And then eventually I outgrew my laptop, and so I had a gaming rig under my desk, right, with a GPU. And eventually there were 8 gaming rigs under my desk. And when you opened the door to my office, the whole floor knew because it sounded like, right? And but now with today's cloud, that doesn't have to be the case. You can go from that single instance all the way up to a massive scale, seamlessly. So with that, today, we bring you TensorFlow Enterprise. TensorFlow Enterprise is designed to do 3 things. 1, give you enterprise-grade support. 2, cloud scale performance. And 3, managed services when and where you want them, at the abstraction level you want them. Enterprise-grade support, what does that mean? Fundamentally, what that means is that as these businesses take a bet on TensorFlow, many of these businesses have IT policies or requirements that the software have, a certain longevity before they're willing to commit to it in production. And so today, for certain versions of TensorFlow, when used on Google Cloud, we will extend that 1 year of support a full 3 years. That means that if you're building models on 1.15 today, you can know that for the next 3 years, you'll get bug fixes and security patches when and where you need them. Simple and scalable. Scaling from an idea on a single node to production at massive scale can be daunting, right? Saying to my boss, hey, I took a sample of the data was something that previously seemed totally reasonable, but now we're asked to train on the entire corpus of data. And that can take days, weeks. We can help with all of that by deploying TensorFlow on Google Cloud, a network that's been running TensorFlow successfully for years and has been highly optimized for this purpose. So scalable across our world-class architecture. The products are compatibility tested with the cloud. They're performance optimized for the cloud and for Google's world-class infrastructure. What does this mean? So if any of you have ever had the opportunity to use BigQuery, BigQuery is Google Cloud's kind of massively parallel cloud-hosted data warehouse. And by the way, if you haven't tried using BigQuery, highly recommend going out and trying it. It returns results faster than can be imagined. That speed in BigQuery, we wanted to make sure we were taking full advantage of that. And so recent changes and recent pieces included in TensorFlow Enterprise have increased the speed of the connection between the data warehouse and TensorFlow by 3 times. Right? Now all of a sudden those jobs that were taking days take hours. Unity Gaming, a wonderful customer and partner with us. You can see the quote here. Unity leverages these aspects of TensorFlow Enterprise in their business. Their monetization products reach more than 3 billion devices, 3 billion devices worldwide. Game developers rely on a mix of scale and products to drive installs and revenue and player engagement. And Unity needs to be able to quickly test, build, scale, deploy models, all at massive scale. This allows them to serve up the best results for their developers and their advertisers. Managed services. As I said, TensorFlow Enterprise will be available on Google Cloud and will be available as part of Google Cloud's AI platform. Will also be available in VMs if you'd prefer that, or in containers if you want to run them on Google Cloud Kubernetes Engine, or using Kubeflow on Kubernetes Engine. In summary, TensorFlow Enterprise offers enterprise-grade support, that continuation, that full 3 years of support that IT departments are accustomed to. Cloud scale performance so that you can run at massive scale, and works seamlessly with our managed services. And all of this is free, fully included for all Google Cloud users. Google Cloud becomes the best place to run TensorFlow. But there's one last piece, which is for companies for whom AI is their business. Not companies for whom AI might help with this part of their business or that, or might help optimize this campaign or this back-end system. But for companies where AI is their business, right, where they're training hundreds of thousands of hours of training a year, petabytes of data, right? using cutting-edge models. To meet their unique requirements, we are introducing TensorFlow Enterprise with white glove support. This is really for cutting-edge AI, right? Engineering to engineering assistance when needed. Close collaboration across Google allows us to fix bugs faster if needed. One of the great opportunities of working in cloud, if you ask my kids, they'll tell you that the reason I work in cloud AI and in kind of machine learning is in an effort to keep them ever from learning to drive. They're 8 and 10 years old, so I need people to kind of hurry along this route, if you will. But one of the customers and partners we have is Cruise Automotive. And you can see here, they're a shining example of the work we're doing on their quest towards self-driving cars. They've also experienced hiccups and challenges and scaling problems. And we've been a critical partner for them in helping ensure that they can achieve the results they need to solve this kind of generational defining problem of autonomous vehicles. You can see not only did we improve the accuracy of their models, but also reduce training times from 4 days down to 1 day. This allows them to iterate at speeds previously unthinkable. So none of this, as I said, would have been possible without the close collaboration between Google Cloud and TensorFlow. I look back on Megan's recent announcement of TensorBoard.dev. We will be looking at bringing that type of functionality into an enterprise environment as well in the coming months. But we're really, really excited to get TensorFlow Enterprise into your hands today. To learn more and get started, you can go to the link, as well as sessions later today. So if you are on the cutting edge of AI, we are accepting applications for the white glove service as well. We're excited to bring this offering to teams. We're excited to bring this offering to businesses that want to move into a place where machine learning is increasingly a part of how they create value. Thank you very much for your time today.
Thanks, Craig. So to learn more about the technologies being covered at this conference, we invite you to start your free 90-day membership to O'Reilly Learning, our online platform of expert content and training. In addition to thousands of books from the leading tech publishers, the O'Reilly Learning platform also has live online trainings, audiobooks, playlists, and of course, conference videos from all O'Reilly events. We'll also have a premium compilation of TensorFlow World video content. So make sure you stop at the O'Reilly booth to activate your free O'Reilly Learning membership. Our next speaker is Kamal El Mujahid. He is the product director for TensorFlow at Google. He is passionate about solving big problems with AI and building developer communities. Please welcome Kamal El Mujahid.
We have a very lively machine learning community in Brazil. If they come to a roadshow, if they're part of a community, they start to understand that they can be part of something so much bigger.
It's been an amazing event here at the TensorFlow Lagos Roadshow. Seeing the AI community in Nigeria is very amazing and inspiring.
I 也是来听讲的，就是来听一听TensorFlow 的一些最新的一些进展，然后认识一些TensorFlow 的一些开发者。
For me, the main object to attend to conference like this is to meet people and to network and to see what are the challenges and what are their solutions about machine learning problems.
It's fun to work with these tools, but it's more interesting when you see people that build them, or people that work underground to make these tools available for you.
Part of what TensorFlow is now is just due to the enormous engagement of developers everywhere around the world.
TensorFlow 2.0 doc sprint in Lagos gave back to the TensorFlow Lagos community, and the TensorFlow Lagos community right now organize events monthly.
在中国，其实我们可以看到，今年中国的 TensorFlow 社区发展的非常快。首先推出了一个叫做 TFUG TensorFlow Youth Group。
I like to teach and provide the biggest amount of information so the community grows faster. The biggest the community gets, the better for us, the better for my work, the better for the country.
It's actually amazing, being part of the community. You meet people who are passionate about what they are working on, and that will actually inspire you. When the community moves forward, you also move forward with the community.
Hi, my name is Kamal. I'm the product director for TensorFlow. So earlier you heard from Jeff and Megan about the product direction. Now what I'd like to talk about is the most important part of what we're building, and that's the community. That's you. Sorry, previous slide. Thank you. So as you've seen in the video, we've had a great roadshow. 11 events spanning 5 continents to connect the community with the TensorFlow team. I personally was very lucky this summer because I got to travel to Morocco and Ghana and Shanghai, amongst other places, just to meet the community and to listen to your feedback. And we heard a lot of great things. So as we're thinking about how can we best help the community, it really came down to 3 things. First, we would like you to help you to connect with the larger community and to share the latest and greatest of what you've been building. Then we also would like you, we want to help you learn about ML, learn about TensorFlow. And then we want to help you contribute and give back to the community. So let's start with Connect. So why Connect? Well, first, the community, the TensorFlow community, has really grown a lot. It's huge. 46 million downloads, 2,100 committers. And again, I know that we've been saying that all along, but I really want to say a huge thank you on behalf of the TensorFlow team for making the community what it is today. Another aspect of the community that we're very proud of is that it's truly global. This is our revised map of our GitHub stars. And as you can see, we're covering all time zones, and we keep growing. So the community is huge. It's truly global. And we really want to think about how can we bring the community closer together. And this is really what initiated the idea of TensorFlow World. We wanted to create an event for you. We wanted an event where you could come up and connect with the rest of the community and share what you've been working on. And this has actually started organically. 7 months ago, the TensorFlow user group started, and I think now we have close to 50. The largest one is in Korea, has 46,000 members. We have 15 in China. So if you're in the audience or in the live stream and you're looking at this map and you're thinking, wait, I don't see a dot where I live, and you have a TensorFlow member that you're connecting with, and you want to start a TensorFlow user group, well, we'd like to help you. So please go to tensorflow.org/community, and we'll help you get it started. So that next year, when we look at this map, we have dots all over the place. So what about businesses? We talked about developer. What about businesses? One thing we heard from businesses is, they have this business problem. They think ML can help them, but they're not sure how. And that's a huge missed opportunity. When we look at the staggering $13 trillion that AI will bring to the global economy over the next decade. So you have those businesses on one side, and then you have partners on the other side, who know about ML, they know how to use TensorFlow. So how do we connect those two? Well, this was the inspiration for launching our Trusted Partner Pilot Program, which helps you as a business connect to a partner who will help you solve your ML problem. So if you go on tensorflow.org, you'll find more about our Trusted Partner program. Just a couple examples of cool things that they've been working on. One partner helped a car insurance company shorten the insurance claim processing time using image processing techniques. Another partner helped a global med tech company by automating the shipping labeling process using object recognition technique. And you'll hear more from these partners later today. I encourage you to go check out the talks. Another aspect is that if you're a partner and you're interested in getting in this program, we also would like to hear from you. So let's talk about Learn. We've invested a lot in producing quality material to help you learn about ML and about TensorFlow. One thing that we did over the summers was really exciting is for the first time, we were part of the Google Summer of Code. We had a lot of interest. We were able to select 20 very talented students, and they got to work the whole summer with amazing mentors on the TensorFlow engineering team. And they worked on very inspiring projects, going from 2.0 to Swift, to JS, to TF agents. So we were so excited with the success of this program that we decided to participate for the first time in the Google Coding program. So this is the same program, but for pre-university students from 13 to 17. It's a global online contest, and it introduces teenagers to the world of contributing to open source development. So as I mentioned, we've invested a lot this year on ML education material. But one thing we heard is that there's a lot of different things, and what you want is to be guided through pathways of learning. So we've worked hard on that. I'm excited to announce the new Learn ML page on TensorFlow.org. And what this is learning path curated for you by the TensorFlow team and organized by level. So you have from beginners to advanced. You can explore books, courses, and videos, help you improve your knowledge of machine learning, and use that knowledge and use TensorFlow to solve your real-world problem. And for more exciting news that will be available on the website, I'd like to play a brief video by our friend Andrew Ang.
Hi everyone, I'm in New York right now and wish I could be there to enjoy the conference, but I want to share with you some exciting updates. DeepLearning.ai started a partnership with the TensorFlow team with the goal of making world-class education available for developers on the Coursera platform. Since releasing the deep learning specialization, I've seen so many of you, hundreds of thousands, learn the fundamental skills of deep learning. I'm delighted we've been able to complement that with the TensorFlow in Practice specialization to help developers learn how to build ML applications for computer vision, NLP, sequence models, and more. Today, I want to share with you an exciting new project that the DeepLearning.ai and TensorFlow teams have been working on together. Being able to use your models in a real-world scenario is when machine learning gets particularly exciting. So we're producing a new full-course specialization called TensorFlow Data and Deployment that will let you take your ML skills to the real world, deploy models to the web, mobile devices, and more. It will be available on Coursera in early December. I'm excited to see what you do with these new resources. Keep learning.
All right. This is really cool. Since we started working on these programs, it's been pretty amazing to see hundreds of thousands of people take those courses. And the goal of these educational resources is to let everyone participate in the ML revolution, regardless of what your experience with machine learning is. And now contribute. So a great way to get involved is to connect with your GDE. We now have 126 machine learning GDEs globally. We love our GDEs. They're amazing. They do amazing things for the community. This year alone, they gave over 400 tech talks, 250 workshops. They wrote 221 articles, reaching tens of thousands of developers. And one thing that was new this year is that they helped with doc sprints. So docs are really important. They're critical, right? You really need good quality docs to work on machine learning. And often the documentation is not available in people's native languages. And so this is why we, in partnership with our GDEs, we launched the doc sprints. Over 9,000 API docs were updated by members of the TensorFlow community in over 15 countries. We heard amazing stories of the power outage and power running out, and people coming back later to finish a doc sprint and actually writing docs on their phones. So if you've been helping with docs, and thank you, if you're in the room over Livestream, thank you so much. If you're interested in helping translate documentation in your native language, please reach out, and we'll help you organize a doc sprint. Another thing that the GDEs help with is experimenting with the latest features. So I want to call out Sam Vitivin, an ML GDE from Singapore, who's already experimenting with 2.xn TPUs. And you can hear him talk later today to hear about his experience. So if you want to get involved, please reach out to your GDE and start working on TensorFlow. Another really great way to help is to join a SIG. A SIG is a special interest group, and it helps you work on the things that you're the most excited about on TensorFlow. We have now 11 SIGs available. Add-ons, I/O, and networking in particular really supported the transition to 2.0 by embracing the parts of Contrib and putting them into 2.0. And SIG build ensures that TF runs well everywhere on any OS, any architecture, and plays well with the Python library. And we have many other really exciting SIGs, so I really encourage you to join one. Another really great way to contribute is through competition. And for those of you who were there at the Dev Summit back in March, we launched our 2.0 challenge on DevPost. And the grand prize was an invitation to this event, TensorFlow World. And so we would like to honor our 2.0 challenge winners. And I think we are lucky to have two of them in the room, Victor and Kyle, if you're here. So Victor worked on handtrack.js, a library for prototyping hand gesture in the browser, and then Kyle worked on a Python 3 package to simulate n-body, to generate n-body simulations. So one thing we heard too during our travels is, oh, that hackathon was great, but I totally missed it. Can we have another one? Well, yes, let's do another one. So if you go on tfworld.devpost.com, we're launching a new challenge. You can apply your 2.0 skills and share the latest and greatest and win cool prizes. And so really excited to see what you're going to build. Another great community that we're very excited to partner with is Kaggle. So we've launched a contest on Kaggle to challenge you with a question answering model based on Wikipedia article. You can put your natural language processing skills to the test and earn $50,000 in prizes. It's open for entry until January 22nd, so best of luck. So we have a few action items for you, and they're listed on this slide. But remember, we created TensorFlow World for you to help you connect and share what you've been working on. So our main action item for you in the next 2 days is really to get to know the community better. And with that, I'd like to thank you, and I hope you enjoy the rest of TF World. Thank you.
Thanks, Kamal. That's awesome. So many ways to get involved.
Our thanks to IBM for sponsoring this afternoon's break in the Expo Hall. Please plan to join us at 5:45 p.m. tonight for our reception. Have a drink, some delicious food, and network with other TensorFlow World attendees, and visit our sponsors who are leading the charge in TensorFlow.
Now, from 7 to 10 p.m. tonight, join us at California's Great America for Tensor Treat, the official attendee party. Halloween costumes are encouraged, but not required, Ben. But it will be a fun evening filled with great food, drinks, and a chance to relax with your peers here at TensorFlow World. Be sure to bring your conference badge to get in, and we'll be meeting over by the conference registration to either walk over together or get a pedicab.
And now, Please join us for our morning break in the expo hall. Afterward, the program splits into sessions, so check out the online schedule for the latest details.
Don't forget, if you're on the live stream, the course sessions will resume after the break. And otherwise, join us bright and early tomorrow morning. We have some amazing demos set out for you. So have a great day.
Welcome to the TensorFlow YouTube channel. On this channel, we'll have a lineup of great shows for you, including Coding TensorFlow, where we explore what it is to write TensorFlow code together. TensorFlow Lite is TensorFlow's lightweight solution for mobile and embedded devices. Here's a sample piece of code. TensorFlow Meets, where you are the star, and we get to meet with you to talk and to learn and to share about all of the great things that you're doing with TensorFlow.
Just learning the basic mechanics and concepts, but seeing how it actually applies to their field.
I like this combination a lot.
There's also Ask TensorFlow, where we answer your questions marked on social media with the Ask TensorFlow hashtag.
What is the difference between TensorFlow Mobile and TensorFlow Lite?
One's mobile, the other's light.
That's right.
We'll also have lots of great content from events like the TensorFlow Developer Summit and special guests from other parts of Google and beyond. So hit that subscribe button now, and we'll see you there.
Consultare documenti storici, soprattutto documenti medievali, richiede sempre molto tempo, molta pazienza. In Archivio Vaticano abbiamo 85 km lineari di documenti, più o meno la lunghezza del Canale di Panama. Le scritture scritte nel Medioevo sono diverse da quelle che noi conosciamo. Se qualcuno mi chiedesse un giorno di trascrivere e tradurre tutti i documenti dell'Archivio Vaticano, sicuramente gli direi che è un matto.
Looking at this book, page by page, and trying to decipher, read and transcribe whatever is there takes an enormous amount of time. You would require an army of paleographers.
What I'm excited the most about machine learning is that it enabled us to solve problems that up to 10-15 years ago we thought unsolvable.
In Codice Razzi è nato da quest'idea di costruire un software per poter interpretare, per poter leggere quello che è scritto dentro i manoscritti. Quando abbiamo iniziato ad approcciare il problema ci siamo resi conto che una soluzione basata su reti neurali fosse assolutamente necessaria. La scelta su TensorFlow è stata abbastanza naturale.
Before using any kind of machine learning model, we needed to collect data first. You have thousands of images of dogs and cats in the internet, but there is very little images of ancient manuscripts. We built our own custom web application for crowdsourcing, and we involved high school students to collect the data. I didn't know much about machine learning in general, but I found it very easy to create a TensorFlow environment. When we were trying to figure out which model worked best for us, Keras was the best solution. The production model runs on TensorFlow layers and estimator interface. We experimented with binary classification with fully connected networks, and finally we moved to convolutional neural network and multi-class classification.
In poco tempo siamo riusciti a sviluppare e a testare le prime soluzioni.
When it comes to recognizing single characters, we can get 95% average accuracy.
Poter accedere a uno strumento informatico abbrevia notevolmente. Sciogliere certe abbreviazioni, comprendere un testo in quella scrittura così criptica è un qualcosa di eccezionale.
This will have an enormous impact. In a short period of time, we will have a massive quantity of historical information available.
I just think solving problems is fun. It's a game against myself and how good I can do.
Lo studio della storia è importantissimo per comprendere il nostro presente e per avere anche una prospettiva per il futuro.
Hello, my name is Alejandra.
And I'm Erickson.
And we're using machine learning to find potholes on the streets of Los Angeles.
LA has over 7,400 miles of roads and freeways.
That's a lot of roads and a lot of potholes to fix.
Right now, construction workers have to manually inspect roads for dangerous potholes and cracks, or rely on people calling in tips, which takes a lot of time.
While studying at LMU, we started to see if we could figure out a faster way to identify potholes throughout the city.
First, we needed data. So we rigged a camera to a car and we drove around to capture footage of different roads and freeways.
Then, we used TensorFlow, Google's open-source machine learning tool, to develop a model that could quickly identify potholes, road cracks, and other weird stuff, with a high rate of accuracy. Which means workers can spend less time finding potholes and more time fixing them.
You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code, predict the y when x equals 10? You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you.
हमारा खेत था तो जाते थे दोस्तों के साथ खेलते थे और वहाँ पे सारा मजा आता था फिर नदी आ गई तो काट लिया
घाघरा नदी सारे काट लिया गांव को कोई सूचना मिलती ही नहीं है अगर कोई सूचना मिलती तो हम लोग को मदद मिलते कोई मदद नहीं है हमारे लोगों को
Aid agencies are struggling to get help to millions of people affected by devastating floods across South Asia. It's thought to be the worst monsoon.
Thousands of troops have already been pressed into action.
It was extremely frightening because we had no warning.
One of the most important variables during a crisis is reliable information. There's so much work that's already been done by governments, by the UN and NGOs, and we're trying to learn from that work, build on that, and assist them with their goals. In India, where we're running our first pilot program, the government has thousands of people who are measuring the water level in rivers across India with what is effectively very long measuring sticks, which are called stream gauges, every hour, which allows them to know whether the river will overflow and flood, but it doesn't yet allow them to understand exactly what areas are going to be affected, what neighborhoods, or even what villages.
Any station calling? Any station?
चेतावनी में तहसील से साहब मिलती है अधिकारी जो हमारे होते हैं कर्मचारी वो हमें सभी सतर्क कर देते हैं कि बाढ़ आने वाली आप लोग ऊंचे आ जाइए जितने नुकसान हैं उससे पहले पता चल जाएगा.
The response time is most crucial thing. Reducing the response time always plays very important and vital role in the whole disaster management framework. Advancement in technology would help us better in spreading this message faster.
Flood forecasting was a very exploratory project. The big technical question was, can we have enough information to try to do forecasting that would be accurate enough to make a difference? Starting with the basic needs for getting information about what's going on, where is it happening, what should I be doing?
To be able to provide a forecast in real time, we rely on the government we're working with. We complement their effort by adding accurate modeling to that process. We start by collecting thousands of satellite images to build a digital model of the terrain. Based on these maps, we generate hundreds of thousands of simulations of how the river could possibly behave. We receive the measurements from the government and cross those measurements with our simulations. We can then send those forecasts to individuals using search, maps, and Android notifications. This is an example of an alert that we can produce. This alert is for Patna. This alert has over 90% accuracy. The lead time is incredibly important, even more than the specifics.
Any information we can give, they will use.
You want to show them the alert? Talking to people who directly experience severe floods and understanding what they really need is incredibly important for us to know how we can really help.
This is an opportunity to collaborate in a global scale. We are in very exciting time to use technology to try to make a difference.
I can't imagine a greater privilege than to do what we love and do it in a way that could actually help people directly in a very profound way.
Our hope for the future is to give people a few more days of warning before a flood occurs, and to use AI to scale this and provide these forecasts anywhere in the world, wherever people need them.
Extreme weather is changing. There's more extreme rainfall, heavy flooding, forest fires. There isn't really a signature done. Being able to predict these extreme events more accurately is kind of the big challenge that we're facing right now. There's 100 terabytes of climate data every day from satellites, from observations, from models. So climate data is a big data problem. We need things that are fast, that can sift through all of that data rapidly and accurately. And deep learning is almost perfectly poised for problems in climate science.
A lot of NERSC users are using TensorFlow. It's one of the more popular frameworks. We use TensorFlow to iterate quickly over different models, different layer parameters. For this particular climate project, to create the deep learning model, we started from segmentation models which have proven to be successful, for example, our satellite imagery segmentation tasks. And then we used TensorFlow to enhance the models until we found like a set of models which perform well enough for this specific task. But for the volume of the data, complexity of the data, the network required 14 teraflops. So if you want to do this on your workstation, it would take like months to train.
To really tackle these problems requires the largest computational resources that are available on the planet. So systems like the Summit supercomputer. 2 tennis courts in total size. I mean, this thing is state-of-the-art. It's 1 million times faster than your common laptop. 3.3 exaflops. Just imagine what you do at your workstation, but now imagine having 27,000 times that power. We can do that now.
We were surprised how good it actually scales. 1,000 nodes, and 2,000 nodes, 5,000 nodes.
This was the first time anybody's ever run an AI application at this scale. Instead of having the climate scientists figure out how to write high-tune code, they could express things in a very natural way in Python in TensorFlow and get all the high-performance code that most HPC people are used to within TensorFlow.
We're now entering the space where AI can actually contribute to the predictions of these extreme weather events.
When you combine traditional HPC with AI, you can tackle things we never thought that we could tackle. Fusion reactor research, understanding diseases like Alzheimer's, cancer, right? That's like incredible.
We've shown that with a high productivity framework such as TensorFlow, you can get to massive scale and you can get like awesome performance and accomplish your goals.
Genetics, neuroscience, cosmology, high energy physics. That's immensely exciting for me.
Hello, everyone. Welcome. My name is Ashley. I will be your host for today. We'll get the show on the road. I would like to introduce our first speaker, Josh Gordon, who's on the TensorFlow team. Josh is going to talk about the ease of TensorFlow 2.0 and will walk us through the three styles of model building APIs complete with coding examples. So please help me in welcoming Josh.
Thanks so much. How's it going, everybody? So let me just unlock this laptop, and then we will get started. So I have only good news about TensorFlow 2.0, which is about a month old. It's wonderful. It is massively easier to use, and it's great both for beginners and for experts. And also from a teaching perspective, it has a lot of things to recommend it that I'll talk about too. And no big deal, but maybe we can close the doors in the back. It's a little bit loud. Thanks. All right, so I'm going to get into an outline in a sec, but one thing I wanted to mention right off the bat is TensorFlow 2 has all the power of graphs that we had in TensorFlow 1, except they're massively, massively, massively easier to use. In TensorFlow 1, the name TensorFlow, a tensor is basically a fancy word for an array. So a scalar is a tensor, a list is a tensor, a cube is a tensor. And flow refers to a data flow graph. And in TensorFlow 1, you would manually define a graph, and you would execute it with a session. And this felt a little bit like metaprogramming. And this is exactly the system you would have wanted several years back if you were an engineer and the challenge you faced was massively distributed training, because graphs are great for that. However, as a developer or a student or as a researcher, you want something that feels a lot more like Python. And on the right, you're seeing how TensorFlow 2 looks. Basically, you can think of a tensor in a very similar way to a NumPy ND array, and you can work with them imperatively, exactly as you would expect in Python. So you no longer need to use things like sessions or anything like that. And it works as you would expect, which is great. But that's low-level details, and here's some of the things I'd like to talk about. So this is a rough schematic of how TensorFlow 2 looks. And TensorFlow 2 is a very, very large system with many moving pieces. It's a whole framework for doing machine learning. And what I'd like to do here is show you a couple of the pieces and what some of your options are to use it. So we will start with designing models using my favorite API of all time, which is Keras. And what's awesome in TensorFlow 2, and this is a really important point, there's a spectrum of use cases. And all of these are built into the same framework, and you can mix and match as you go. And what this means is if you're a total novice to deep learning, you can start with something called the sequential API, which is by far the easiest and clearest way to develop deep learning models today. And it's wonderful. You can build a stack of layers, you can call things like compile and fit, and that is 100% valid TensorFlow 2 code. It is just as fast as any other way of writing code. There's no downsides to it at all if your use case falls into that bucket. And what's really important in TensorFlow 2 is, as is helpful to you, you can optionally scale up in complexity using things like the functional API or going all the way to subclassing, all in the same framework, and you can mix and match as you go. And what this means is when I'm teaching this, for example, I can start in these really simple, clear, easy ways, and then when I want to write gradient descent from scratch, I can do that. Or write custom layers from scratch, I can do that, and it's very easy. So let's take a look at what some of these pieces look like. And I only have one slide on sequential, and the reason is we have so many tutorials on it. There's an entire book on it, which I'll recommend at the end. So I have just one slide on this. But in case you're new to this, the sequential API lets you define a stack of layers. And this is by far the most common way to build your models, and something like, I'd say 80 to 90% of machine learning models will fit into this framework. So you define a stack of models, and that's great. What's interesting is when you're using the sequential API and the functional, although a lot of developers don't realize this, what you're actually doing is defining a data structure. And this means you can do things like model.summary and see a printout of all the layers and all the weights. It also means that we can do compile time checks. So when you call model.compile, we can make sure all your layers are compatible. It also means that when you share your model with other people, for example, imagine that you want to do fine-tuning for transfer learning. If you have a model that's defined with the sequential API or the functional API, because it has a data structure of a stack of layers, or with the functional API, a graph of layers, you can inspect that data structure. And you can pull layers out of it and get the activations, and you can do fine-tuning and things like that really easily. Anyway, defining a stack of layers is very common. In TensorFlow 2, this works exactly like it does at Keras.io with the multi-backend Keras. So that's great. One thing that's also extremely powerful that a lot of people are new to is the functional API. And the sequential API is for building stacks. The functional API is for building DAGs, or directed graphs. And I just want to show you how powerful this is. So to be honest, most of what I've been doing myself is using either the sequential API or going all the way to subclassing and just write everything from scratch. But I heard a really awesome talk on the functional API a couple weeks ago in Montreal, and I've been using it a lot since, and I love it. So I just want to show you what it can do. And so I just want to show you what a quick model would look like for something like visual question answering. And a lot of the time when you start with machine learning, you spend a lot of your time, or deep learning rather, you spend a lot of your time building image classifiers and doing things like cats and dogs. But we can take a look at a slightly more sophisticated model, and this is VQA. And in VQA, you're given two inputs. One, you're given an image. So here we have a pair of dogs, and you're given a question in natural language. And here the question is asking, what color is the dog on the right? And so to answer a question like this, you need a much, much, much more sophisticated model than just an image classifier. You can still phrase this as a classification problem. And if you Google for VQA, there's two really excellent papers that will go into detail. But you can imagine, you have some model. Well, let's talk about how we would do this. Here we have a model with two inputs. We have an image and a question. And if you take a machine learning course, or deep learning course rather, you'll learn about the processing images with convolutional layers and max pooling layers, and you'll learn about processing text with things like LSTMs and embeddings. And one thing that's really powerful about deep learning is all of these layers, regardless of what they are, they take vectors as input. And if you're a dense layer, you don't care if your input happens to be the output of some convolutional layer, or if your input happens to be the output of some LSTM. It's just numbers that you're taking as input. So in deep learning, there's no reason that we can't process the image with a CNN, process the text with an LSTM, and then concatenate the result and feed that into a dense layer and phrase this as a classification problem. So you can imagine the output of our dense layer might have 1,000 different classes, and each class corresponds to one possible answer. So here, if the answer is golden, we want to classify both of these inputs jointly as golden. And I want to show you how quickly we can design something like this with the functional API, which is really amazing. So cool, I probably should have flipped to this slide, but this is what I was just talking through. So this is the architecture that we want. This is one model, and it's going to have two heads. And the first head is going to be a standard stack of CNNs and max pooling layers. And this is exactly the same model you would use to classify cats and dogs. And you can do all the same tricks that you will learn about there. You can import, like here, I want to show you how to write it from scratch, but there's no reason that you couldn't import like MobileNet, V, whatever, and use that to get activations for the images. But basically, we're going to go from an image to a vector, and in the other head, we're going to process the question. And we're going to go from a question to a vector. And to do that, we use an embedding in an LSTM. At the end, we concatenate the results and classify it. And this is nearly the complete code for this entire VQA model. Actually, it is the complete code for the model, a Hello World version of it, which is nuts when you look at it. So here, this is our image classifier. And you would want something much deeper, but this would be your Hello World image classifier. So a vector is going to go in, and just some random tips. I can see my slides, that's cool. So you'll notice in the first layer, this is a convolutional layer. It has 64 filters, each of which is 3 by 3, and it has ReLU activation. And you see in the input shape there, I'm specifying how large my image is. Although you'll find that Keras can often infer the input shape. Whenever you can, you should specify it. And it's just one less thing that can go wrong. So fully specify it, catch bugs early. After that, we're doing max pooling, and the important part is we're flattening it. So that's actually a sequential model that we're using inside the functional API. After that, we're creating an input layer, and this is for the functional API, and we're beginning to chain layers together to build up a graph. So here what we're doing is we're chaining the vision model to the input layer. So that's the first half of our model. And here's the second half, and we're almost done. So this is the model that's going to process the question. Here we're creating another input, and I don't have the pre-processing here, but you can imagine that we've tokenized the text, and we've vectorized it, we've padded it. And then what we're doing is we're feeding that into an embedding, and then into an LSTM. And this is exactly what you might do if you were training a text classifier. The important thing is that a vector is coming out, and we're chaining these together to build a graph. And at the very end, and this is the magic bit about deep learning, we can simply concatenate the results. Nothing simple, but it's one line of code, which is nice. Nothing simple conceptually. But what we can do is we can concatenate the results, and now we just have a vector. And just like any other problem, now that we have this vector, we can feed it into dense layers, and we can classify it. And so here's the tail of our model. And now we have a TensorFlow 2 model that will do VQA, and this will work exactly like any other Keras model. So if you want, you can call model.fit on this thing. You can call model.trainOnBatch. You can use callbacks. If you want, you can write a custom training loop using gradient tapes. And so I think this is really powerful. And what's nice about these functional APIs, just like sequential models, because there's a data structure behind the scenes, there's a graph. TensorFlow 2 can run compatibility checks and make sure your layers work with each other. So it's really, really nice. So basically, if you haven't used the functional API, either you just learned about Keras sequential from a lot of books, or you're coming from PyTorch and you've only used things like subclassing, I really encourage you to try it out. I've had only positive results in the last few weeks, so I love it. Other things, of course, so that graph I just made in Google Slides, but because you have a data structure, instead of calling something like model.summary, you can call model plot model, and you'll actually get a nice rendering of a graph that looks exactly like what I just showed you. So for complicated models, so this is cool. The only time I found it really useful is when you have complicated models, things like ResNets, you can actually plot out the whole graph and just make sure that it looks as you expect as you're assembling it. So it's really nice. Anyway, and then there's another style in TensorFlow 2. So the last two things I showed you were built into what you'll find at keras.io, and that's multi-backend Keras. Keras in TensorFlow 2 is a superset of what you'd find at keras.io, and this is something that's new. So this is subclassing, and this is a Chainer/PyTorch style of developing models, which is also really, really nice. And basically, you'll see this little spectrum here. You're getting increasing control as you move up. And so in this style, you can be a researcher or a student learning this for the first time, but what you're saying is, I just want to write everything from scratch to learn how it works, or because I have some special use case that doesn't fit into the other ones. So here what we're doing is we're defining a subclass model. And I also really love this. This feels a lot like object-oriented NumPy development. So what we're doing, and the idea is basically, it's very, very similar in all of these frameworks. The framework gives you a class, and here this class happens to be model. And there's two chunks to writing a subclass model. You have the constructor and the call method, or the forward method, or the predict method. And in the constructor, you define your layers. So here I'm creating a pair of dense layers, and it's the exact same layers that you'd find in the sequential and the functional model APIs, which is great. So basically, you learn these layers once, and you can use them all over the place. And in the call method or the forward method, you describe how these layers are chained together. So here I have some inputs, and I'm feeding the inputs through my dense layer, and then I'm feeding that result through my second dense layer and returning it. And what's nice is this is not symbolic. So if you're curious what x is, you can just do print x, of course, like you would in Python, and that will give you the activations of that first dense layer. If you want, you can modify it. So for example, here I've highlighted ReLU. Let's say for some reason I'm not interested in using the built-in ReLU activation. I want to write my own. What you can do simply is just remove that, and you can write your own with just regular Python flow right there. So there I've written ReLU using the built-in method, but I could also just write that using regular Python. So this is great for hacking on things. It's great if you want to really know the details of what exactly is flowing in and out of these layers. It's a perfect way to do it. Also, for example, there's nothing here that's saying that you have to use these built-in dense layers. So if you look at the code for the dense layer, that's doing something like wx plus b. You can absolutely just write that from scratch in Python and use that here instead. And then these are just a whole bunch of references. I'm going to tweet out these slides when we finish, so you don't have to write it down. But what these are guides from TensorFlow 2 that will go into detail on how do you use each of these three styles of the Keras API, how do you write custom layers and stuff like that. They're great. And then we have a couple tutorials that I recommend that are really, really nice that show different ways of building stuff. If you haven't seen these, by the way, the segmentation one is super nice. We wrote it this summer. It runs really, really fast, and I think you'll like it. Also, by the way, because this is an intro to TensorFlow 2 talk, let me just show you what the tutorials are in case you're new to these. And there's just one thing I want to point out. So this is a tutorial on our website. Big surprise. What I wanted to mention, and I think this is a really nice feature of TensorFlow.org, obviously this is a web page, HTML, but this is just a direct rendering of this Jupyter Notebook. So the web page is just the Jupyter Notebook, and the reason we've done that is all of the tutorials are runnable end-to-end. So you can install TensorFlow 2 locally and run this tutorial, or if you click Run in Colab, this is exactly the same page as you have on TensorFlow.org. For all of these, you can do runtime run all, and this has the complete code to reproduce the results that you see here. And what this means is that our tutorials are testable. And do you know the expression trust but verify? So for a long time, I've seen like nifty tutorials that are like, yeah, like let me show you how to write this like neural machine translation model. And then the code doesn't work. Or it's missing, you know, a key piece that's left as an exercise to the reader. So at least all the tutorials on the website, all of them run end to end, which is really, really nice. Some, we still have plenty of work to do cleaning them up, but at least they guarantee you they have the complete code to do the thing. So I really like that a lot. All right, I want to talk a little bit about training models. And so basically, there are several ways to train models. And again, you can use, the nice thing about TensorFlow 2 is you can use the one that's most helpful for your use case. So you don't always need to write a custom training loop from scratch. So you have other options. And the first is that you might be familiar with from Keras is just simply calling model.fit. And what's really nice about model.fit, it doesn't care if you have a sequential model, a functional model, or a subclass model. It works for all of them. And model.fit, it's fast, it's performant, it's simple. One thing that's a little bit less obvious, when you do model.fit, this is not just the baby way of training models. So if you're working in a team and you call model.fit, you've reduced your code footprint by a lot. This is one less thing that your friends need to worry about when they're playing with your models down the road. So if you can use the simple things, you should, unless there's a reason for more complexity, of course, just like in regular software engineering. The nice thing about fit is you can pass in different metrics. And a lot of examples, you'll see things like accuracy. By the way, TensorFlow 2 has really nice metrics for things like precision and recall built in. You can also write custom metrics. And something that's really helpful too is callbacks. So for instance, these are things that I don't see a lot of new developers using, and they're super helpful. So callbacks, and one of my favorites is early stopping. And so typically, you know, when we're training models, we need to prevent overfitting. And a really wonderful way to do that is to make plots of your, you know, loss over time and so on and so forth. These callbacks can do things like that for you automatically, which can be helpful as well. You can also write custom callbacks. So a cool thing would be, like, let's say you're training a model that takes a very long time to train. You could write a callback to send you a Slack notification after every epoch of training completes. And so that can be really nifty too. So callbacks are great. And then I don't have slides for train on batch here, but I did want to show you custom training with a gradient tape, because this is also very powerful. Especially for students who are learning this for the first time and don't want a black box, or for researchers. And so here's a custom training loop, and I have an example of this for you in a minute, just with linear regression, so you can see exactly how this works. But this is a custom training loop, and what we're doing here is we have some function, and for now you can pretend that @tf function in the orange box doesn't exist. So that's optional, so just pretend that doesn't exist. We have some function that's taking features and labels as input, and whenever we're doing training in deep learning, we're doing gradient descent. The first step in doing gradient descent is getting the gradients. And the way all frameworks do this is by backprop, which is reverse mode autodiff, and the implementation in TensorFlow is we start recording operations on a tape. So here we're creating a tape, and we're recording what's happening beneath that tape. So we have just regular Python code that's calling the forward method, or the call method rather, on your model. So we forward the features through our model, then we're computing some loss, and maybe we're doing regression, and that's squared error. And then what we're doing is we're getting the gradients of the loss with respect to all the variables in the model. And if you print those out, you'll see exactly what the gradients are. And then here we're doing gradient descent manually. We're applying them on an optimizer. We can also write our own optimizer, and I'll show you that in a second. Anyway, this is a custom training loop from scratch. And what this means is that if you, so in model.fit, you can use optimizers like RMSprop and Atom and all this stuff. But if you'd like to write like the Sarah optimizer, you can go ahead and write it in Python, and it will fit right in with your model. So this is great for research. TF function, by the way, first of all, you never need to write it. Your code will work the same. But if you do want a graph in TensorFlow 2, or if you want to compile your code and have it run faster, you can write that TF function annotation. And what this means is that TensorFlow 2 will trace your computation, compile it, and the second and on time that you run this function, it will be much, much, much faster because it's running entirely in C++. So all there is to graphs in TensorFlow 2 is basically @tf function. But it's optional, you don't even need to use it. But it's easy performance if you need it. And then I just want to make this super concrete, because this is a getting started with TensorFlow 2 talk. There's a lot of awesome tutorials that will quickly show you on the website how to train, image classifiers and whatnot. But I think a good place to start too is just looking at linear regression. And the reason is it's gradient descent. All deep neural networks are trained by gradient descent. And a nice place to start is seeing exactly what that is. And because I have I know it's tiny, but because I have a graphic here on the left, I'm just briefly going to explain how linear regression works, and it's the same pattern for deep neural networks too, which is really surprising. So in linear regression or deep neural networks, you need three things. The first thing you need is a model, which is a function that makes a prediction. And so a model for linear regression that you might have learned in high school could be y equals mx plus b. We're trying to find the best fit line, and we can define a line, y equals mx plus b. That means we have two parameters or variables that we need to set. We have m, which is the slope, right? And we have b, which is the intercept. And by wiggling those variables, we can fit the line to our data. So on the right, you'll see a plot, and we have like a scatter plot with a bunch of points, and we have the best fit line. And the idea is, now that we have a model or line that we can wiggle, we need a way of saying or quantifying how well does this line fit the data. One way to quantify how well the line fits the data is squared error. What that means is you drop a line on the page, and then you measure the distance from your line to all the points. And you take the sum of the squares of that. The higher the sum of the squares is, the worse your line fits the data. The better your line fits the data, the lower the sum of the squares. So you can have a single number, which is called loss, that describes how badly your line fits the data. And then you want to reduce that loss, and you know that if the loss gets to a minimum, your line will fit the data well, and you found the best fit line. The way we reduce the loss is gradient descent. And on the left, you'll see a gradient descent plot. And we're looking at loss, or a squared error, as a function of two variables, m and b. And you can see that if we set m and b with a random guess to start, our loss is pretty high. And then as we wiggle them, we can reduce the loss. The trick is, how do we figure out which way to wiggle m and b? And briefly, I don't want to go on too much of a tangent, there's two ways to do that. If you forget calculus, you can find the gradient numerically. And it's not rocket science. You take m, and you wiggle it up a little bit, recompute your loss. Then you take m, and you wiggle it down a little bit, and you recompute your loss. You figure out which way makes the loss go down. That's the direction you're going to be wiggling m. You do the same thing for b. That's very, very slow, and there's faster ways to do it too. But I want to show you what this code looks like in TensorFlow 2. So basically, you don't have to use Keras at all. You can also use TensorFlow 2 a lot like you would use NumPy. And basically, whenever you see something like tensor, just replace that in your head with NumPy and array. So we have constants, and you see if you print out a constant, it has a shape and a data type. One really nice thing about TensorFlow tensors is they have a NumPy method. So you can go straight from tensors to NumPy, which is great. So you're free of the clutches of TensorFlow 2. Tensors have a shape and a data type. And then just like you would expect in NumPy, we have things like distributions. So if you want to create some random normal, here's how you would do it. I just want to fly through this really quick. And you can do math in TensorFlow 2 a lot like you would do math in NumPy. So basically, just like you have things like numpy.square and numpy.matrix multiply, TensorFlow has all these same things too. And the idea is the same. The names might be slightly different. You might have to poke around a little bit, but the names are all there. And here's an example of very, very simple. Here's how we get the gradients using the gradient tape. But this is more concrete. So here we have a constant that's 3. And we have a function which is x squared. And so if you think about your rules of calculus, if we have 3x squared, you take the 2 and you multiply it by the 3 and you get 6. And if you walk through this code, you'll see that it returns you 6 too. So basically, this is how we get the gradients using the gradient tape. And you can also do that with all the variables and layers at once. So here we have a pair of dense layers, and we're calling the dense layers on some data, and we're getting the gradients also under the tape. And let me just show you what this looks like in linear regression, just to make this concrete. So this is code for y equals mx plus b. And the first thing I wanted to mention is how you install TensorFlow 2. If you're running in Colab, right now in Colab, TensorFlow 1 is installed by default. But there's a magic flag you can run. So that magic command will give you the latest version of TensorFlow 2. If you're running this locally, you can visit tensorflow.org/install, and you can do pip install TensorFlow. So anything you can do in Colab, you can do locally. But I have this here because it's convenient. TensorFlow is just a Python library. You can import it as you always would. And the first thing we do in this notebook, I know I flew through some of those code examples, but what we're going to do is just create a scatter plot. So just some random data, and then we're going to find the best fit line. So here what we're doing is we're creating some data. Let me see if I've run this before. Yeah. And then we're plotting the data, and here's what we get. The slides had TensorFlow constants, and these are TensorFlow variables, and basically constants are constant, and variables can be adjusted over time. You almost never need to write code this low level. This is pretending that we don't have Keras, we don't have any of these built-in fit methods, we just want to do this from scratch. But here's how you would do it from scratch. So I'm creating some variables. Here I've initialized them to 0. I probably should have initialized them to a random number, but this will work too. And then here, this doesn't look scary at all. This is the predict function for linear regression. So this is our equation for a line, y equals mx plus b. And our goal is going to be to find good values for m and b. Here's our loss function. And what we're doing is we're taking the results that we predicted minus the results that we wanted. We're squaring it, and we're taking the average. So that's squared error. And then as we go through this notebook, we can see our squared error when we start. And here's gradient descent from scratch, pretending that we didn't have anything like model.fit. So for some number of steps, what we're doing is we're taking our x's and we're forwarding through the model to predict our y's. We're getting the squared error, which is a single number, and then we're getting the gradients of m and b with respect to the loss. And this will literally tell us, if you print those out, those are just numbers, and the gradients point in the direction of steepest ascent. So if we move in the direction of gradients, our loss will increase. We want the loss to decrease, so we move in the reverse direction of the gradients, which is gradient descent. And here, again, this is like the lowest possible level way to write this code. We're doing gradient descent from scratch, so we don't have any optimizer. What we're doing is we're taking a step in the negative gradient multiplied by our learning rate, and that adjusts m and b as we go. And if you run this code, you'll see the loss is decreasing, and you'll see the final values for m and b. We can plot the best fit line. And then what I did for you is I wrote, this is a little bit uglier, but I wrote some code to produce this diagram, just so you can see exactly what the gradient descent is doing. So that's how you would write things from scratch in TensorFlow 2. And what's really, really awesome, when you move to things like neural networks, this code is basically copy and pasted. So if you can compare this custom training loop for linear regression to the custom training loop for Deep Dream, or any of the fancy models on the website, it looks almost identical. You always have this tape, and the steps are the same. You make a prediction, you get your loss, you get the gradients, and you go from there. So that's really nice. All right. Other things I wanted to mention. Oh, I got to move a lot faster here. So in terms of data sets, basically you have two options in TensorFlow 2. The first option is at the top, and these are all the existing Keras data sets that you'd find at keras.io. And these are great. They're good to start with. They're in NumPy format, and they're usually really tiny. They fit into memory, no problem. Then we have this enormous collection of research data sets, which is awesome, and that's called TensorFlow datasets. And here I'm showing you how you can download something like CycleGAN in TensorFlow datasets. What's important to be aware of, I just have a couple quick tips. If you're downloading a dataset in TensorFlow data format, by the way, it's going to give you something called, the dataset's not going to be NumPy, it's going to be in TF data. And TF data, it's a high-performance format for data. It's slightly trickier to use than what you might be used to. And so if you're using TensorFlow datasets, you have to be very, very careful to benchmark your input pipeline. If you just import a dataset and try and call model.fit on the dataset, it might be slow. So it's important to take your time and make sure that your data pipeline can read images off disk and things like that efficiently. And I have just a couple tips that might be helpful. TensorFlow datasets recently added an in-memory flag. So if you don't want to write fast input pipelines, you can pass in-memory, and you can slurp the whole thing into RAM. So that will make it really easy. And it also added this caching function, which is really, really nice. So here's some code for TF data. And maybe we have an image data set, and we have some code to pre-process the images. And let's pretend that that pre-processing code is expensive, and we don't want to run it every time we need to on every epoch. What you can do is you can add this cache line at the end. Cache will keep the results of the pre-processing in memory, and it will make subsequent runs of your pipeline much faster. So cache is a really handy thing to be aware of. The goal here is not to give you all the details for this. It's just to point you to some things that are useful to know about. You can also cache to files. So cache without any parameters will cache it into RAM. If you pass a file name, you can actually cache it to a file on disk too. One thing that's awesome in TensorFlow 2 that you, if you're an expert, you'll care about, and if not, you'll care about down the road, is distributed training. And I'm going to skip some slides to move faster. What I wanted to say briefly is distributed training in TensorFlow 2 is awesome, and it's awesome because if you're doing single machine, multiple GPU, synchronous data parallel training, or you're doing multi-machine, multi-GPU, synchronous data parallel training, you don't need to change the code of your model, which is exactly what I care about. And so it's awesome. And basically, here is some Keras model. This happens to be a built-in application for ResNet, but it doesn't matter. And I just want to show you how we run this code on one machine with multiple GPUs. We just wrap it in a block. That's it. And model.fit is distribute aware and will work. So you don't need to change your model to run it on multiple GPUs. And this particular strategy is called the mirrored strategy. There's different strategies you can use to distribute your models. There's another strategy, it's like mirrored multi-worker, which you can change that one line, and then if you have a network with multiple machines on it, again, your code doesn't change. So that's awesome. I really, really like the design of this. All right. Other things that are awesome about TensorFlow 2 that I'd really encourage you to check out, especially if you're learning or you have students, is going beyond Python. So we've talked about training models in Keras, and I just want to show you some of the cool things you can do to deploy them. And roughly, there's a bunch of different ways that you can deploy your models. The way that I was used to a few years ago as a Python developer was I throw up a REST API, and I can do that using like TensorFlow serving or Flask or whatever you want, and I serve the thing behind an API, because that's what I know how to do. There's a couple things that I've been learning since then, which have been great, and that's basically deploying models in the browser with TensorFlow.js, deploying them on Android and iOS using TensorFlow Lite, and very recently running them on Arduino using TensorFlow Lite Micro. And I have a couple suggested projects for you that I just wanted to point you to. So the first is it's TinyML, and this was a blog post, this was a guest article on our blog a few weeks ago by the Arduino team. And this article is basically a tutorial. And what we're looking at is an Arduino. It's a microcontroller. And if you're new to microcontrollers, it's a system on a chip, but it also has pins that it can run voltage to or read voltage from. And so, for instance, you can plug an LED light bulb into one of those pins, and you can have C code, which runs voltage to the pin and turns on the light. Likewise, you could have an accelerometer attached to one of the pins, and you could have C code that reads from the accelerometer and gives you some time series data. So that's what a microcontroller is. It's a computer plus these basically pins that you can read and write to. TensorFlow Lite is the code we use to deploy TensorFlow models onto phones. But recently, TensorFlow Lite Micro now lets you deploy them onto Arduino. And these things are smaller than a stick of gum. This is a really nice one. It has, this is a Nano that has built-in sensors. I have one at home, but it's still about 30 bucks. And it has a built-in accelerometer, a temperature sensor, stuff like that. But anyway, what we're looking at here, this is a demo using the accelerometer. Someone trained a model to recognize two gestures. One is like a punch and one is an uppercut. And you can see they're holding the Arduino in their hand, and as they're moving it, the laptop is recognizing the gestures. But the workflow, and this is in the blog post, is not bad at all considering how much power you're getting out of it. So what you're doing, and let me see if I can just show you the steps. Basically, the first thing you need to do is capture data. And I wanted to bring an Arduino with me. I thought it would be better just to quickly show you these GIFs. But you can plug the Arduino into your laptop with a USB cable. You need to collect training data for your model. So what you do is you hold the Arduino in your hand, and you collect a bunch of data for your punching gesture. And you save that to disk as a time series. And the diagram on the right there, I was just capturing the IDE this morning. As you move the accelerator, as you move the Arduino around, you're reading from the accelerometer, and what you get out is just a CSV file with time series data, exactly like you would have if you were looking through the time series forecasting tutorial on TensorFlow.org. And you can do the same thing for your other gestures. So what you do is you gather data, you save CSV files, you upload them to Colab. In Colab, you write a model using TensorFlow 2 and Keras to classify the data. And that's just a regular Python model. You don't need to know anything special about TensorFlow Lite to do it. And then what I wanted to show you, and you can find the complete code in the blog post, there's a very small amount of code that you need to convert your model from Python down into TensorFlow Lite format to run on device. And this is a tiny amount of code. Once you have this model, and this is a little unusual, we're going to convert it to a C array, and that's because this Arduino, it has like 1 megabyte of disk space, and I think like 256 KB of RAM. So we're converting it into the smallest, simplest possible format, but you convert it to a C array, and then what you can do, we have an example, And you could paste the C array into the example, and now you're running your TensorFlow model on device. And it's amazing. Like, I've had so much fun doing this. The reason I wanted to point it to you, if you have kids or you have students that want to play with this stuff, if you teach them just to train a time series forecasting model, which is a really valuable skill, we have a pretty good tutorial for it. I mean, it's interesting, but it's vastly more interesting if they can then deploy it on device. It gives them something tangible that they can play with and show their friends. It's super cool. Also, this is a brand new area. So TinyML, referring to doing machine learning on small devices, I think has a lot of promise. Another way to deploy your models, which is super powerful, is in JavaScript. And this is using TensorFlow JS. Here's another project suggestion. One of the first tutorials you might run through in deep learning is sentiment analysis. So given a sentence, predict if it's positive or negative. Also, a really valuable skill can be somewhat dry, right? But the first time I've ever been super excited about sentiment analysis, other than many years ago when I found out I could make money for it, that was not the link that I wanted. If you go into this GitHub repo, link from the slides, you will find that you can run sentiment analysis live in JavaScript. So for example, this is just a web page, and down at the bottom here, the movie was awesome. So I wrote a sentence, and you can see that's predicted positive. And here you can see that's predicted negative. And what's nice about doing JavaScript in the browser from a user perspective is there's nothing to install, which means if you're a Python developer and your goal is to have a cool demo, instead of throwing up a REST API, you can create a web page and share it with your friends. And what's nice, this model was written in TensorFlow 2 using Keras, and we have a converter script that will convert it into TensorFlow JS format to run in the browser. So following the examples, I am not a JavaScript developer at all. I can get through the examples, and it's not too bad. So it's possible to do, but it's a really good opportunity. If you have friends that are good JavaScript developers, this is a huge collaboration opportunity where you can develop models, and your friends can help you deploy them in the browser. Also, if you haven't seen it, you can also write models from scratch in JavaScript. And I just wanted to show you a couple demos here. I'm almost certainly going to accidentally unplug this laptop. But another super convincing thing about why you might want to do JavaScript in the browser. This is a model called PoseNet. This could be the end of the presentation. This is a model called PoseNet. It's running entirely client-side in the browser, so nothing's being sent to a server. And it's not meant for this many people. But you can see that it's starting to recognize where people are in the audience. And what's cool, I know this is all obvious for web developers, but I'm not, so this is all new to me. For me to do this in Python would have been a nightmare. Like, I would have to be streaming data from the video camera, sending it to a server, classifying it server-side, sending the results back. There's no way I'd be able to do that in real time like that. Also, for privacy reasons, that would not be cool. But because this is running client-side in JavaScript, we can do that. And so immediately, like, you can see all the things that we can do on top of this. There's other models like that too that are just really compelling. And then for people looking for applications, so there's sentiment analysis, but a model built right on top of that in the browser is just text classification, but this is multi-class text classification. And this is a toxicity detector. It's basically a sentiment analysis model, but the idea is you're given a sentence and you want to figure out if this is like a comment that you might want to post on YouTube or something like this. But you can build tools like this that analyze text privately, quickly, client-side. So you can imagine, for example, if you had a job as like a Wikimedia moderator and you wanted to take a look at article edits to see if they were something you wanted to publish or not, you might spend a lot of your time looking for toxic comments. With something like this, you could very quickly pre-process, you could immediately have code that right in the web page highlights the bad parts of the article. And I need to move a little bit quicker, so let me just point you to one demo and then I'll stop. If you're new to TensorFlow JS, by far the best demo, there's two and they're right here. One is PoseNet, which you can get at that link. There's also Pac-Man. If you haven't seen Pac-Man, you can control Pac-Man with your face. You can train a model live in the browser to do that, which is awesome. And then flying through this, last comment, then learning more. If you're working in Colab and you're used to using Keras, what you don't want to do is import Keras. You want to say, from TensorFlow, import Keras. And that will give you the version of Keras in TensorFlow 2 that's a superset of regular Keras. This is only a problem in Colab because Keras is installed there by default. If you ever see a message that says using TensorFlow backend, you've imported the wrong version of Keras. And then last slide, here are 4 books that I'd recommend. The very first book is about TensorFlow 2, and this will give you low-level details. It's great. only buy the second edition. The first edition teaches TensorFlow 1, which you do not need to learn how to use TensorFlow 2. The second book doesn't mention the word TensorFlow at all. That's the Keras book by Francois Chollet, but it's outstanding if you're new to deep learning. It's a perfectly good place to start. All the code from the second book will also work inside TensorFlow 2 just by saying from TensorFlow import Keras. Nothing else will change. It's all completely good. The next book is Keras in JavaScript, so deep learning with JavaScript, which is great. The fourth book is brand new. That's by Pete Warden, TinyML. So thanks very much, and I'll stop there and I'll be around after for questions.
Thank you so much, Josh. Where can we find you?
I'll be right outside.
Okay, awesome. All right, we're going to take a 10-minute break. For those of you who are standing in the back, there's some more seats over on this side of the room. We'll be back in about 10 minutes. See you soon. Thanks again.
Thanks a lot.
Cool. Awesome. So good.
Yeah, this is fun.
Hi everyone, my name is Ashley. I'll be your host for today. It's a pleasure and an honor to welcome our next speakers, Paige Bailey and Brennan Saeda, who are going to talk to us about Swift for TensorFlow, a next-generation machine learning platform that leverages innovation. So please help me in welcoming Paige and Brennan.
Good morning, everyone. So thank you for coming to join us during lunchtime. We very much appreciate you taking the time to come to TensorFlow World and also to learn a little bit more about Swift. I'm Paige. I'm the product manager for Swift for TF. And
I'm Brennan. I'm a tech lead manager for Swift for TensorFlow.
excellent. And so first, we kind of want to get a feel for the room. How many of you have used Swift before? Excellent. And how many of you attended Paris and Tim and their session, their workshop on earlier this week? Few hands. Cool. So this is a great place to get started if you've never used Swift before, and it's also a wonderful place to learn how Swift is getting more and more functionality added specifically for machine learning and for deep learning. So it's an exciting time. Do you want to get started, Brennan?
Yeah, let's do it.
Perfect.
So today we want to bring you a little bit different kind of a presentation. Since a lot of you actually know Swift, or at least to some degree, we wanted to really dig one level deeper and really explore Swift for TensorFlow from its foundations. So before we get into the meat of the talk, I wanted to take a moment to acknowledge a few very important folks. So number one is this work would not be possible without the rest of the Swift for TensorFlow team that really does a huge amount of work to make this platform awesome. So a huge thank you to them. But also not just the core team itself, but there are a number of other teams that we collaborate with at Google, from the JAX team to the rest of the TensorFlow and beyond. And so we really are collaborating together and building on each other's work to make something awesome. So thank you to everyone both at Google, but then of course our awesome open source contributors beyond. We have a lot of contributors that are really making a huge difference to the project. And finally, for those of you who are familiar with FastAI, some of the slides may be familiar. So Jeremy Howard and Chris Lattner co-presented a little bit of Swift for TensorFlow earlier this year, and I encourage you all to check that out. So to begin with, I like to start with a question. Why Swift for TensorFlow?
And I could give my answer.
Let's hear it.
Awesome. So I've been using Python for a long time. I really love kind of the flexibility and often the user experience that you get using the language. It feels very understandable. You read the code on the page and it reads almost like a plain sentence. And it also has a vibrant ecosystem of data science tooling. But something that I was always really frustrated about whenever I was trying to deploy Python models into production is that often you have to do a lot of rewrites. Like part of Python's benefits don't necessarily translate so well to deployment scenarios. So Swift is, to me at least, kind of a happy way to get a lot of the great benefits of Python, but also the benefits of a typed language.
That's right. And so what we are going for with Swift for TensorFlow is an infinitely hackable platform that gets you all the way from research into production. And most importantly, that everything is customizable, because although there's a lot of flexibility that you need to do research, you need just the same amount of flexibility and capability, often sometimes slightly different, to really make a high-quality production application.
Yep.
And that's what we're really excited about with Swift for TensorFlow, and especially with the Swift platform, how we can do interesting things to optimize for productivity. So let's take a moment to ask the question, what is Swift?
And Swift is a programming language that was created by Chris Lattner pretty recently, when he was spending some time over at Apple. Since then, Chris has come to join us and worked at Google. You'll be hearing a lot about one of Chris's other projects later this week. MLAR, I believe, is in the keynote tomorrow. But Swift is a programming language that's focused on that extensibility component that Brennan just mentioned, as well as readability, usability, and kind of production readiness. So.
That's right. So this is Swift for TensorFlow from the foundation. So let's really dig in, and let's really go from the foundations. So I think an important question to understand what is Swift at a deeper level is to understand what is a compiler. And so as you program computers, right, there are sort of two fundamental things that are sort of immovable and that like to think about the world in their own particular ways that are sort of sometimes incompatible. You've got humans on one hand that want to think about the world in a particular way, and you've got hardware, which also thinks about the world in its own particular way. And a programming language is basically an intermediate point in between these two immovable fundamental truths of technology. And so programming languages are designed for humans to express ideas, but they're also designed to be executed on hardware. And there are different points in that space that you can pick. And Swift is just one of such points, but we think it's a really interesting one, and we'll talk about why in a couple minutes.
Right. So one of the benefits of having a typed language is that a lot of the responsibility that might be pushed on you if you're using a language like Python is suddenly abstracted away. So I don't have to care so much about baking performance optimizations into my code immediately. The compiler can just do it for me. Another great thing is that if you look at the screen right now, you can see an example of a few commands in Swift. It looks very, very similar to Python, right? Like there's some lets sprinkled in. There's a few indications of types. But other than that, pretty straightforward to understand. If your only experience using typed languages is something like C++, this probably looks a great deal friendlier.
That's right. And Swift is a very modern and powerful programming language. So even though Swift is statically typed, you don't actually see very many types in advanced Swift code. Right here we're defining a dictionary numbers from strings to lists of integers. And the compiler can just figure this out for you. One of the principles of Swift is that you have a very helpful compiler. And you can define higher order operations, reduces, a common pattern from functional programming across a sequence of elements. And you can then call this, x.sum, mapped over all the values in a dictionary, and voila, you've now used a number of higher order functions together without having to write types in a very seamless and nice manner. So what we're trying to get across is that Swift is almost as high level as Python. So this is actually a slide that I'm borrowing from Chris and Jeremy's Fast AI lectures. And at the top, you have a Swift or TensorFlow model. And at the bottom, you actually have a Python model. And if you look at the code, if you squint a little bit, they're almost exactly the same thing, right? You've got a few more self dots on the bottom, and you've got some more curly braces on top, but they're basically the same thing. So Swift is just as high level, almost, as Python.
We also have fewer lines of code in that example, is that right?
Well, it depends on how you count the curly braces, so a little bit of here, a little bit of there.
Yep.
But what's really important about Swift is that it's designed to be fast, right? It's practically in the name. So who here has actually looked at assembly in the last 6 months? Fewer hands this time. Well, I bet you didn't expect to be looking at assembly today. So for those of you who don't know, the Godbolt Compiler Explorer is really neat. You can plug in some source code on the left-hand side, and it will give you the assembly on the right-hand side. And here we have Swift. We're calling a higher order function, reduce, on a generic type, so it's actually an array, in this case an array of integers, passing in the plus function, reducing over everything. And if you look at the loop that is going on here, so you've got your function prelude, you do a couple checks to make sure that everything is reasonable. You actually just have these 5 instructions that form the main body of your loop. You do the add, you check to make sure that you don't have any overflows. You then increment 1 to get to the next value in the array. You compare to make sure you've not reached the end of the array, and if you haven't, then you do your loop again. This is like the most efficient set of instructions you could possibly do to sum across an array. And so even though you have all these higher order things, you're not even writing types, the Swift compiler can helpfully optimize it all the way down for you. Now, actually, for those of you who really know about performance in assembly, a really helpful compiler will actually vectorize this operation for you. And so Swift by default is safe. So when you use plus, you're getting safe integer add that checks for overflows. But if you do ampersand plus, the ampersand plus function, this says just give me 2's complement, don't bother checking for overflows. And the Swift compiler will helpfully vectorize your operation for you to make it run extremely quickly. So Swift is designed to be safe, to be high level, but of course also fast. So programming languages are all about atoms and composition. And so the atoms in Python are C code that implements Python objects, and the composition is an interpreter that lets you combine these C calls in very interesting ways, right? Like Python array, Python dictionary. They're very, very carefully implemented in Python to be as quick as possible in C. And then you get to build your whole universe on top of it. C++, however, takes a different tack. There is no C underneath C++, right? It's just C++. So the atoms in C++ are int, float, C arrays, and pointers. And you got a few other atoms as well. And you get to build up your own structures in C++, like structs, classes, std complex, std string, std vector, right? So that's a C++ and C++'s view of the world. But as you think about C++, what's the real difference between string and array? They both are sequences of things, right? And so programming language has actually evolved since when C++ was initially created. And we actually can do more interesting things today. And so Swift builds on top of a lot of this programming language evolution and design. So Swift is really syntactic sugar for LLVM. Remember, getting back to that picture, you've got humans and you've got hardware. Programming languages are in the middle. You've got text editors to have humans interface with the programming language. And you've got compilers to interact with from the programming language to the hardware. And so why don't you define your language in terms of the compiler? You can just get rid of a lot of extra intermediate things, and by doing so, you can make a programming language that is more powerful. And so the primitives in Swift are LLVM instructions, and the composition are structs and classes, just like C++. But in Swift, instead of float and int being defined by the language, they're defined in the standard library, so that you can define your own int and float. Now, this may seem like an esoteric question that isn't terribly important. But, well, as it turns out, the definition of float is something that's in question these days. For those of you who are not familiar with TPUs, but TPUs define their own version of floating point format. They define bfloat16, which is short for the Brain floating point format that was developed as part of the Google Brain research efforts. And we found that the bfloat16 format is much better for both efficiency in the hardware and for training neural networks. And so Swift as a language is especially interesting for us because it lets us define a bfloat16 type that works exactly like int and float in the rest of the language. So what does it actually look like? It can't be, is this super weird? What's this black magic? Well, again, this is Swift from the foundation, so let's understand what is the implementation of float. You can totally check it out on GitHub, but here's sort of what it looks like, right? You've got struct float, because your composition is structs. And you define the value type, which is defined in terms of the LLVM primitives, this built-in FP IEEE 32. Plus equals is just a function, just a normal function that's defined in Swift, and it's implemented using the LLVM primitives.
And bfloat16, as Brennan mentioned, is incredibly important to us specifically for TPUs. But we're seeing even more kind of exotic data formats and sort of requirements for floats for other specialized hardware. So we anticipate this will become even more important in the future. And it's a place that we're really excited to explore more with Swift.
That's right. And so even though int and float are elements in the standard library, they're just as fast, right, as we looked at the assembly instructions before. But that also means that Swift as a language is super flexible, right? So you can define extensions on int, and so you can define the is-odd property of int just in a Jupyter notebook. You can define an extension on Boolean symbol, which returns a Unicode character string of thumbs up or thumbs down. And you can then compose all of these exactly as you'd expect to print out these silly true falses and emojis and whatnot. But Swift, again, even though you're using all these high-level operations, is just as fast as C. And so these notebooks, which I encourage you to check out from Jeremy Howard and Chris Latner's Fast AI course, actually show you how you can build a matmul in Swift that is just as fast as C. Perfect performance parity. So that's a little bit about Swift. Let's talk about deep learning.
Yes.
Okay, no, let's actually have a brief detour before we get there.
Well, it's also very important to understand the mathematics involved in implementing a deep learning project, right? You have to understand a little bit about linear algebra and a little bit about math in order to effectively architect your experiments. So for this next slide, we have a quiz, and I promise it isn't too scary. But somebody in the room, shout out what you think B will print based on this slide. I think I heard a 3. So that is
3.
correct.
Very good.
Excellent.
This is value semantics. This is how integers work in Python. It is exactly what you'd expect.
Yep.
If A is 3, B is equal to A, that means B is 3. No matter what you do with A, 3 is still 3, B is still 3, we're all good.
Yeah. So let's take a look at this next slide. We have a Python list, and this, crazily enough, whenever you add 4, would print 3 and 4 for the values of B. So this is not value semantics, and this offers a great many frustrations for developers as they're attempting to architect their experiments.
That's right. Math operates on value semantics, and Swift is designed to be a very, very fast programming language, but at the same time really push forward value semantics. And so in Swift, arrays actually do have value semantics and behave exactly as you'd expect.
Yep.
So here's a copy-paste from a terminal where B stays the same, and just to show you that I don't have anything up my sleeve, right, A is actually 3 and 4. But see, in Swift, not just arrays, but so do dictionaries, and so do all other sort of higher-level types. Many high-level types that you build can have value semantics as well. And this has important ramifications for how to write neural networks and do machine learning and automatic differentiation. Which leads us to our next topic.
Excellent. Automatic differentiation is one of the sort of product-defining features of Swift. And it's one of the things that we're most excited about upstreaming to the Swift programming language. So we showed in one of our slides previously, I believe, a function that was prefaced with @differentiable. And this is sort of functionality that allows you to differentiate not just sort of aspects of machine learning models, but literally any function in Swift you can take the gradient of. So do you want to show an example, Brennan?
You know what? It's better to show, not tell. So let's see. Here we are in a Google Colab. So this is a hosted Jupyter notebook. And here we define my function that just takes 2 doubles, does some math operations, and returns another double. And so to make this function differentiable, you just annotate it @differentiable. And once you've done that and run the cell, the compiler has now constructed the forward pass, but also the backwards pass for this function automatically. And so to then figure out what the derivative of that function is, you just call the gradient function. So you do the gradient at 0.5 of my function, and this gets you the partial derivative with respect to A. Of course, you may want to take the partial derivative with respect to both A and B, and so that is exactly as you'd expect. So you have now both points. When you're training neural networks, you sometimes also want like the value of the function in addition to the partial derivatives at a particular point. And so to do that, instead of calling gradient, you just call value with gradient. And this will return a result that has, it's just a tuple. So in Swift, you've got named tuples optionally. And so you've got the value and the gradient, and you can manipulate them exactly as you'd expect.
Excellent. And if you're coming from Python land, or you stuck around for the presentation a little bit earlier, this would be sort of taking the equivalent place of gradient tape in TensorFlow. So instead of having to create a gradient tape and collecting your variables on that, you can just go ahead and do the annotations for your functions.
That's right. And the thing we're really excited about is, again, this is language integrated. So these aren't just on tensor of double that are 1D or 0D tensors. These are just regular built-in int and float and double and beyond. So that's how you write a function, a custom function, and take the derivative of it. But we really want to build this next generation platform that allows for maximum flexibility. So you need to be able to write your own types that can also be differentiable. So let's see how to do that. So here we define a point in 2D space. You got x and y, and we just mark it as differentiable. We can then we can define some properties on it, right? So the function dot and this silly helper function. And you can then compute the gradients of this dot product, this point dotted with itself. And so there you go. You then get the tangent of this point at that space. Now, often it's a good idea to mark your functions as differentiable because this helps the compiler catch errors for you and is also a great form of documentation. And here we see an example of the compiler catching an error for us. So page, this says, error can only differentiate functions with results that conform to differentiable, but int does not conform to differentiable. What does that mean?
All of the values are discrete. Like, you can't add a little incremental step change.
That's exactly right. So integers, right, the derivatives are about infinitesimally small steps, and integers don't allow you to take infinitesimally small steps, right? You've got 0 and 1. There's nothing in between. And so this function is not differentiable, and the compiler is very helpful in telling you, hey, you can't do this, and this is why, instead of silently giving you a wrong answer. So if we remove the annotation from that function, the compiler caught an error for us. Great, we can keep going on. But let's say we want to take things to the next level. What if we want to define an additional property, say like the magnitude property, which is defined by a vector from the origin to that particular point?
And it looks like you're importing glibc here, which means do you get all of the mathematics operations that are already within the C? Okay, cool.
That's right. Yeah. So this is a great excuse for us to show the Swift C interop. So in Swift, you can just import any arbitrary C header and use the symbols defined in it. No boilerplate, no wrappers, no nothing. Just go straight for it. So here we're going to import glibc, and this is the square root function defined by C standard library. So we can then use that to define point, the magnitude, extension on point, which is the square root of x squared plus y squared. So we run this and we get magnitude, and dang it, we got another compiler error. What's this saying?
So read through cannot differentiate functions that have not been marked differentiable and that are defined in other files. So it looks like you have to go and change this in another file.
That's right. So square root is defined by the C compiler, and the C compiler hasn't been taught how to take derivatives.
Yep.
So this is a great excuse to show you how you can write your own custom derivatives for arbitrary functions. If we recall that the derivative of the square root of x is 1 over 2 times the square root of x, we can define my square root, which underneath the hood just calls c. And we can define the derivative right here with this function closure, inline closure here. So we run that, and that compiles successfully. We go up here, change square root to my square root. That runs, and voila, we're off to the races. We've now defined a differentiable magnitude function on point. We can then use this function inside other differentiable functions exactly as you'd expect. Everything fully composes. So here we define this silly function taking points and doubles, right? You can mix arbitrary differentiable types. And we're going to define our point, take the gradient of it. We can get our tangent vector, which has the partial derivatives with respect to both x and y at that particular point.
Excellent. And so I love that you're able to sort of use all of the great code that's been written to support mathematics. But I also really love that with Swift, you get C and C++ interop. And as Brennan mentioned, you can import any header, use it as is, or extend it to meet your use case. So if you're working in an enterprise and you have a massive existing C++ code base, like Google. And then it's really helpful to be able to not have to rewrite the entire wheel, right? Like you can just import things that people have created over time, use it, and then everything as part of a Swift program would compile down to a .so file. So you can deploy it on any platform, Windows, Linux, Mac, iOS, Android, embedded devices even.
That's right.
It really is sort of the most multi-platform approach that I've seen for machine learning.
That's right. So I think this is enough. There's actually more power in the Swift for TensorFlow automatic differentiation system, and I encourage you to check out more details later. But let's move on to actually talking about neural networks.
Cool.
And here we go. So tell us about writing neural networks in Swift.
Writing neural networks in Swift, we just saw an example of it. It's pretty straightforward. You only have about 5 lines of code. It looks very similar to Keras. And if you open up a Colab notebook,
there we go.
You can see an example of it here.
Great. So why don't you walk us through this right here?
Right. So you create a model by adding some layers. Here we see a convolutional layer, conv2D, a pooling layer. We flatten it. And then we call a function with at or we preface the call as function with at differentiable, and that gives us our gradients.
Yep. So here we define a sequential model, just in Swift. So now let's actually use this as we would to actually train this model on some data. So here we define some random training data, just because, for convenience purposes. We instantiate the model and an optimizer for it, and then we're going to run this for 10 training steps. So we do this in just a few lines of code. We're actually handwriting out the training loop up here. But here we get the value with gradient, which gets us our loss and our gradient. And we then print out the loss and use the optimizer to update our model along the gradient. And so just like that, we're training a model, and you can see the loss values decreasing.
Yep. And if you're not a fan of writing out as many custom steps as we have expressed here, Jeremy Howard did a great collaboration with Chris and with the Swift for TensorFlow team where he re-implemented FastAI on top of Swift. So if you're looking for higher level constructs, you just want things that are kind of out of the box, I highly recommend checking out those notebooks as well.
That's right. But one of the common workflows that anyone who's doing machine learning is they have their first version of the model, they train it, and they figure out how to make it better, right? That's one of the great promises of machine learning is you can keep incrementing and optimizing. So let's see how we can optimize this model to make it a little bit better. So you may be following a lot of research, and you may hear that skip connections or residual networks are a really good idea. And so in the next 30 seconds, we're going to convert this network to be a residual network with a skip connection. Are you ready? All right, here we go. So what we need to do is we need to define our second dense layer that we're going to use as part of the skip connection. So we're going to do dense float, and I can't type. And here you can see the autocomplete, right? We care a lot about developer productivity. Autocomplete that's helping to fill in the initializer parameters for us. Fix up a little bit of the shapes. Great, now we're all good. So we've now added the extra layer. Now we need to add in that skip connection. So let temp is equal to input, and we need to capture the value after the flatten step. Let temp2 is equal to dense of temp, so this is going to be the first part, and now we do our skip connection. Dense of temp plus temp2. Voila, we have now added an additional layer and added a skip connection to our model right here in a Jupyter Notebook. So we now recompile that to make sure that that's working well. Looks like it is. And so we're going to reinstantiate our model, because it's now a different model, and we're going to retrain it for 10 steps. And looks like we actually got slightly lower or similar loss values. So this was good, but we can, of course, do better. But this is sort of an example workflow of how easy it is to customize models using Swift for TensorFlow. Yep. But for those of you who are, just applying models to standard data sets, customizing the model architecture is the bread and butter workflow. But we're finding more and more that both research and production, you sometimes need to be a little bit more advanced. And so Swift for TensorFlow, the platform is infinite hackability, infinite customizability. Let's actually see how you can write your own custom layer also in a Jupyter Notebook. All right. So let's say if we're a researcher and we wanted to define a custom layer that we add 2 bias terms to our dense layer instead of just 1. Well, in about 10 seconds, we're gonna write this. All right, ready? Here we go. Boom. All right. Great. It worked this time. All right. So here we define our weights, our weight tensor, and our first bias term and our second bias term. We have our constructor, and then finally the actual forward function or call this function, where you take the matrix multiplication of the input and the weights, and you add in the 2 bias terms. So there we go. This should compile. And once it does, there we go. We can then use it in our new model. So instead of a dense layer, we use a double bias dense layer. We can then compile this, instantiate the model, and whoops, this doesn't quite work. Again, here you see the Swift compiler being extremely helpful. You have a quick typo here. Instead of label, it should be labels. And it just tells you this is what you should be doing, and you're off to the races. So we fix that up, and we can run the training steps, and
the loss is worse.
Dang it.
So.
We have a little bit of bug in our implementation, And so exercise for the audience to figure out where that bug was, but we'll let you think about that on your own time. Anyway, that's a brief tour about how to use Swift for TensorFlow as an ML practitioner applying and fitting against data sets and models. Excellent. So we'll head back to the slides. I forgot. So one other thing, right? So we showed how to write a custom model. We showed how to write a custom layer. But if you're doing research into different optimizers, you also want to be able to customize that. And so optimizers in Swift are just pure Swift code. And so here we have the salient bits of the stochastic gradient descent optimizer that we were using just now. And so it's just 10 lines of code to implement momentum, Nesterov, and other advanced features for a stochastic gradient descent optimizer. So we've been spending a lot of time really thinking about what are the right APIs and what are the right ways to factor machine learning to make it easy to use, powerful, and flexible. And we're pretty excited by where we are today. But we're always looking, of course, to improve. So if you're interested in pushing the limits of the state of the art, here are a bunch of other things that we'd love to have you try and give us feedback and really to help us improve our APIs.
So we mentioned before that one of the biggest sort of wins for Python is that an entire ecosystem of data science products have been built around it. And the good news is with Swift, you don't have to give any of that up. So I think Brennan has a demo coming up showing that you can use tooling like matplotlib or numpy or scipy or any of your favorite Python packages directly from Swift, almost identical to the same way that you would run it in a Python Jupyter notebook. Is that correct?
That's right.
Yep.
So let's take a look. My secret notes. All right, there we go. So here is a Jupyter notebook, or actually Google Colab, where we import TensorFlow. And we also import Python. And once we've imported Python, we can use this Python object to import arbitrary Python libraries with no wrappers at all. So here we're going to import matplotlib, the pyplot actually type from there, and numpy. And we're going to assign these to plot and np. And after that, you can write Swift code. Now again, this is Swift code that looks almost exactly like Python. So here we're going to call np.linspace, assign that to x, and we're going to plot x and sine of x and x and cosine of x. And just to show you that this really does work, we'll run it, and voila, you're using pyplot from matplotlib and numpy right from Swift. In short, you don't have to lose all the great Python ecosystem while taking advantage of all the capabilities that Swift offers. Now, sure, what about a more wackier library? I mean, these are kind of wacky, but one of the important parts of the Python data science ecosystem are all the machine learning libraries. And one of my favorites is actually OpenAI Gym. So this is a Python library that has a bunch of reinforcement learning environments that you can use to train and evaluate neural networks as you're doing research in reinforcement learning. And so, it's a Python library, but as it turns out, with Swift for TensorFlow, you can just use it. So here we're going to use Python to import Gym. We're going to define some hyperparameters. Here we're going to define our neural network using Swift for TensorFlow. So just like you saw before, we've got 2 dense layers. We have some code to interact with the Python environment, and including defining the next batch. But here we use that Gym library to make the cartpole environment. We instantiate our neural network and our optimizer for it, and then we're going to train it for as many steps as we need. Again, we see that the Swift compiler is actually really helpful. It's telling us that on line 24, instead of one-hot labels, we probably mean probabilities. And if I type that right, we should now see this training. So here we're using a neural network defined in Swift for TensorFlow, training in the Python OpenAI Gym library totally seamlessly right in a Jupyter notebook. In fact, it solves it, and of course, you can take the results that you've the intermediate values that you've computed while you've been training this model and plot it using matplotlib right in the notebook. Yep. So it all totally works all back and forth.
And as a machine learning engineer, I think an important thing to note with this is that your workflow doesn't change, right? Like the only sort of incremental step that you need to add is importing Python and assigning with some lets, and that's about it.
Yeah. Excellent. So that's a number of demos and notebooks that you can see sort of the state of the world today. But let's talk a little bit more about what's been going on in the future, the directions that we're heading. So we have C interop, and we've been working on C++ interop as well. So here's sort of an example of what we have. So on the left column, you define a C++ type, header file, etc. And on the right-hand side, if you define this in example.h, you can then import it in Swift as import example, and you can then call these methods directly on it. We have a number of features already supported, including instantiated templates, because as it turns out, C++ is not quite the simplest language. But we're seeing that it's available to be useful for a number of things already today. One of the mantras is infinite flexibility and infinite hackability. And so we've talked about writing custom networks, custom layers, custom optimizers. But what about custom kernels as well? As it turns out, we've been working on that. And so this is some of the work that is preliminary work on the team. But here you can define 1D average pooling in pure Swift. And this actually runs on both CPUs and GPUs in the prototype that we put together. Now we're still iterating and getting the fundamentals of the design right, but this is sort of an example or the direction that we're trying to go with Swift for TensorFlow, with infinite hackability, so that you're not limited to what's in the box for you. The whole world's your oyster. You get to program at any level of the stack, doing whatever you need to do. You're never limited when you're building on the Swift for TensorFlow platform. We've had a lot of amazing things happen as part of the community that's been growing around Swift for TensorFlow. So we have in development a model garden with a variety of supervised learning models and some unsupervised learning models. But one of the collaborations that I've been super excited about has been with the DeepMind team that's part of Alphabet. They recently released OpenSpiel, which is a collection of reinforcement environments and algorithms. And a subset of those have been ported to Swift. And so that's a great place if you want to check it out if you're really interested in reinforcement learning. So if you've been interested, how do you get started, Paige?
Well, you can get started writing Google Colab, so the examples that Brennan showed. We also have a variety of tutorials available at tensorflow.org/Swift. And I also encourage you to look at Jeremy Howard's Swift AI implementation of FastAI that's available on GitHub.
Did want to take a moment to really highlight some of the community projects that have been going on. So we talked about OpenSpiel, but Anthony Platanios has done amazing work with SwiftRL, another reinforcement learning library, and Swift Atari Learning Environment, which I think are really great. There's SwiftPlot, SwiftML that have happened as a result of the Google Summer of Code project. There's projects that have happened this summer that Paige has organized that I think are really fantastic. Swift AI came out of the FastAI collaboration. We have tensors fitting perfectly, where Adam Pashka joined the Swift for TensorFlow team this past summer and did some really great research. Everything is open source. We'd love to have you join our community. We have open design meetings every Friday at 9 a.m. Pacific or 1600 UTC, and we'd love to have you all join in and really help shape this platform together with us. We've recently released 0.5 with a number of improvements, and stay tuned for our next releases coming up. And with that, I'd like to thank you all for listening to us today.
Excellent.
We will be around here and in the hallways for the rest of the day. We have for those of you here in person at the conference, we will be hanging out at the Ask a TensorFlower Cafe in the Expo Hall. Come with your questions, feedback. We'd love to hear what you're thinking and see you at our open design meetings. Thanks.
Thank you so much, both of you. Just a reminder now, we have lunch. There is the lunch and topics table that's happening in the Expo Hall, and there's a Better Together Diversity Lunch sponsored by Google happening in the Magnolia Hall. Enjoy your lunch.
Hi, and welcome to the TensorFlow YouTube channel. On this channel, we'll have a lineup of great shows for you, including Coding TensorFlow, where we explore what it is to write TensorFlow code together. TensorFlow Lite is TensorFlow's lightweight solution for mobile and embedded devices. Here's a sample piece of code. TensorFlow Meets, where you are the star, and we get to meet with you to talk and to learn and to share about all of the great things that you're doing with TensorFlow.
Just learning the basic mechanics and concepts, but seeing how it actually applies to their field.
I like this combination a lot.
There's also Ask TensorFlow, where we answer your questions marked on social media with the Ask TensorFlow hashtag.
What is the difference between TensorFlow Mobile and TensorFlow Lite?
One's mobile, the other's light.
That's right.
We'll also have lots of great content from events like the TensorFlow Developer Summit and special guests from other parts of Google and beyond. So hit that subscribe button now, and we'll see you there. At Google, we've been on a journey to make the training, deployment, managing, and scaling of machine-learned models as easy as possible. To that end, we're now delighted to say we've released TensorFlow 2.0. TensorFlow 2.0 has been driven by feedback from lots of folks in the community, from individual developers to enterprises to researchers, telling us that they want an easy-to-use framework that is both flexible and powerful and supports deployment to any platform. TensorFlow 2.0 provides a comprehensive ecosystem of tools for developers, enterprises, and researchers who want to push the state-of-the-art of machine learning and build scalable ML-powered applications. With TensorFlow 2.0, we strive to make development of machine-learned applications much easier. With tight integration of Keras into TensorFlow, eager execution by default, and an emphasis on Pythonic function execution instead of sessions, the goal is to make the experience of developing applications with TensorFlow 2.0 as familiar as possible for Python developers. Our drive to make simpler APIs does not come at the expense of giving you the flexibility to develop advanced customizations for your needs. We have invested heavily to create a more complete low-level API. So for example, you can now export all ops that were used internally and provide inheritable interfaces for crucial concepts such as variables and checkpoints. This allows you to build on top of the internals to TensorFlow without having to rebuild TensorFlow. For example, creating your own optimizer like you can see here. We have standardized on the save model file format to run models on a variety of runtimes, including the cloud, web, browser, Node.js, mobile, and embedded systems. This allows you to not just run your models with TensorFlow, but deploy them to web and cloud with TensorFlow Extended. You can use them on mobile and embedded systems with TensorFlow Lite, and you can train and run them in the browser or Node.js with TensorFlow.js. With the Distribution Strategy API, you'll be able to distribute training with minimal code changes, yielding great out-of-the-box performance. It supports distributed training with Keras's model.fit, as well as with custom training loops. Multi-GPU support is available, and of course TensorFlow 2.0 also supports TensorRT for fast inference on GPUs. Check out the guide for more details. Another feedback item we heard was that making access to data easy would be a massive benefit. Much of the code that developers write is in managing and preparing their data, so we have expanded TensorFlow datasets, giving a standard interface to a variety of diverse datasets, including those containing images, text, video, and much more. While the traditional session-based programming model is still maintained, we recommend using regular Python with eager execution. The TF function decorator can be used to convert your code into graphs, which can then be executed remotely, serialized, and optimized for performance. This is complemented by autograph, which is built into TF function, and it can convert regular Python control flow directly into TensorFlow control flow. And of course, if you've used TensorFlow 1.x and you're looking for a migration guide to 2.0, we've published a guide which includes an automatic conversion script to help you get started. If you want to learn how to build applications using TensorFlow 2.0, take a look at the Effective 2.0 guide and then try out our online courses that we've created together with the folks from deeplearning.ai and Udacity. For more about TensorFlow 2.0, including how to download and get started with coding machine-learned applications, check out the official TensorFlow site at tensorflow.org.
I often look at the news to find problems around the world. I heard about the Zika virus outbreak, and I wanted to use gene editing techniques to help prevent this from happening. And then I heard about Malaysian Airlines going missing. So I created a black box finder. But then I found out about Flint, which was one of the biggest problems I'd ever seen. My name is Gitanjali Rao. I'm a scientist and an inventor. In 2014, Flint switched their water source from Lake Huron to the Flint River, which caused lead contamination in drinking water. The part that hit me the most was that there are all these children who don't deserve unclean water to drink. I wouldn't want that to happen to me or my family, so why should it happen to them? I saw my parents testing for lead and other contaminants in our drinking water, and it wasn't reliable, it was inconvenient.
The current test for lead can take up to 2 weeks. That is quite expensive and is very laborious to get a result.
So what I wanted to do is create a lead in water detection tool. I came across this new technology using carbon nanotube sensors and wanted to expand the idea to detect lead in drinking water. In the beginning, I wasn't even sure if this idea would even work. I needed guidance and I needed a lab.
When I met Gitanjali, I thought that she conducts herself pretty much like an adult. She's combining the skills of an engineer, of a scientist, of a designer. So we decided to partner up with her because we have a common goal to provide safe drinking water.
When they offered me the lab space, I come home and I start screaming my head off. It's like, ah, or something like that. I was so excited. I knew that if I could get this to work, I could help so many residents of Flint. My device is named Tethys, after the Greek goddess of fresh water. To create Tethys, I went through a lot of different versions, and now it's a 3D printed, fully wired device. In order to test for lead in your water using Tethys, you attach a disposable lead sensor cartridge specially treated with chloride ions. If the water has lead, it sticks to the chloride ions and causes resistance to the flow of current. So the more resistance, the more lead. To display the results, I wanted to create an app. So I used Android App Maker because that's what was easiest for me for my first time creating an app. I connected the device to the phone using Bluetooth, and I could see my results of either safe, slightly contaminated, or critical.
She's just amazing. She's taking advantage of that knowledge and that passion to build something that is for the benefit of humanity.
Coming to Flint just makes me want to work harder. People are lined up for hours waiting to get bottled water, which won't even last them a whole month. I know my device only solves a small part of this huge problem. But if people can test their water themselves, that gives them the power to do something about it.
Society tells you that you can't do certain things because you're a child or because you are a female. Seeing someone like Gitanjali, so eager, so smart, so prepared, she's pushing the envelope, not only for herself, but for other generations to come.
चार साल पूरे दुनिया का सफ़र करूँगा 75 कंट्रीज़ में.
I want to learn more about the world. I want to know about people.
And this is my first step to understanding.
Hello, everyone. I hope you enjoyed lunch. We're now going to start our afternoon session. Please welcome Robbie Neal, who will be talking about tensors and tf.text. He's on the TensorFlow team, and we look forward to hearing what he has to say. So please help me in welcoming Robbie.
Hi. Y'all hear me? Okay, I can hear myself now. I'm Robbie. Yeah, I'm an engineer in Google, and I'm going to talk to you about how to leverage TF-text for your pre-processing and language models inside of TensorFlow. So for those unfamiliar with language models, all right, there we go, forward. They're basically everywhere. You use them in query understanding. You have related keyword searches, article summaries, spell check, autocomplete, text-to-speech, spam filters, chat bots. You really can't get away from them. And it's really a good time to be into NLP right now because we're going through somewhat of a renaissance. Last year, this paper on BERT was released that uses attention and transformers. I'm not going to go too much into it other than traditionally, obviously, when you're working with text, models don't play as well with strings, so you convert those into numbers. And so we've used embeddings, different ways to embed, like GLOVE, Elmo, Word2Vec are different ways to create vector representations of your words. And these worked really pretty well. The one problem is you have with some words when you look them up in your vocab, like bat. Am I talking about an animal? Am I talking about baseball equipment? Even words that don't sound the same, entrance and entrance, they're spelled the exact same. So when you're trying to represent these as a vector, you're trying to have two different meanings to the same sequence of letters. And so BERT has gone around this by, it's a model that actually uses the context of the sentence to actually create this vector for the words. And so it's done really well, and this is the Stanford question and answer data set. So BERT was late 2018. The scores before that were in the low 70s. It came out, it jumped up to around 82, and ever since then, people have been iterating on this model through Roberta, XLNet, Albert, and I pulled the scores up, from last week, and you can see that like the most recent model, Albert, is actually outperforming humans. So that's pretty crazy. So it's really exciting right now to be into this. And so let's just jump right in. So what is TF-text? Our charter was basically to make programming these language models in TensorFlow easier. Traditionally, it's been very difficult to do this. You would get, let's say you have some data, like here's an example of queries, and we want to train on this data, right? Well, before we can do that, we need to do some pre-processing, which is basically tokenization outside of that because we didn't have that availability inside of TensorFlow. And then once we did this pre-processing, we had to somehow fit it into a tensor, so we would get this pre-processed text, add it into the graph, and then normally like pad out our tensors to make them a uniform shape so they're available. And then we finally train our model, and we go to publish it, and we put it on our model server, and we're like, okay, we're ready to go, right? And then so when we get the serving data, well, you can't just plug that serving data right in, right? We had this pre-processing that has to happen, and so either you're relying on the client to transform the data as well, or you're doing it yourself, and a lot of times it's a different language than when you did your normal scripts in. And I've seen it even like when the pre-processing is exactly the same, like it's used the exact same regex, like because it's different libraries, like one might consider a character class to be punctuation where the other doesn't. And so you get training skew when these like pre-processing steps are different. And so when you actually go to serve the model, you don't have the same performance, and that's problematic, right? So our charter was to make this as easy as possible, to support TensorFlow, or to support text inside of TensorFlow. And to do this, we want to do all the text processing in graph. And we do this through a series of like text and sequential APIs that were not available, and actually create a new tensor type called ragged tensors that better represents this text. So if we go back to when it was painful, what we really want to do is just get rid of this pre-processing step, right? Put everything in the graph. And so all your pre-processing happens in graph, and then when you go to serve the model, you're not relying on the client to perform those same steps when you serve the model, and they call it. And so really the main thing that was missing was tokenization. So last year we had an RFC with the tokenizer API, and we wanted to make this as easy as possible and straightforward. So it's very simple. It's an abstract tokenizer class, has one method, tokenize. It takes input of string and gives you back your tokens. And so if you see this, it's very simple. We have a couple sentences here. We tokenize them into words. The one thing I like to point out, which is not completely obvious immediately until you see examples, is that our input is a rank 1 tensor, and our output is a rank 2. The reason why this is our tokens are grouped by the string that they're split from. And so it's really easy from the engineer's perspective to be able to tell which string tokens were pulled from which string in the original tensor. The one thing you can't do from this output is tell where in that originating string it came from. And for that, we have like one extra tokenizer with offsets class, abstract class, that has tokenizer with offsets, which is the same thing. You give it an input tensor of strings. It gives you your tokens, but also gives you where those tokens start and end. So we can see that example here. We call it tokenize with offsets, and we can see the letters like I starts at 0 and moves 1 position, and then no is in the 2nd position and moves up 6 characters. So through these offsets, if you want to know where the tokens are in your originating string, you can do that. And in you'll notice the shapes are exactly the same as the shapes of the tokens. So mapping token to starts and limits is very simple from here. And so we provide 5 basic tokenizers. One of the questions when we first did the RFC was, why don't we just have one and like one tokenizer to rule them all? The problem is every model is different. You have different limitations and things you want to get around, and we don't want to like push our opinion on you because they're all different. We just want to build the tools and allow you to make the decision. And so a lot of these are very simple. The white space obviously just splits a sentence on white space. Unicode script, so if you know Unicode, characters are grouped together in what they call Unicode scripts. So you would have like Latin characters, Greek, Arabic, Japanese are just some examples. And then they also group spaces, punctuation, and numbers as well. And so it splits on those. I would say in the most simple case, if you're just working with English, the main difference between white spaces, it splits out the punctuation. So word piece, this was popularized by the BERT model, which I had mentioned earlier. It basically takes text that you've already tokenized and then splits those words into even smaller subword units. So this is actually, it greatly reduces the size of your vocabulary. As you're trying to encapsulate more information, your vocabulary will grow. And by actually breaking the words down into subword units, you can greatly get that smaller and encapsulate more meaning and less data. And to generate the vocab, we have a Beam pipeline in our GitHub, so you can generate your own. Or the original BERT model has a vocab you can use. Sentence piece is a very popular tokenizer. So this is actually released previously. There's a GitHub where people have downloaded, and it's pretty popular. Basically takes a configuration where you set up a bunch of pre-processing steps already, and you feed that to it, and it does that. And so it does subword tokenization, word and character. And finally, we're releasing a BERT one that does all the pre-processing that the original BERT paper did. And so you can use, like I said, their word piece tokenization, and it'll do the pre-tokenization steps, some other normalization, and then the word piece tokenization. So now that we had tokenizers, we really just needed a way to represent these. And that's where we created ragged tensors for this better representation of text. So if we look at an example, we have two sentences, and like I said, normally your sentences are never of the same length. So when you try and create a tensor out of these, you get a value error. It needs to be of a uniform shape. And so traditionally, like I said previously, we padded out the strings. And in this example, you're like, okay, so 3 extra values is not so bad. But when you're actually writing out these models, you don't know how long your sentences are going to be, so you have a fixed size. And so a lot of times they've seen fixed size of 128 characters or 128 words, and your just pad has all this extra information that you don't really need inside your tensor. And then if you try and make that smaller, when you do have a long sentence, then those sentences are truncated. So you may think, well, we have sparse tensor. And this is also not quite as good because there's a lot of waste of data that you're having to supply a sparse tensor. As you know, or if you don't, sparse tensors, because really in TensorFlow, everything's made of tensors, so it's actually made of 3 tensors, which is values, a shape, and then where those values exist within your matrix shape. And so you can see there's actually a pattern, because ragged tensors aren't necessarily, or for a string, it's not necessarily that they're sparse, it's dense, they just have varying lengths. So it would be good if we could say, hey, the first row has indices 0 through 5. The second row has indices 0 through 2, and those make up our sentences. Excuse me. And so that's what we did with ragged tensors. It's easy to create. You just have a TF ragged constant to create it. It's similarly built like a sparse tensor. It's made up of values and row splits. And so it minimizes the waste of information. So you can see that all the values are in one tensor, and then we say where we want to split up that tensor to build up our different rows. It's easier to kind of see it in this form, where the gray block on the left side is what the ragged tensor is in its representation, and on the right is how it would look represented. And down below is how you would actually do that call or build this if you're using values inside of TensorFlow. And so this was the original way. We had row splits. We had some people come to us. They represented these in different ways. So we also provide row IDs where the ID tells where that value is inside your tensor, and row lengths that says these are the lengths of each row. So the first one takes the first 4 values. You could have empty rows, so 0, 2, and so on. And so we want to treat these like any normal tensor. So ragged tensors, they have rank, just like you would see in normal tensors. So in this example, we have a rank of 2. They also have shape. The question mark, when we find our shape, denotes the ragged dimension. It's not necessarily always on the end, but in this case, it is on the end. And we can use normal TensorFlow functions and ops like we would with normal tensors. So here we're just using gather. It grabs the second and then the first row. Gather ND, which grabs the index. Concat, we can concat on the different axes. And of course, we made this for sequential and text processing, so your string ops work well with ragged tensors. So here we decode the strings into code points, encode them back into strings, and conditionals work as well. So in this case, where clause, where we use ragged tensors inside. The one case here is that the ragged tensors for the where, they must have the same row split, so the rows must be the same length. And it's easy to convert into and out of ragged tensors. You can just do from tensor or from sparse to create a ragged tensor. And then to move back, you just have your ragged tensor and just call toTensor or toSparse. And then toList actually gives you a list if you want to print it out. So we're also adding support to Keras. These are the layers that are currently available or compatible. And there's a lot left we have to do on this front. We're pushing to get more layers compatible with ragged tensors. If you are using them within your Keras model and come across something that's not compatible, in TensorFlow Text there at the bottom, we do provide a toDense layer that will just convert it for you. And the real cool thing that I want to point out is the RNN support. So we've seen on tests that we get 10% average speed up with like large batches, like 30% or more. This is very exciting, and I won't go into details, but it's very intuitive, because if you think about when you are looping through your tensor, when you're at the end of that ragged dimension, you can stop computation. Where before, if you're using tensors, you're using mask values, and masks can be not necessarily at the end, but in the middle, so you have to keep computing until you're end of the full tensor length or width. So yeah, you just have a lot less computation, and so you save a lot there. All right, so I want to go over a couple examples, show you how easy it is to work with. You can just install TensorFlow Text with pip. Our versions now map to TensorFlow versions. So if you're using TensorFlow 2.0, use TensorFlow Text 2.0. If you're using TensorFlow 1.15, use TensorFlow Text 1.15. Because of the custom ops, our versioning must match. And you can import it like this. We generally import TensorFlow Text as text. So in these examples, you will see it written as text. So let's go over a basic preprocessor, what you might do. So normally you'll get your input text. Here we have a couple sentences. We want to tokenize it, split those sentences into words, and then we want to map those words into IDs inside our vocabulary that will feed into our model. And so the preprocess function might look like this, where we just instantiate the tokenizer, create a ragged tensor of that input, and then map a table lookup into our vocabulary along the values of that ragged tensor. So if you remember what the ragged tensor looked like underneath, when we have our words and tokens, we have the ragged tensor above, and where the values are set, and then the row splits are separate in a separate tensor. So really, when we want to map those words to IDs, we're keeping the same shape. We only want to map over the values. And so that's why the map over values is there, because we're just converting, we're doing the lookups on each word individually. And so the resulting ragged tensor is there at the end, and we can see what it actually represents above. And so this is our preprocessing, and once we're done, you using TF data, normally create a data set from it. You map that preprocessing function over your data set. I won't go into model details, but you can create a model with Keras pretty simply, and then fit that data set on the model, and that trains the model. And so you can use that same preprocessing function in your serving input function. So you have the same preprocessing that's done at training time as it is in serving time with your inference. And this prevents training skew. that we have seen multiple times in the past. I have, at least. So let's go over another example. Character bigram model here. Before I jump in, I just want to quickly go over n-grams. So a bigram is like a form of an n-gram with a width of 2. It's basically, I say, like a grouping of a fixed sized over a series. We provide 3 different ways to join those together. So there's the string join, and you can sum values and also take averages. So let's pull an example here. So here we're doing a bigram of words. So we have a sentence. We just tokenize it to split it up into words. And then we call the n-gram function in TensorFlow text that groups those words together, which basically is joining a string. So every 2 words are grouped together, as you can see. So that's generally a bigram. So trigrams is 3. So you can see here we split our sentence into characters, and then we group them together with every 3 characters. We set the width to 3. And then in this situation, the default is separator is a space, and so we just do the empty string. So the other 2, it also works with numbers. So if we have a series here, 2, 4, 6, 8, 10 is our tensor. We want to sum up every 2 numbers, so 2 plus 4 is 6, 4 plus 6 is 10, and so on. And then also average, which is the mean reduction type. So where this might, generally when you talk about like n-grams, you are talking about it in a language context. But where this would be helpful, let's say, if you're taking like temperature readings every 20 minutes, and so you had a series of temperature readings every 20 minutes, but what you want to actually feed in your model is an average of those temperatures over an hour period every 20 minutes. You could do a trigram with a reduction of mean. So it takes the average of those 20-minute intervals, and so you get average temperature over the hour at every 20 minutes, and you can feed that into your model. But generally, like I said, with the bigrams and trigrams, it's often used in NLP, and how that works is you generally split it up either into words or characters, and then have a vocabulary dictionary you can look up those groupings in. In our example, we cheat a little bit. We get our code points from our input. So we have this input. We can get code points. As you see again, the rank is increased. So we had a shape of 3, and then had now a shape of 3 with a ragged dimension. And we use merge dimensions to actually combine those 2 dimensions because we don't care about it in this case. So it takes a second to last axis and the last axis and combines them. And then we're just summing those up to create kind of our unique ID in this case that will feed into the model. I think generally, like I said, you would do string joins and look those up in a vocabulary, but for this case model, it works. And we just cast those values. This is our preprocessing function that, again, we create a data set using TF record data set, map our preprocessing function on those values, and then the model that's created, we can train using this preprocessing function. All right, finally, I was going to go over the BERT preprocessing. There's a little bit more code in this one, so I just want to say that, we provide the BERT tokenizer for you. So feel comfortable in knowing that you don't really have to write this if you don't want to. You can just use the BERT tokenizer tokenize, and it does all this stuff for you. But I feel like there's a lot of good examples in what this does, and if you're doing text preprocessing, these are things you should probably think about and know about. So I wanted to go over it with you. So this is like a slim version of that. So what it does, what BERT did in its preprocessing, it lowercased and normalized the text. And then it did some basic tokenization. It split out Chinese characters and emoji by character splitting, and then it did word piece on top of all that. With lowercase and normalizing, this is like very common that you would do when you're looking up words in your vocab. You want the words to match and not have like duplicate words. So capitalization kind of gets in the way with that. Words at the beginning of a sentence are capitalized, so when you look it up, it would be like in your dictionary or vocabulary twice. And so it's generally thought that you would lowercase these. And normalization is a lot of Unicode characters with accents can be represented in different ways. And so normalization basically normalizes that text so it's represented in a single way and again, so you don't have the same word multiple times in your vocabulary, which would confuse your model also as making your vocabulary larger. So we provide casefold, which is just an aggressive version of toLower. What it does is it lowers lowercase's characters. It works with non-Latin characters, accented characters. It doesn't mess up non-letters, so it keeps them as is, and does NFKC folding and normalization. So I'll talk a little bit more about that. So we do that in our first step. I have examples of what this would look like. So in this example, it really is just lowercasing our I in its. And then BERT actually normalized to NFD, and because casefold does NFKC, we're going to normalize to that next. I won't go over this. Just know again that like letters have many different forms, so it's good to have like a single normalization. So when you're working with international characters, they're not represented in different ways. So here we are. We just normalized to NFD. Now we're going to do some basic tokenization. We'll split on Unicode scripts. Tokenize our text. And then what you might notice here is while our sentence "it's a trap" has been tokenized, the Chinese characters have not. And that's because it's a single script throughout that whole sentence, and there are no spaces or any other method of like defining separations in words. So what we want to do is we want to like split that up. So this is kind of like where a lot of code comes in. You can follow. And I think the main point is just to know that like these things, we've thought about, and if you run across it, there's like ways to work around this. I prepared you, tried to. And it's simple ops when we step through it, you'll see. So first, we just get code points, we get code points of the characters. And then we just get script IDs of those characters. So you can see that the first sentence is all script 17, which is Han script, it's Chinese. And then our Latin characters are 25, and emoji and punctuation 0. And we can just apply math.equal like you can on our ragged tensor. It gives you, and we're just checking if it's Han script, so we have true. And then we use the slice notation to just grab the first character, because we know they're all the same already from our Unicode script. Then we also want to check for emoji. In TensorFlow text, we provide a function word shape, which you can ask basically different questions on words. It's basically like different regular expressions that you want to ask. So here we're asking, does this text have any emoji? Other ones is like, is there any punctuation? Are there any numbers? Is my string all numbers? And so these are things you might want to like find out about, and we provide you a method to do that. And so here we just or our two conditions together to say whether we should split or not. It works with ragged. And then we go ahead and split everything into characters so that when we do our where clause and our conditional, if we should split or not, if we should split, we grab it from the characters that we've already split. If not, we just grab it from our tokens that we used when we tokenized. And here we just do a little reformatting of how the shape looks. So once we've done that, can finally word piece tokenize. We provide it with our vocab table. We split it up into subwords. And we have an extra dimension, so we just get rid of that with merged ins. All right, we made it through that. Wasn't too bad. And so, we apply this just as we did before. We have a data set we've created with TF data. We map our pre-processing across from that. Here we can grab a classifier BERT model from the official BERT models and just train on that classifier. So I know that was a lot to go through. Hopefully you followed along. But the main thing to know is that, as TF text, we're looking to basically bring in all that pre-processing inside the graph, so you don't have a problem. You don't have to worry about training skew. You can just write your TensorFlow and train. And so we do that by giving you what I consider a superior data structure for sequence data as well as text data through ragged tensors and the APIs that are required for this pre-processing. Again, you can install it with pip install TensorFlow text. And thank you. Here's some links. That's our GitHub. If there's anything that you think is missing that we should add, feel free to add an issue. And we also have a Colab tutorial on tensorflow.org that you should check out, and it'll walk through some of this more slowly through a Colab for you. Thanks.
7 minutes. Do you want to do Q&A?
Oh, yeah.
We'll do that.
Okay.
Okay, so we still have about 7 minutes left, so we can open this up for Q&A. There are some microphones on either side, but I can also help provide those if needed.
Do you want to go to the microphones or grab these mics? Okay, go ahead.
Hi, very nice to see that you have all this support. Just a quick question. Can TF text handle Japanese text that's a mixture of hiragana, katakana, kanji, romanji, all thrown in? Really?
Yeah, like in this previous example where we go through the characters, there's a lot of the core Unicode we've added to core TensorFlow. But when, I don't know where we are in here. So when we're searching for like the scripts, this is ICU, which is like the open source library scripts. And so you can just as well like grab that kanji, and they have different script tokens there.
Thank you.
Sure. We'll just switch sides back and forth. Here we go.
Yeah. Thanks for the information. For inferencing, do you send in text, or do you have to put it in a tensor and send it?
Yeah, no, you can send text. So at inference time, like here the training, we use this like pre-processing function. And so you can use that same pre-processing function. When you save your model in saved model, you give it a serving input function that basically does pre-processing on your input. And so if you send in like those full string sentences, you can use the same function or a variation of that in that input function, and so it should process.
Okay, thank you.
Input. Sure. Back over here.
Hi. Thank you very much. And my question kind of relates to his question. So what's the advantages of applying it with a map versus having a layer that does it? Because you could, even with a Lambda layer or with the new RFC for pre-processing layer, have a layer that does it?
A layer that does the pre-processing?
Yeah, just applies that function and then it's saved as a checkable as part of the model?
Yeah, no, you could certainly do some of this with layers. Actually, we're looking at like what layers we should provide, and someone on our team is helping Karis in building out like their pre-processing layer, which is basic, and if there's added functionality that we find that people need, we'll supply it for in our TensorFlow text library. So it's really up to you as someone who wants to model it, like how you want to apply those.
Thank you for the talk. Two quick questions. The first one is, do the tokenizers that you provide also have a decoding function so that you go from the tokens, from the integers to the sequence of text?
From the integers, yeah, those TF strings Unicode decode. Is that what you're talking about? From code points, or are you?
Then talking about, so for instance, if you decode them in, for instance, with a BERT vocabulary, then you will have all these additional characters there, and then you want to concatenate them into, again, a sequence of text that's proper text, right?
Yeah, so you're, I think what you're asking is, so if you send your word through a BERT model and you get a vector representation, if you can translate that vector representation back to text?
Yeah, because that's the case when you, for instance, generate text. And so then you may want to map that text back, like the sequence of generated tokens back into a string of text.
Yeah, I mean, this is more along the lines of kind of like, I think you want like an encoder-decoder model. Like, there's models that do this. It's not something that is like we provide inside the library.
Well, we can take it flying. It's like such a different question. The second question is why this is not in TensorFlow?
Yeah. So with 2.0, I mean, you might know that like TensorFlow has gotten rid of contrib, and it's kind of for the core team has gotten unhandily, or it's too much to handle. The tests are running too long, and it's really like it's too much for one team to maintain. And so, you know, I think we'll see more kind of modules like TensorFlow Text to that are like focused on one particular area like this. As a team, like we want to make it easier across. So a lot of the stuff we've done, like with ragged tensors, some of the string ops are actually in core TensorFlow. But for some of these things that are outside the scope, like n-grams and tokenization, it's just a separate module.
Thank you.
Sure.
Hi.
Go ahead.
So since TF text can be incorporated into the TensorFlow graph, is it intended that you actually build a model with this pre-processing step? And if true, like what are there like performance implications in like TensorFlow serving? If that's there, has that been measured? And
yeah, there's definitely like some performance. I think, you know, it's done at the input level. I'm just going to skip ahead to right here. So it's done at the input. So this is actually a problem that TF Data is looking at as far as like consuming this data and then parallelizing. Right. I said this wrong earlier today too. Parallelizing these like input functions. And so if you're actually your model's on GPU or TPUs, right, like the input's parallelized and then you're feeding as much data as possible. So this is like something you might worry about and look at, but it's also what a lot of other people are looking at, helping.
Okay, and then, yeah, I guess if it's part of the TensorFlow graph in TensorFlow serving, like how are like the nodes allocated and computed, right? Like it's pre-processing on the CPU or like?
Yeah, most of this is done on the CPU.
Okay.
I'd say all of it.
Can I just quickly ask, are you compatible with TF2? Because I just pip installed TensorFlow Text and it uninstalled TensorFlow 2 and installed 1.14.
So if you did, so like I said, the versions need to match. If you just do pip install TensorFlow Text equals 2.0.0, which I think maybe why it did that is because that version is actually a release candidate, so just do RC0. It'll reinstall TensorFlow 2 for you.
Okay.
So, yeah. Sure. Last question.
Yeah, first of all, I'd like to say that this is really cool. Second is that do TF.text integrate with other NLP libraries such as like SpaceC or anything in that area? Just out of curiosity.
No, our focus is really just on TensorFlow right now.
Okay.
Thanks.
Thank you, Robbie.
Hey everybody, welcome to the ML and AI Sandbox here at I/O 2019. So in the keynote, we saw some amazing stuff that you can accomplish with on-device ML. And I'm here with TensorFlow Lite, showing developers how they can build that same stuff themselves. So we've got everything through from object detection to image classification and voice recognition. And we're showing people how they can deploy that down to devices that are really tiny and run for weeks on a single battery. So to really show you what's possible with TensorFlow Lite on device, we built this amazing experience called Dance-like.
Okay, behind me is Dance-like. It's a super fun application using TensorFlow Lite, which is TensorFlow's mobile and embedded systems framework for running machine learning. It basically teaches people how to dance, and so it does this by running pose segmentation on the GPU. We have a bunch of GPU-related ops that we just released for TensorFlow Lite, so you should check those out. It enables you to run super fast models. We're running 2 in real time and giving the user a heap of feedback which helps them dance better. So to go and build really interesting applications on mobile phones, embedded systems, and executing this all on device, you can go to tensorflow.org/lite. There's heaps of sample code, there's lots of documentation and tutorials, and you can go and build an amazing application like Dance-like and release it to the world.
What we're looking at here is a model called PoseNet. PoseNet is a model that's trained on images of human beings and is trained to predict their skeletal pose. This model here is actually running entirely in the browser with a library called TensorFlow.js. TensorFlow.js is a machine learning library for JavaScript that can run entirely in the browser and use your GPU through WebGL. Now, TensorFlow.js also runs in Node.js using the entire TensorFlow C++ binary and all of its hardware acceleration stories behind it. Piano Genie is a model that runs in TensorFlow.js entirely in the browser as well that generates MIDI notes as part of a piano performance. Now, this model is interesting because it brings a human in the loop and lets the human condition where the model is actually going to go. TensorFlow.js is open source and is available online on tensorflow.org/js, as are multiple more examples and demos of how to use it. Head over there today to start building machine learning for the browser.
So we take an old cell phone, we put it up in the trees, and it listens to all the sounds of the forest to pick up the sound of anything that indicates there's some danger.
Já tem um caminhão aqui para carregar as madeiras que estão derrubadas, né? E aqui está a nossa floresta sendo desmatada pelo madeireiro. Tá? No ponto de vista de vocês estão achando bom o que está acontecendo na nossa floresta? Não. Por quê?
Porque está acabando as frutas, não tem mais árvores.
E você, Isaac? O que você acha?
Estão cortando madeira, aí não chove muito aqui.
Quando eu era pequeno, tinha muita fartura. Agora já está para todo mundo ver, né? Os estragos da floresta que está feita. Já é uma floresta totalmente furada, né?
A floresta, para nós, é tudo na vida. A invasão traz a devastação, acaba com tudo que tem na floresta, acaba a floresta em si. A gente monitorava fiscalizando a pés, esbarrando com os invasores, aí nós tínhamos vários problemas, vários conflitos. Morreu parente da gente, morto pelos pistoleiros ainda. E isso começou a marcar na nossa vida. No correr do tempo a gente foi buscando o mecanismo. O entorno aqui, eu acho que nós temos 30% ainda que ainda falta nós dominar dessa parte da área.
Would it be easier for us to do that by focusing on the perimeter?
O Toffoli, quando ele veio a primeira vez, veio ouvir a gente qual era a nossa necessidade e a gente ficou se perguntando, será se de fato ele vai conseguir fazer alguma coisa porque nós estamos querendo?
The Tembe people are an amazing example of a people that's trying to preserve their forest. They are well organized, they're well educated, are not afraid to use different tools, new technologies. They're looking for collaboration, they're not looking for help. People on the ground in these places, they're the solution. They're the ones who can actually really fight off deforestation, but technology can play a really big part in helping them do it more safely and more effectively.
O Toffoli está trabalhando muito num sistema de monitoramento para que a gente possa ter esse controle e passar para as autoridades a necessidade que nós temos, ou melhor dizer, facilitar as nossas denúncias.
And all you have to do is just be kind of precise with this one here, because the antenna is both fragile and sensitive. You want to put the microphone on there. Yeah, that's good. Old cell phones are available to almost anybody all the time. And these aren't trash. These are actually really, really powerful little computers. They can connect to the networks that are there. They can record the sound. They can do all this great processing. The hard parts, of course, have to do with making it possible to power them and making sure they can actually pick up sounds from a great distance. But all these are things that you can do with pretty standard electronics.
Cool.
Pronto?
Pronto.
Here
we go. Catu.
The Tembe themselves have at most 30 rangers, 30 warriors that are able to sort of patrol the area and take responsibility for protecting it. And yet we're talking about an area that's huge. And that's where this ability for us to be able to listen to parts of the forest 24/7, it really increases the efficiency and the safety of the entire operation for them. And that's a really critical tool given what they're up against. No person could be able to detect the chainsaw at a kilometer away, given how loud and how noisy and how complex the sound really is. So we're actually using an open source machine learning tool, TensorFlow, that's able to detect a logging truck, the sounds of birds or animals or chainsaws in the forest. It's amazing what they can actually find that we cannot even hear. And it can send a real-time alert to the rangers, to the guards, to the chiefs, so they can decide how to respond.
O sistema vai acusar onde é que está tendo problema. Aí não tem aquele tempo de correr para estar fiscalizando meses e meses, como a gente fazia antes. Quer dizer, nós ter mais tempo para a nossa cultura, ter mais tempo para a nossa família, ter mais tempo para sobreviver. Um povo sem cultura não é ninguém. O nosso sonho é de ter nossa floresta em pé, preservada, que nós não deixe para os nossos filhos e nossos netos os problemas que nós estamos tendo hoje. Nosso sonho é viver em paz, como antigamente, como nós vivíamos.
And Taylor Roby. They're engineers on our TensorFlow team at Google, and they're going to talk to us about performance and scaling in TensorFlow 2.0. Thank you.
Thanks. So I'm Taylor. I'm an engineer on the TF Keras team.
And I'm Priya. I'm also an engineer on the TensorFlow team. I lead the distribution strategy team.
And today we're going to be talking about writing performant models in TensorFlow 2. Just to give a brief outline of the talk, we're first going to talk about the structure of a training loop in TensorFlow 2, and then we're going to talk about the different APIs that you can use to make your training more performant. The first API that we're going to be talking about is TF Data. This is the API for writing high-performance pipelines to avoid various sorts of stalls and make sure that your training always has data as it's ready to consume it. Next, we're going to be talking about TF Function. This is how you can formulate your training step in a way that is efficient so that the runtime can run with very minimal overhead. And finally, we're going to be talking about TF Distribute, which is how to target your training to specific hardware and also scale out to more hardware. In order to demonstrate all of these APIs, we're going to be walking through a case study, starting with the most naive implementation, and then progressively adding more performant APIs and looking at how that helps our training. So we're going to be training a cat classifier, because we're an internet company, that's what we do, and we're going to be training it on MobileNet v2. This task was largely chosen arbitrarily just as a representative task, so these lessons should be broadly applicable to your workflows as well. And there's a notebook, and I'll put the link back at the end of the slide, so you are encouraged to take a look afterward and compare back to the talk. So let's get started. A brief overview of training loops in TensorFlow 2. We're going to be writing a custom training loop, and the reason is that we want to look at the mechanics of what the system is actually doing and how we can make it performant. If you're used to using a higher level API like Keras Model Fit, these lessons are still broadly applicable. It's just that some of this will be done automatically for you. So if we want to show why these APIs are important, it's useful to really dig into the internals of the training loop. So because we're training on MobileNet, we've chosen to use the Keras Applications MobileNet v2, which is just a canned MobileNet v2 implementation. We're training a classifier, so we're going to be using sigmoid cross-entropy with logits. This is a numerically stable cross-entropy function. And then finally, we're going to be using the Keras SGD optimizer. So if we were to call our model on our features, in this case, it's an image classification task, so our features are an image, we would get logits, which is the predicted class. If we then apply our loss function comparing the labels and the logits, this gives us a scalar loss, which we could then use to optimize and update our model. We'll want to call all of this under a TF gradient tape. What the gradient tape does is it watches the computations as they're performed and maintains the metadata and keeps the activations alive. This is what allows us to take gradients, which we can then pass to the optimizer to update our model weights. And finally, if we wrap all of this into a step and then iterate over our data in mini batches, applying this step in each mini batch, this comprises the general structure of our training loop. On the data side, we're going to start out with just a strawman Python generator to show the different parts of the data pipeline, and then we'll look at its performance a little bit later. So what do we need to do? Well, first we'll want to shuffle the data so that we see a different ordering each epoch. We'll need to load all of the images from disk into memory so that they can be consumed by the training process. We'll also want to do some augmentation. So we'll want to resize the images from their native format down back to the format that the model expects, and then we'll do some task-specific optimization. So in this case, we'll randomly flip the images, and we'll add some pixel-level noise to make our training a little bit more robust. And finally, we'll need to batch these. So the generator that I've shown is producing examples one at a time, but we'll need to collect them into mini batches, and the key operation for that batching operation is a concatenation. It's worth noting that different parts of the data pipeline will stress different parts of the system. So for loading the disk, this is an I/O-bound task, and we'll generally want to consume this I/O as fast as possible so that we're not constantly waiting for images to arrive from disk one at a time. Secondly, the augmentations tends to be rather CPU intensive because we're doing various sorts of math in our augmentation. And finally, batching tends to be a somewhat memory intensive task because we're copying examples from their original location into the memory buffer of our mini batch. So now that we have a scaffolding, let's just go ahead and run this. We're going to be running on an NVIDIA V100 GPU. By default, TensorFlow will attempt to place ops on the optimal device, and because we're doing large matrix multiply sort of operations, it will place them on the GPU. However, we find that our training at the start is pretty lackluster. We're under 100 images a second, and if we actually look at our device utilization, it's well under 20%. So what's going on here? Well, in order to determine that, we can actually do some profiling, and TensorFlow 2 and TensorBoard makes this quite easy to do. You might already be familiar with TensorBoard. This is the standard way of monitoring training as it runs. So you might be, for instance, familiar with the Scalars tab, which will show things like losses and metrics as your training continues. Well, in TensorFlow 2, there's a new tab, and that is the Profiler tab. And what this does is it looks at each op as it runs in TensorFlow and shows you a timeline of how your training is progressing. And we're going to look in a little bit more detail about how to read and interpret these timelines. Before we do, however, let's talk about how to enable it. So it's quite straightforward. You simply turn on the profiler. This will signal to the runtime that it should keep records of ops as it runs them. Write your program as normal, and then simply export this trace, and this will put it in a format that TensorBoard can consume and display for you. So this is a timeline. Moving left to right, we have time, and then each row is a different thread. And you can see that they're annotated with device. So the top row is the CPU, and then the bottom ones are the various GPU threads. And in this case, we're looking at 3 different training steps. Each vertical line is an individual op that's been run by TensorFlow. So you can see that the ops are scheduled from the CPU, and then they appear on the GPU stream, and the GPU actually executes the ops, and this is where the heavy lifting is done. But you can also see that we have these large gaps in between where no ops are running and our system is essentially stalled. And this is because after each step, we have to wait for our naive generator to produce the next batch of data. So this is obviously quite inefficient. So Priya is going to tell you how we can improve that.
Thanks, Taylor. So as Taylor just showed us, writing your own input pipeline in Python to read data and transform it can be pretty inefficient. TensorFlow provides the TF-Data API to allow you to easily build performant and scalable input pipelines. You can think of the TF-Data input pipeline as an ETL process. So the first stage is the extract stage, where we read the data from, let's say, network storage or from your local disk, and then you potentially are parsing the file format. The second stage is the transform stage, which is where you take the input file data and transform it into a form that's amenable to your ML computation. So this could be image transformations and specific to your ML task, or they could be generic transformations like shuffling or batching that apply to a lot of ML tasks. Once you've transformed this data, you can then load it into your accelerator for your training. So let's take a look at some code to see how you can use TF-Data to write the same input pipeline that Taylor showed you before, but in a much more efficient way. So there's a number of steps here, and I'll go over them one by one. The first one is we create a simple data set consisting of all the file names in our input. So in this case, we have a number of image files, and the path glob specifies how to find these file names. The second thing we do is we want to shuffle this list of file names, because in training, typically you want to shuffle the input data as it's coming in. And we apply a transformation called the map transformation. And we provided this get bytes and label custom function. And what this function does is that it's going to read the file one by one using the TF-IO read file API. And it uses the file name path to compute the label and returns both of these. So these 3 steps here comprise the extract stage that I talked about before. We're reading the files and parsing the file data. Note that this is just one way in which you can read data using TF-Data, and there are a number of different APIs that you can use for other situations, which we've listed here. The most notable one is the TF-Record dataset API, which you would use if your data is in the TF-Record file format. And this is potentially the most performant format to use with TF-Data. If you have your input in memory in a NumPy array, let's say, you can also use the from tensor slices API to convert it into a TF-Data dataset and do subsequent transformations like this. The next thing we do is another map transformation to now take this raw image data, but convert it and do some processing to make it amenable for our training task. So we have this process image function here, which we provide to this map transformation. And if you take a look, this could look something like this. We do some decoding of the image data, and then we apply some image processing transformations such as resizing, flipping, normalization, and so on. The key things to note here are these transformations are actually very similar and correspond one-to-one to what you saw before in the Python version. But the big difference here is that now instead we're using TensorFlow ops to do those transformations. The second thing is that TF-Data will take the custom function that you specify to the map transformation, and it will trace it as a TensorFlow graph and run it in the C++ runtime instead of Python. And this is what allows it to make it much more efficient than Python. And finally, we use the batch transformation to batch the elements of your input into mini batches, and this is a very common practice for training efficiency in ML tasks. So before I hand it off to Taylor to talk about how using TF data can improve the performance in our MobileNet example, I want to walk through a few more advanced performance optimization tips for TF data. And I'll go through them quickly, but you can also read about them in much more detail on the page that's listed here. The first optimization that I want to talk about is pipelining. And this is conceptually very similar to any other software pipelining that you might be aware of. The high-level idea here is that when you're training a single batch of data on your accelerator, we want to use the CPU resource at the same time to process and prepare the next batch of data. What this will do is that when the next training step starts, we don't have to wait for the next batch of data to be prepared. It will automatically be there, and this can reduce the overall training time significantly. To use software pipelining in TF data is very simple. You can use the prefetch transformation as shown here. The second optimization that I want to talk about is parallelizing the transformation stage. So if by default, the map transformation will apply the custom function that you provide to each element of your input data set in sequence. But if there's no dependency between these elements, there's no reason to do this in sequence, right? So you can parallelize this by passing the num_parallel_calls argument to the map transformation. And this indicates to the TF data runtime that it should run these map operations on your elements of the data set in parallel. And the third optimization that I want to talk about is parallelizing the extraction stage. So similar to how transforming your elements in sequence can be slow, similarly reading files one by one can be slow as well. So of course you want to parallelize it. And in this example, since we're using a map transformation to read our files, the way you do it is actually very similar to what we just saw. You add a num_parallel_calls argument to the map function that you have to read your files. Note that if you're using one of the built-in file readers, such as the TF record dataset, you can also provide very similar arguments to that in order to parallelize the file reading there. So if you've been paying close attention, you'll notice that we have these magic numbers x, y, and z on the slides, and you might be wondering, how do you determine the optimal values of these? And in reality, it's actually not very straightforward to compute the optimal values of these parameters, because if you set them too low, you might not be using enough parallelism in your system. And if you set them too high, it might lead to contention and actually have the opposite effect of what you want. Fortunately, TF data makes it really easy for you to specify these. Instead of specifying specific values for these XYZ arguments, you can simply use this constant TF data experimental auto-tune. And what this does is it indicates to the TF data runtime that it should do the auto-tuning for you and determine the optimal values for these arguments based on your workload, your environment, your setup, and so on. So that's all for TF data. I'm now going to hand it off to Taylor to talk about what kind of performance benefits you can see.
Thanks, Priya. So on the right here, we can see the timeline before and after we add TF data. So before, we have this long stall in between our training steps where we're waiting for data. Once we've used TF data, you'll note two things about this timeline after. The first is that the training step begins immediately after the previous one, and that's because TF data was actually preparing the upcoming batch while the previous training step was happening. The second is that before, it actually took longer than the time of a batch in order to prepare the next batch, whereas now we see no large stalls in the timeline. And the reason is that TF data, because of the native parallelism, can now produce batches much more quickly than the training can consume them. And you can see this manifest in our throughput with more than a 2x improvement. But sometimes there are even more stalls. So if we zoom in on the timeline of one of our training steps, we'll see that there are a number of these very small gaps. And these are launch overheads. So if we further look at different portions of the GPU stream, near the end, this is what a healthy profile looks like. You have one op runs and then finishes, and immediately the next op can begin, and this results in an efficient and saturated accelerator. On the other hand, in some of the earlier parts of the model, an op is scheduled on the GPU immediately chews through it, and then it simply waits idle for Python to enqueue the next op. And this leads to very poor accelerator utilization and efficiency. So what can we do? Well, if we go back to our training step, we can simply add the TF function decorator. What this will do is this will trace the entire training step into a TF graph, which can then be run very efficiently from the TF runtime. And this is the only change needed. And now if we look at our timeline, we see that all of the scheduling is done in this single, much faster op on the CPU, and then the work appears on the GPU as before. And this also allows us to use the rich library of graph optimizations that were developed in TensorFlow 1. And you can see this is, again, almost another factor of 2 improvement. And it's pretty obvious in the timeline on the right why. Whereas before TF function, when we were running everything eagerly, we had all of these little gaps waiting for ops. Now, once it's compiled into a graph and launched from the C++ runtime, it's able to do a much better job keeping up with the GPU. So the next optimization that I'm going to talk about is XLA, which stands for Accelerated Linear Algebra. To understand how XLA works, we have just this simple example of a graph with some skip connections. What XLA will do is it will cluster that graph into subgraphs and then compile the entire subgraph into a very efficient fused kernel. And there are a number of performance gains from using these fused kernels. So the first is that you get much more efficient memory access because the kernel can use data while it's hot in the cache as opposed to pushing it all the way down the memory hierarchy and then bringing it all the way back. It also reduces the overhead from launch overhead. This is the C++ executor launch overhead by running fewer ops but the same math. And finally, XLA is heavily optimized to target hardware. So it does things like use efficient hardware-specific vector instructions, specialize on shapes, and choose layouts so that the hardware is able to have very efficient access patterns. And it's quite straightforward to enable. You simply use this tfconfig optimizer set JIT flag, and this will cause every TF function that runs to attempt to compile and run with XLA. And you can see that in our example, it's a very stark improvement. It's about a 2.5x improvement in throughput. The one caveat with XLA is that a lot of the optimizations that it uses are based on specializing on shapes. So XLA needs to recompile every time it sees new shapes. So if you have an extremely dynamic model, for instance, the shapes are different each batch, you might actually wind up spending more time on the XLA compile than you gain back from the more efficient computation. So you should definitely try out XLA, but if you see performance regression rather than performance gain, it's likely that that's the reason. So next we're going to talk about mixed precision. If we want to go even faster, then we can give up some of our numeric stability in order to obtain faster training performance. So here I have the IEEE float32, which is the default numeric representation in TensorFlow, but there are also 2 half-precision formats that are relevant. The first is bfloat16, where we keep all of the exponent and simply chop off 16 bits of mantissa. And the other is float16, where we give up both some exponent in exchange for keeping a little bit more mantissa. And what's important about these formats is that they actually have native hardware support. So TPU has hardware support for very efficient bfloat16 operations, and GPUs have support for very efficient float16 operations. So if we can formulate our computation in these reduced precision formats, we can potentially get very high speedups from the hardware. In order to enable this, we need to do a couple things. First, we need to choose a loss scale. So what is a loss scale? A loss scale is a constant that's inserted into the computation, which doesn't change the mathematics of the computation, but it does change the numerics. And so this is a knob where the runtime can adjust the computation to keep it in a numerically stable range. The next thing we'll want to do is we'll want to set a mixed precision policy. And this will tell Keras that it should cast tensors as they flow through the model in order to make sure that the computation is actually happening in the correct floating point representation. In a custom training loop, we'll want to wrap our optimizer in this loss scale optimizer. And this is the hook by which the loss scale is inserted. So as training happens, TensorFlow will do a dynamic adjustment of this loss scale to balance vanishing gradients from FP16 underflow while still preventing nans from FP16 overflow. If you're using the model fit workflow, this will be done for you. And finally, we generally need to increase our batch size when we're doing this mixed precision training. The reason is that mixed precision makes computing a single example much less expensive. So if we just turn on mixed precision, we can go from a saturated accelerator in float 32 to an underutilized accelerator in float 16. So by increasing the batch size, we can go back to filling all of the hardware registers. And we can see this in our example. If we just turn on float 16, there's actually no improvement in performance. But if we then increase our batch size, then we see a very substantial improvement in performance. It is worth noting that because we've both reduced the numeric precision and changed the batch size, this can require that you retune the hyperparameters. And then finally, if we look at what are the remaining bits of performance. So about 60% of what's left is actually the copy from the host CPU to the GPU. Now, in a little bit, Priya is going to talk about distribution. And one of the things that the distribution-aware code in TensorFlow will do is it will automatically pipeline this prefetch. So you'll actually get that 60% for free. And then finally, you have hand tuning. So you can give up some of the numeric stability. You can mess with thread pools. You can manually try and optimize layouts. This is included largely for completeness in case you're curious what real low-level hand tuning looks like. But for most cases, given that we can get the vast majority of the performance with just simple, idiomatic, easy-to-use APIs, this very fine hand tuning is not recommended. But once we've actually saturated a single device, we need to do something else to get another order of magnitude improvement. And so Priya is going to talk to you about that.
Thanks, Taylor. All right, so Taylor talked about a number of different things you can do to get the maximum performance out of a single machine with a single GPU. But if you want your training to go even faster, you need to start scaling out. So maybe you want to add more GPUs to your machine, or perhaps you want to train on multiple machines in a cluster, or maybe you want to use specialized hardware such as cloud TPUs. TensorFlow provides distribution strategy API to allow you to do just that. We built this API with 3 key goals in mind. The first goal is ease of use. We want users to be able to use the distribution strategy API with very little changes to their code. The second goal is to give great performance out of the box. We don't want users to have to change their training code or tune a lot of knobs to get the maximum efficiency out of their hardware resources. And finally, we want this API to work in a variety of different situations. So for instance, if you want to scale out to multiple GPUs or multiple machines or TPUs, or if you want different distributed training architectures, such as synchronous or asynchronous training, or you're using different types of APIs. So if maybe you're using high-level keras APIs like model.fit, or you have a custom training loop, as in our example earlier. We want distribution strategy to work in all of these potential cases. There are a number of different ways in which you can use this API, and we've listed them here in the order of increasing complexity. The first one is if you're using keras high-level API model.fit for your training loop, and you want to distribute your training in that setup. The second use case is what we've been talking about in this talk so far, where you have a custom training loop and you want to scale out your training. The third use case is maybe you don't have a specific training program, but maybe you're writing a custom layer or a custom library, and you want to make it distribution aware. And finally, maybe you're experimenting with a new distributed training architecture and you want to create a new strategy. In the talk here, I'm only going to talk about the first 2 cases. So let's begin. The first use case we'll talk about is if you have a single machine with multiple GPUs and you want to scale up your training to this situation. For this setup, we provide mirror strategy. Mirror strategy implements synchronous training across multiple GPUs on a single machine. The entire computation of your model would be replicated on each GPU. All the variables of your model would be replicated on each GPU as well, and they will be kept in sync using all-reduce. Let me go through step by step to talk about what this synchronous training looks like. Okay, there was some gray boxes around these which are not really visible. But so let's say we have, in our example, we have 2 devices or 2 GPUs, device 0 and 1. And we have a very simple model with 2 simple layers, layer A and B. Each layer has a single variable. As you can see, the variables are mirrored or replicated on these 2 devices. So in our forward pass, we'll give a different slice of our input data to each of these devices. And in the forward pass, they will compute the logits using the local copy of the variables on these devices. In the backward pass, each device will then compute the gradients, again using the local copy. Once each device has computed the gradients, they'll communicate with each other and to aggregate these gradients. And this is where all-reduce that I mentioned before comes in. All-reduce is a special class of algorithms that can be used to efficiently aggregate tensors such as gradients across different devices, and it can reduce the overhead of such synchronization by quite a bit. There are a number of different such algorithms available, and some hardware vendors such as NVIDIA also provide specialized implementations of all-reduce for their hardware, such as the nickel algorithm. So once these gradients have been aggregated, the aggregated result would be available on each device, and each device can update its local copy of the variable using this aggregated tensors. So in this way, both the devices are kept in sync, and the next forward pass doesn't begin until all the variables have been updated. So now let's take a look at some code to see how you can use mirror strategy to scale up your training. As I mentioned, we'll talk about two types of use cases. The first one is if you're using the Keras high-level API, and then we'll come back to the custom training loop example after this. So the code here is some skeleton code to train the same MobileNet v2 model, but this time with using the model.compile and fit API in Keras. In order to change this code to use mirror strategy, all you need to do is add these 2 lines of code. The first thing you do is create a mirror strategy object, and the second thing is you move the rest of your training code inside the scope of this strategy. Putting things inside the scope lets it take control of things like variable creation. So any variables that you create under the scope of the strategy will now be mirrored variables. You don't need to make any other changes to your code in this case because we've already made components of TensorFlow distribution aware. So for instance, in this case, we have the optimizer, which is distribution aware, as well as compile and fit. The case we just saw was the simplest way in which you can create mirror strategy, but you can also customize it. So let's say by default, it will use all the GPUs available on your machine for training. But if you want to only use specific ones, you can specify them using the devices argument. You can also customize what all-reduce algorithm you want to use by using the cross-device ops argument. So now we've seen how to use mirror strategy when using the high-level Keras model.fit API. Now let's go back to our custom training loop example from before and see how you can modify that to use mirror strategy. And there's a little bit more code in this example because when you have a custom training loop, you have more control over what exactly you want to distribute, and so you need to do a little bit more work to distribute it as well. So here, this is the skeleton of the custom training loop from before. We have the model, the loss function, the optimizer, and you have your training step, and then you have your outer loop, which iterates over your data and calls the training step. The first thing you need to do is the same as before. You create the mirror strategy object, and you move the creation of the model, the optimizer, and so on inside the scope of the strategy. And the purpose of this is the same as before. But as I mentioned, you need to do a few more things, so this is not sufficient in this case. And let's go over each of them one by one. The first thing you need to do is to distribute your data typically. And if you're using TF data datasets as your input, this is straightforward. All you need to do is call strategy.experimental distribute dataset on your dataset, and this returns a distributed dataset which you can then iterate over in a very similar manner as before. The second thing you need to do is to scale your loss by the global batch size. And this is very important if you, so that the convergent characteristics of your model do not change. And we provide a helper method in the NN library to do so. And the third thing you need to do is to specify which specific computation you want to replicate. So in this case, we want to replicate our training step on each replica. So you can use strategy.experimental run v2 API to provide the training step function as well as your distributed input. And you wrap this whole thing in another TF function because we want all of this to run as a TF graph as well. So those are all the code changes you need to make in order to take the custom training loop from before and now run it in a distributed fashion using distribution strategy API. So let's go back and take a look at what kind of scaling you can see. So just out of the box, adding this mirror strategy to the MobileNet V2 example from before, we're able to get 80% scaling from when going from 1 GPU to 8 GPUs on a single machine. It's possible to get even more scaling out of this by doing some manual optimizations, which we won't be going into today. To give another example of the scaling, we ran multi-GPU training for ResNet50, which is a very popular image classification benchmark. And in this example, we also used the FP16 and XLA techniques that Taylor talked about before. And here you can see going from 1 to 8 GPUs, we're able to get 85% scaling. And this example was using the Keras model.fit API instead of the custom training loop example. If you're interested, you can look at the link in the bottom and you can try out this model yourself. Another example is using the transformer language model to show that this is not just for images. We're able to scale up other types of models as well. And in this case, we're able to get more than 90% scaling when running from 1 to 8 GPUs. So far we've been talking about scaling up to multiple GPUs on a single machine, but most likely you would want to scale even further to multiple machines, maybe with multiple GPUs or perhaps just with CPUs. For these use cases, we provide the multi-worker mirror strategy. As the name suggests, this is very similar to the mirror strategy that we've been talking about. It also implements synchronous training, but this time across all the different machines in your cluster. In order to do the all reduce, it uses a new type of op in TensorFlow called collective ops. Collective op is a single op in the TensorFlow graph which can determine the best all reduce to use based on a number of different factors such as the network topology, the type of communication available between the different machines, as well as tensor sizes. It can also implement optimizations such as tensor fusion. So for instance, if you have a lot of small tensors that you want to aggregate, it may batch them up into a single tensor in order to reduce the load on the network. So how can you use multi-worker mirror strategy? It's actually very similar to mirror strategy. You create a strategy object like so, and the rest of your training code actually remains the same, so I've omitted it here. Once you have the strategy object, you can put the rest of your code in strategy.scope and you're good to go. One more thing you need to do, however, in the multi-worker case is to give us information about your cluster. And one way to do that for multi-worker strategy is using the tfconfig environment variable. tfconfig, you might be familiar with this environment variable if you've used distributed training in using estimator in TensorFlow 1. So it basically consists of two components. The first is the cluster, which gives us information about your entire cluster. So here we have 3 different workers at these hosts and port. And the second piece is information about this specific worker. So this is saying this is worker 1. Once you provide this tfconfig, the task part would be different on each worker, but your training code can remain the same. And distribution strategy will read this tfconfig environment variable and figure out how to communicate to the different workers in your cluster. So we've been talking about multiple machines, multiple GPUs. What about TPUs? You've probably heard about TPUs in this conference somewhere else before. TPUs are custom hardware built by Google to accelerate machine learning workloads. You can use them through cloud TPUs, or you can even try them out in Colab. Distribution strategy provides TPU strategy for you to be able to scale up your training to TPUs. It's very similar to mirror strategy in that it implements synchronous training, and it uses the cross-replica sum API to do the all reduce across the TPU cores. You can use this API to scale your training to a single TPU or a slice of a pod or a full pod as well. And if you want to try out TPU strategy, you can try it with TensorFlow Nightlies, or you can wait for the 2.1 stable release for this as well. Let's look at the code to see how you can use TPU strategy. The first thing you need to do is to provide information about the TPU cluster. So the way you do that is create a TPU cluster resolver and give it the name or address of your TPU. Once you have a cluster resolver, you can use the experimental connect to cluster API to connect to this cluster and also initialize the TPU system. Once you've done these 3 things, you can then create the strategy object and pass the cluster resolver object to it. Once you have the strategy object, the rest of the code remains the same. You create the strategy.scope and you put your training code inside that. So I won't be going into that here. So looking at this code, you can see that distribution strategy makes it really easy to switch from training onto multiple GPUs or multiple machines to specialized hardware like TPUs. So that's all I was going to talk about distribution strategy. To recap, today we talked about a few different things. We talked about TF data to build simple and performant input pipelines. We talked about how you can use TF function to run your training as a TensorFlow graph. We talked about how you can use XLA and mixed precision to improve your training speed even further. And finally, we talked about the distribution strategy API to scale out your training to more hardware. We have a number of resources on our website, a number of guides and tutorials, so encourage you to check those out. And if you have any questions or you want to report bugs, please reach out to us on GitHub. We'll also be available in the expo hall after the talk if you have more questions. And finally, the notebook that we've been using in the talk is listed here, so if you want to take a picture, you can check it out later. That's all. Thank you so much for listening. I guess we have some time, so we can take some questions.
Hi. Thanks for the nice presentation. So I have two questions, both regarding inference. So you mentioned how we can use TensorBoard for profiling to see how well our CPUs and GPUs are utilized. Can we do the same to see how well our inferences are working?
Yes, so the profiler has no concept of training or inference. It just looks at ops as they execute. So if you're just running the forward pass, they'll show up all the same.
Okay. It also kind of depends on how you're doing inference. Like, are you doing it using Python APIs or like, are you?
Saved model. So let's say I have a saved model format and I want to use that in TensorBoard.
So you're not really using like any of the Python APIs, right?
So I use Python APIs, but basically to...
So you're loading a save model in Python and then, then you can use TensorBoard as well.
Okay. Regarding mixed precision, will it help in inference as well, and how to enable that?
It can potentially. Typically for inference, the integer low precision formats tend to be more important than the floating point ones. If you really care about very fast inference with low precision, I would suggest that you check out TF Lite because they have a lot of quantization support.
Okay, thank you.
Hello, I had just one question about how to save your model when you are training in a distributed strategy, because your code is replicated in all the nodes. And what's the official way to do this?
Yes, so you want to save a full save model?
Yes.
Yeah, so you can use the standard APIs, just the tf.save model.save, and what it'll do is it'll not save the replicated model, it'll save a single copy of the model. So then it's like any other save model. And you can then reload it. If you load it inside another strategy again, then it'll get replicated at that point, or you can use it for inference as another save model.
Because what I experienced was that all the nodes tried to save the model at the same time, and then it was an issue between a race condition with the placement where the models were saved.
And so you got an error?
Yes, it crashed.
Maybe we can talk after offline. Yes. It's supposed to work, but there could be bugs.
Thanks for the talk. I have a quick question about mixed precision and XLA. Will the API automatically use the hardware related features? Like, for example, in mixed precision, if you have Volta machine, it will be able to use Volta machine's mixed precision.
Yes, so it will, for instance, on Volta, it will automatically try to use the Tensor Core, and in fact, XLA and mixed precision synergize very well because mixed precision inserts a bunch of casts, and then XLA will go along and actually optimize a lot of those away. We'll try and make the layout more amenable to mixed precision. So XLA tends to talk to the hardware at a very low level.
Okay, so basically, from user point of view, it's transparent. If I run the same code on the CPU, on the old GPU, new GPU, it will automatically try to use the hardware ability.
Yes.
Okay, that's very cool.
I'm really sorry, we kind of have to stop this now for the live streaming.
We can take more questions outside the hall.
So thank you, Priya and Taylor. That was excellent.
Airbnb is an online marketplace. We have over 5 million different homes in 81,000 cities, which equates to hundreds of millions of photos, making it possibly the largest collection of images of homes in the world today. When a guest decides to select a home, one of the biggest influences in their decision is a diverse set of images. But a lot of times hosts will take a lot of pictures of a single room and forget to take pictures of the other rooms.
They also have the option to add captions, but a lot of cases they're totally off.
We were faced with a challenge of identifying what's actually in these pictures and present them properly on the site. That's one area where machine learning excels. The real challenge was one of scale. We had upwards of 500 million images to get through. It was going to take months to really go through all of these.
Using TensorFlow, we were able to speed up the process and deliver a reasonable model within days. BigHead is Airbnb's machine learning platform. We had the idea of making it very agnostic to different ML frameworks, and so we leveraged TensorFlow to train the model, and then BigHead helps with the model lifecycle, the feature management, and then TensorFlow serving to help serve the model results.
Before you think about which tool to use, you first think about which model to use, right? And we did research on this. We find that ResNet 50 was one of the state-of-the-art performing models. We used that as the basic architecture.
We used TensorFlow's Keras APIs and serving and some of the distributed GPU computations. This ultimately led to a pipeline that we can deploy to go through hundreds of millions of images very quickly.
So the end goal is basically using these classifications of images to make sure that their first initial set of photos that they see aren't just a picture of the garage and bathroom, but it could be of the living room that's gorgeous, in the bedroom, and the swimming pool. Future applications could be to detect different objects in homes, and if users decide to search on the website for specific amenity types, we can actually bubble that up to the surface.
If you like how Airbnb operates today, the reason was because of machine learning, because machine learning is almost everywhere in the company. Search ranking, pricing, predicting booking.
We're passing into the hundreds of models, so it's something I expect to keep growing.
And with a lot of these new frameworks coming out, we can make better experiences for our guests and better business decisions as well.
You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. We also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code, predict the y when x equals 10? You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you. Hi everyone, and welcome to episode 2 of TensorFlow Zero to Hero. In the last episode, you learned about machine learning and how it works. You saw a simple example of matching numbers to each other and how, using Python code, a computer could learn, through trial and error, what the relationship between the numbers was. In this episode, you're going to take it a little further by teaching a computer how to see and recognize different objects. For example, look at these pictures. How many shoes do you see? You might say 2, right? But how do you know they are shoes? Imagine if somebody had never seen shoes before. How would you tell them that despite the great difference between the high heel and the sports shoe, they're still both shoes? Maybe they would think, if it's red, it's a shoe, because all they've seen are these two and they're both red. But of course, it's not that simple. But how do you know that these two are shoes? Because in your life, you've seen lots of shoes and you've learned to understand what makes a shoe a shoe. So it follows logically that if we show a computer lots of shoes, it will be able to recognize what a shoe is. And that's where the dataset called Fashion MNIST is useful. It has 70,000 images in 10 different categories. So there's 7,000 examples of each category, including shoes. Hopefully, seeing 7,000 shoes is enough for a computer to learn what a shoe looks like. The images in Fashion MNIST are only 28 by 28 pixels, so they're pretty small. And the less data used, the faster it is for a computer to process it. That being said, they still lead to recognizable items of clothing. In this case, you can still see that it's a shoe. In the next few minutes, I'll show you the code that will teach you how to train a computer to recognize items of clothing based on this training data. The type of code you write is almost identical to what you did in the last video. That's part of the power of TensorFlow that allows you to design neural networks for a variety of tasks with a consistent programming API. We'll start by loading the data. The FashionMNIST dataset is built into TensorFlow, so it's easy to load it with code like this. The training images is a set of 60,000 images, like our ankle boot here. The other 10,000 are a test set that we can use to check to see how well our neural network performs. We'll see them later. The label is a number indicating the class of that type of clothing. So in this case, the number 9 indicates an ankle boot. Why do you think it would be a number and not just the text ankle boot? There's two main reasons. First, computers deal better with numbers. But perhaps more importantly, there's the issue of bias. If we label it as ankle boot, we're already showing a bias towards the English language. So by using a number, you can point to a text description in any language as shown here. Can you guess all the languages that we used here? When looking at a neural network design, it's always good to explore the input values and the output values first. Here we can see that our neural network is a little more complex than the one in the first episode. Our first layer has the input of shape 28 by 28, which if you remember was the size of our image. Our last layer is 10, which if you remember is the number of different items of clothing represented in our dataset. So our neural network will kind of act like a filter, which takes in a 28 by 28 set of pixels and outputs one of 10 values. So what about this number, 128? What does that do? Well, think of it like this. We're going to have 128 functions, each one of which has parameters inside of it. Let's call these F0 through F127. What we want is that when the pixels of the shoe get fed into them, one by one, that the combination of all of these functions will output the correct value, in this case 9. In order to do that, the computer will need to figure out the parameters inside of these functions to get that result. And it will then extend this to all of the other items of clothing in the dataset. The logic is, once it has done this, then it should be able to recognize items of clothing. So if you remember from the last video, there's the optimizer function and the loss function. The neural network will be initialized with random values. The loss function will then measure how good or how bad the results were, and then with the optimizer, it will generate new parameters for the functions to see if it can do better. You've probably also wondered about these, and they're called activation functions. The first one is on the layer of 128 functions, and it's called ReLU, or Rectified Linear Unit. What it really does is as simple as returning a value if it's greater than 0. So if that function had 0 or less as output, it just gets filtered out. And softmax has the effect of picking the biggest number in a set. The output layer in this neural network has 10 items in it, representing the probability that we're looking at that specific item of clothing. So in this case, it has a high probability that it's item 9, which is our ankle boot. So instead of searching through to find the largest, what softmax does is it sets it to 1 and the rest to 0, so all we have to do is find the 1. Training is then very simple. We fit the training images to the training labels. This time we'll try it for just 5 epochs. Remember earlier we had 10,000 images and labels that we didn't train with? These are images that the model hasn't previously seen, so we can use them to test how well our model performs. We can do that test by passing them to the evaluate method like this. And then finally, we can get predictions back for new images by calling model.predict like this. And that's all it takes to teach a computer how to see and recognize images. You can try this out for yourself in the notebook that I've linked in the description below. Having gone through this, you've probably seen one drawback, and that's the fact that the images are always 28 by 28 grayscale with the item of clothing centered. So what if it's just a normal photograph and we want to recognize its contents, and you don't have the luxury of it being the only thing in the picture as well as being centered? That's where the process of spotting features becomes useful, and the tool of convolutional neural networks is your friend. You'll learn all about that in the next video, so don't forget to hit that subscribe button, and I'll see you there. Hi, and welcome to episode 3 of Zero to Hero with TensorFlow. In the previous episode, you saw how to do basic computer vision using a deep neural network that matched the pixels of an image to a label. So an image like this was matched to a numeric label that represented it like this. But there was a limitation to that. The image you were looking at had to have the subject centered in it, and it had to be the only thing in the image. So the code you wrote would work for that shoe, but what about these? It wouldn't be able to identify all of them because it's not trained to do so. For that, we have to use something called a convolutional neural network, which works a little differently than what you've just seen. The idea behind a convolutional neural network is that you filter the images before training the deep neural network. After filtering the images, features within the images could then come to the forefront, and you would then spot those features to identify something. A filter is simply a set of multipliers. So for example, in this case, if you're looking at a particular pixel that has the value 192, and the filter is the values in the red box, then you multiply 192 by 4.5 and each of its neighbors by the respective filter value. So its neighbor above and to the left is 0, so you multiply that by -1. Its upper neighbor is 64, so you multiply that by 0, and so on. Sum up the result and you get the new value for the pixel. Now this might seem a little odd, but check out the results for some filters, like this one, that when multiplied over the contents of the image, it removes almost everything except the vertical lines. And this one, that removes almost everything except the horizontal lines. This can then be combined with something called pooling, which groups up the pixels in the image and filters them down to a subset. So for example, max pooling 2 by 2 will group the image into sets of 2 by 2 pixels and simply pick the largest. The image will be reduced to 1/4 of its original size, but the features can still be maintained. So the previous image, after being filtered and then max pooled, could look like this. The image on the right is 1/4 the size of the one on the left, but the vertical line features were maintained, and indeed they were enhanced. So where did these filters come from? And that's the magic of a convolutional neural network. They're actually learned. They're just parameters like those in the neurons of a neural network that we saw in the last video. So as our image is fed into the convolutional layer, a number of randomly initialized filters will pass over the image. The results of these are fed into the next layer, and matching is performed by the neural network. And over time, the filters that give us the image outputs that give the best matches will be learned, and the process is called feature extraction. Here's an example of how a convolutional filter layer can help a computer visualize things. You can see across the top row here that you actually have a shoe, but it has been filtered down to the sole and the silhouette of a shoe by filters that learned what a shoe looks like. You'll run this code for yourself in just a few minutes. Now let's take a look at the code to build a convolutional neural network like this. So this code is very similar to what you used earlier, where you have a flattened input that's fed into a dense layer that in turn is fed into the final dense layer that is our output. The only difference here is that I haven't specified the input shape. That's because I'll put a convolutional layer on top of it like this. This layer takes the input, so we specify the input shape. And we're telling it to generate 64 filters with this parameter. That is, it will generate 64 filters and multiply each of them across the image. Then, each epoch, it will figure out which filters gave the best signals to help match the images to their labels in much the same way it learned which parameters worked best in the dense layer. The max pooling to compress the image and enhance the features looks like this. And we can stack convolutional layers on top of each other to really break down the image and try to learn from very abstract features like this. With this methodology, your network starts to learn based on the features of the image instead of just the raw patterns of pixels. 2 sleeves, it's a shirt. 2 short sleeves, it's a t-shirt. Sole and laces, it's a shoe, that type of thing. Now we're still looking at just the simple images of fashion at the moment, but the principles will extend into more complex images, and you'll see that in the next video. But before going there, try out the notebook to see convolutions for yourself. I've made a link to it in the description below. And before we get to the next video, don't forget to hit that subscribe button. Thank you. Hi everybody, and welcome to the 4th and final video in this series of Zero to Hero with TensorFlow. I'm Lawrence, and today we're going to look back at the very first problem that we spoke about, and then we'll see how we can build a machine-learned model to solve it. Remember this, all the way back in episode 1, where we showed a scenario of rock, paper, and scissors and discussed how difficult it might be to create an application that recognizes hands of different shapes, sizes, ethnicities, decorations, and more. We discussed how difficult it would be to write code to detect and classify these, even for something as simple as a rock, paper, or scissors. But since then, you've looked into machine learning and you've seen how to build neural networks, first to detect patterns in raw pixels to classify them, and then to detect features using convolutions to have a convolutional neural network trained to spot the particular features that make up an item, like the soles of a shoe. Let's put all that together, and in this video, we'll see how to create a neural network that is trained on data of rock, paper, and scissors to detect and spot them. We'll start with the data. There's a data set here that has several hundred images of rock, paper, and scissors poses. We'll train a neural network with this data. So first of all, we have to download the zip files containing the data. The code to do that is here. One file has the training set, the other has a testing and validation set. In Python, you can unzip a file with the zip file library, and we unzip them to a temp directory like this. This creates folders with subfolders of each of our categories. When training in TensorFlow using an image data generator, it will automatically label the images based on the name of their parent directory, so we don't need to create labels for the images. It's a really nice shortcut. So I'll achieve that with this code. This creates an image data generator that generates images for the training from the directory that they were downloaded to. We can then set up something called a training generator, which, as its name suggests, creates training data from that. We can do exactly the same for the test set with this code. Later, when you see the model.fit, you'll see that we pass these in as the training and validation parameters. Now let's look at our neural network definition. This is very like what you saw in the last video, just with more layers. One reason is that the images are more complicated than the grayscale clothing you saw previously, and another is that they're bigger. You can see that our input is now 150 by 150. Our images are certainly bigger than they were before. And our output is a layer of 3 neurons. Well, why would that be? Because there are 3 classes, rock, paper, and scissors. Between these, the code is very similar to what you saw previously, just more of it. So we have 4 layers of convolutions, each with max pooling, before feeding into a dense layer. The dropout is a little trick to improve the efficiency of a neural network by throwing away some of the neurons. We'll compile the neural network as before with this code, and then we can fit the data with the model.fit call. Note that we don't have labels. That's because we're using the generator. It's inferring the labels from the parent directories of both the training and the validation datasets. When you run this, you'll probably get accuracy of about 100% on the training data quite quickly, with the validation data getting to about 87% accuracy. This is something called overfitting, which happens when the model gets really good at spotting what it has seen before, but it's not so great at generalizing. Think about it this way. So for example, if all your life, the only shoes you had ever seen were hiking boots, you probably wouldn't recognize high heels as shoes. You would be overfitting yourself. There are a number of methods to avoid this, and one of them is called image augmentation. And I've put the code for this into the notebook for you to try yourself to see how it helps avoid overfitting. Once your model is trained, You can then call model.predict to see how well it spots rock, paper, or scissors. This code will take an image, reformat it to 150 by 150, which the model is trained for, and it will then return a prediction. And here's a few examples that I ran so that you can see that it's actually predicting quite well. But the best thing to do is to try it for yourself. I've put a link to the notebook in the description below, and you can use this code to train a neural network to recognize rock, paper, and scissors images. That's it for this short series of videos. I hope it was useful for you to see the new programming paradigm that is machine learning, and through these examples of computer vision, how you can get yourself on the path to become an artificial intelligence engineer. If you have any questions, please leave them in the comments below, and don't forget to subscribe for more great content. Thank you. Hi everybody, I'm Lawrence Moroney from the TensorFlow team at Google. TensorFlow is all about community, and in the show TensorFlow Meets, we want to talk with you about what you're doing with TensorFlow.
TensorFlow.js. People will be able to author models in R.
That's right.
Using the Keras interface.
And then deploy them right into a browser. Yeah.
That's going to be huge.
Okay, we have a course on TensorFlow, and they were like, oh, we are too busy to teach it.
So you do it.
Yes, it's like, okay.
So if you have a project or research or anything that you'd like to talk about, just drop us a line and maybe you just might see yourself on the show. Hi everybody and welcome to TensorFlow Meets. I'm Lawrence Moroney and I'm delighted today to meet with Arun Subramanian from BHGE. And Arun, I know you've been doing lots of great stuff with probabilistic modeling. So for those of us who don't really understand probabilistic modeling, and could you tell us all about it?
First of all, good morning and thank you for having me here. And yeah, so probabilistic modeling and probabilistic theory generally is something that we've been using for several years now. And it's mostly for modeling systems that have a combination of very complex phenomena coupled with things that we can't measure precisely.
Okay.
Right? And to give you a simple example, if I were to ask you to predict where a stone would land if you throw it,
okay,
then any high school student would tell you that they can calculate it precisely based on how fast you threw it and at what angle you threw the stone at.
Okay.
Now, if I were to add a little bit of uncertainty to it, saying I don't know exactly at what angle you threw the stone at or what velocity you threw it at,
then maybe like wind shear
and stuff like that, then all of a sudden your predictions are no longer as precise. Right? Now, in a simple system like that, you can already see things starting to get complex. Imagine a complicated system in the real world. Things can get much more complex if you're trying to predict something precisely.
So you're working on a lot of complex systems like this. Could you share some examples?
Absolutely. So at BHGE and broader GE, we work on a lot of complex systems. For example, say designing gas turbines, or trying to predict what a very large-scale system like an offshore oil platform would do. Right? We're talking about hundreds, if not thousands, of variables interacting with each other, and most of the time you can predict or you can measure maybe a few hundreds, if not a few tens of those variables. So how do you predict behavior of such complex systems and still have actionable, meaningful outcomes from your models without knowing all the information about the system? That's really where we use probabilistic modeling.
I see. Okay, it sounds complex. So what is your approach to this? How do you get started?
Fantastic. So we get started with starting with the domain. So we understand the domain. So what I mean by domain is you might be a mechanical engineer, you might be an aerospace engineer, you might be a petrophysics engineer. You start with the understanding of the domain and marry that with traditional machine learning techniques. And that's been going on for several decades. That gives you a very good understanding of how to predict things precisely. And that's what we call known knowns.
Okay.
Right? So we can predict the known things.
Known knowns, right?
Exactly.
Core area you can
core area we can start from. And then we add a layer of probabilistics on top of it to say what are the things that we cannot measure precisely or measure at all.
Okay.
And that's where probabilistic modeling comes in. And that is what I would call known unknowns.
Okay.
Right? An example of that would be, say, if I'm trying to predict how a crack is going to propagate in a particular component, then I need to know what is the temperature of that particular component, for example. I measure it to within plus or minus 10 degrees, but I don't know what that variation in temperature is going to do to my crack propagating.
I see.
Right? So that's what I would call known unknowns.
Okay.
And once I know what are the unknowns that I'm not entirely sure about, I can go say, okay, this is what is the impact of that on something real. There is another level of complexity where things that I don't know, I don't know.
Got it.
right? And that's what I would call unknown unknowns.
Unknown unknowns, right?
So I know it's a mouthful, but an example of that would be, say, you have designed a system, you have put it out in the real world, you know some of the things that is going to affect that system,
right.
but you're not entirely sure of everything that's going to affect the system. And that is that other everything, that is what we would call unknown unknowns.
I see.
Right? And most of the time in real world, you can predict something up to, say, 90% or 95% of the time. The last 5% is what surprises us.
Okay.
And in systems which are safety critical, systems that are critical to keep up the infrastructure of the world, you can't necessarily have even a 1% chance of something going down, right? So for example, if power goes down, you need to be able to bring that back up very quickly, right? So those are the kinds of things where unknown unknowns come into play.
Okay, got it. So starting from the known knowns, then going to the known or knowable unknowns, and then there's the unknown
unknowns.
Yes. Unknown unknowns.
Exactly.
Right, okay, I see.
Yes.
So you've gone from like known knowns to knowable known unknowns, and then unknown
unknowns, right? And when you're trying to model systems that are highly complex and are extremely critical, you need to be able to predict things at all of those levels.
Right.
And even if you're not able to predict unknown unknowns, you need to know how much are you missing. Right? If an event like that happens, how would you respond to it? Right? That is really where unknown unknown comes.
Right. So now bringing this then into just developing these things, you use TensorFlow probability, right?
Yes, and we started with TensorFlow and then combined that with TensorFlow probability quite a bit.
So could you tell us a little bit about how you use all that?
Absolutely. So we started with TensorFlow for deep learning precisely, and when we got introduced to the TensorFlow probability team and Josh Dillon specifically, what we realized was they were bringing extremely deep research concepts from the probabilistics world into a production world that is not generally common. Right? And we were able to mix the deep learning community with the probabilistics community we had within our own teams.
Okay.
Right? So running a reasonably large data science team, what you have to do is mix teams that are not necessarily talking the same language.
Okay.
And TensorFlow allows us to do that very effectively, because now a deep learning expert who doesn't understand probabilistics well can talk to a probabilistics expert who doesn't understand deep learning in the same language.
Nice. So having that framework that they could work together was very powerful for me.
Absolutely. And it helped scale both our teams as well as our deployments very quickly.
Wow. So a lot of complex stuff that you've been working on. There must be somehow you got started to figure out this, and you know, how did you learn all this?
Absolutely. So I'm not a trained data scientist by training. So I got into data science by accident. So I'm an aerospace engineer who had to solve very complex problems by mixing these concepts together. So
it's a very common story, by the way.
Absolutely. So one of the things that helped me a lot was trying to mix practical aspects with the deeply theoretical aspects. So for practical aspects, a book that I really love is called Doing Bayesian Data Analysis.
Okay.
And that gives, at least it gave me, quite a bit of understanding of how these are applied in the real world. But at the same time, thinking about probability requires people to think about solving problems in a very, very fundamentally different way. Because we're good at being trained at saying, here are the bunch of inputs, how is that going to get me one outcome? But if the same inputs give you multiple outcomes, that's a very different paradigm to think about. So a set of books that helped me were from E.T. James, which is at a much more philosophical level of understanding probabilistics. I would urge folks to at least dabble in both the practical aspects as well as some bit of the philosophical aspects together. And if you look at the recent blogs from the TensorFlow team as well as the broader community in doing probabilistic deep learning, there's a lot of fantastic blogs out there that will help people get started as well.
And I'd say one thing, I know you've written a couple of blogs yourself, there's another one on the way where you've gone into a little bit more detail on what you've been talking about today.
Absolutely, and we walked through the three blogs because we wanted to walk through known knowns, known unknowns, and unknown unknowns and bring it all together.
So the one that you're still working on is the unknown unknowns?
Yes, and we are close to getting done with it, and it's getting published in the next month or so.
So all that's on blog.tensorflow.org, right?
Absolutely.
So thanks so much, Arun, and thanks everybody for watching this episode of TensorFlow Meets. If you have any questions for me or if you have any questions for Arun, just please leave them in the comments below. And also in the description for this video, we'll put links to everything that we spoke about today so you can check them out for yourself. Thanks, and see you next time.
Absolutely. Thank you, and thanks for having me.
So this is our mobile soundscape exhibit. Where do we go from here?
Sound waves are just vibrations in the air.
Signal. Such a vast and strange environment.
World of music.
As long as you have curiosity, you know there's life. When I look out to the ocean, I get that same feeling as I do when I look up into the stars. Hearing my parents playing guitar, that's probably my first memory. As a kid, I would run through the hallways and I would hear them practicing Mexican traditional music.
I went to a Catholic school, and the nun who had the Spanish class always took students down to San Blas, and that's where I met him. And I was 15, and he was 16 years old. Here we are at the plaza, La Plaza Principal. Qué bonito.
My mom didn't know Spanish and my father didn't know English, but they were able to communicate at least with music. And then I came along.
Danny, he was a busy one, very inquisitive when he was little, but his curiosity sometimes got him in trouble.
I was not a good student in high school. I didn't have any expectations. I wasn't looking at universities or anything like that. But after graduating, I thought, well, might as well go to community college. I started at Cabrillo and I didn't know what engineering was. As far as I was concerned, it was like a mechanic or something like that. But I started taking some math classes and it was different.
You know, there's lots of types of students. The majority of the students, they want the equation so that they could calculate a number. And then there are students who actually try to understand. That's Daniel.
I would always question things. I would always wonder like how light works, like why the waves are crashing the way they do. And when you start looking at physics and learning about these sound waves are just vibrations in the air and how we can represent those mathematically, my eyes opened to like a new world. And that's, I think, when it clicked that I knew I wanted to do engineering. Cabrillo College held a symposium where they connect students to research institutions. It was really interesting what Danelle and John were doing.
Daniel had a musical background. That's an important part of working on audio, is you have to have an understanding of the way sound works.
Light may reach a couple hundred meters in the ocean. Sound can travel thousands of miles. It's not a surprise that many life forms use sound for communicating. Blue whale is the largest animal to have ever lived on Earth, including bigger than any dinosaur.
They vibrate your body. They're incredible to hear.
The scientists at Mbari wanted to figure out a way to listen in and count how many blue whales there were.
So the process that we're using involves recording audio from the ocean 24 hours a day, 7 days a week, but that's a lot of information. Too much information for a human to try to look at and listen to.
We were able to turn those sounds to spectrograms, which are just images or mappings of what sound looks like, and fed those images into TensorFlow, this machine learning tool. Machine learning is getting the computer to be able to pick up patterns.
It allows us to take a mammoth pile of data and distill it into something meaningful so that we can do the analysis.
We want to understand how and when they're using all these calls, because that can help us understand their ecology.
It can answer a lot of questions about the way we are affecting the marine environment and how we can help conserve it.
Daniel was key in developing the software to automatically find calls for us.
Daniel started with the artistry of sound and found a meeting place with the science of sound.
That note is this note here.
Ultimately, both of those experiences, they're from the same source. That is sound energy varying in frequency through time. That's what makes music, and that is the signal we analyze.
The whales are communicating something to each other. I don't know what it is, but it made me think about how music is a way of communicating. Just like going back to my parents and how they met each other. They were doing the same thing. When I was a kid, I didn't think I was going to be a scientist or an engineer. And especially as I grew up, I didn't think I was capable of doing it. School was hard for me, and it still is hard for me. I don't know if I found my passion. I find myself so interested in a lot of different things. But knowing that I'll never stop learning makes me feel pretty lucky.
have a nice snack. We've got a great talk for you now. We have Joanna Karashkaira, who's a program manager in TensorFlow, and we have Nicole Pang, who is the product manager for growth and education in TensorFlow, and they're going to talk to you about how you can get involved in the community.
Thank you. Thank you so much, Jocelyn. First of all, welcome everybody. It's an absolute pleasure to be here with you today. As Jocelyn mentioned, I'm Joanna Karashkaira and I'm a program manager for TensorFlow at Google. I'm joined by my colleague Nicole Pang.
Yes, I'm Nicole. I'm a product manager for TensorFlow at Google.
And we're going to talk about the TensorFlow community and the many exciting ways by which you can get involved in the work that we do. So let me start by saying thank you. Thank you to the community for all the hard work that you've done. Since we've open sourced TensorFlow in 2015, we've received so many contributions and so much support from the community that really the project where it is today is due to you, to all your efforts and all your hard work. So thank you for that. Just on core TensorFlow alone, we've received more than 6,000 commits from over 2,000 contributors. This is so impressive, but not just only this. On Stack Overflow, we have received more than 50,000 questions, and we have onboarded more than 120 machine learning experts through our Google Developer Expert Program. And we have established 50 user groups all around the world. We've also had 25 guest posts on our TensorFlow blog, which is fantastic. And our community only continues to grow. Here's a snapshot where you can see that the number of commits from 4 years ago has been rapidly growing, and there's so much support and excitement from the community. We truly couldn't have gotten this far if it wasn't for you, for the contributors, for all the work that you do. So thank you so much for that.
And it's not just the contributions you see and the feedback we get from our community on GitHub and Stack Overflow, but of course, as you all know, TensorFlow has a global worldwide community. And we see a lot of love for TensorFlow also on other avenues. You probably have heard a lot about TF 2.0 today, yesterday, and you certainly will hear more about it tomorrow. But TF 2.0 is one instance where our global community responds really positively, and we see so many cases of that. And today we'll touch on these cases and, of course, how you can get involved in our community. So briefly, what we'll talk about today, we want to tell you how you can learn TensorFlow, how you can get started in your own journey of using TensorFlow, whether you're more in the beginning stages or you're a really advanced user of TensorFlow in your applications. Then we want to showcase to you our global community, really run through some really amazing use cases, really tell you what we've seen people do TensorFlow, or people use TensorFlow for, and hopefully that can be very inspirational for all of us, right, in the community. And of course, what you're here today, you want to know how to get involved with TensorFlow. So we'll walk you through not just the ways that you might first think of, which might be contributing code because TensorFlow is open source, but also a lot of community groups, a lot of special interest groups, and those, again, are all over the world, so both for everyone here in this room and, of course, everyone watching online. There's many, many resources, and we're so excited to share with you.
So we truly, as you could see, we truly have a vibrant global community that continues to grow because there's so much that you can do, so much that we can all contribute to TensorFlow. And let's have a look at where our community is based and what are they doing right now. So the TensorFlow user groups, they are a wonderful way in getting involved with TensorFlow. Either online or face-to-face, you can meet with other like-minded contributors and developers really to answer questions, to solve problems, challenges, and building those use cases on really how you can implement TensorFlow across different industries. So just an example, One of our user groups in Korea, that one is the biggest that we have in the world, and we have engaged more than 46,000 members. It is very impressive. And then China alone, it's the country with most user groups, and they have user groups across 15 different cities. It's really impressive how the community is growing so fast all over the world. And one of the key messages that Nicole and I would like you to retain from our presentation today is that if you don't have a user group where you're based or in your region, feel free to start one, share your experiences, connect with other like-minded developers, and start talking about TensorFlow. We are here to support you throughout this process and this journey, so feel free to reach out to us. We're very happy to guide you through the process. And like I mentioned, if you'd like to start your user group, here are some of the resources that you can have a look online if you are interested in starting your own group. We also are sharing our alias, so you can really get to know the team and how you can start creating your user group.
Yeah, so in the spirit of honoring our global community, we want to briefly touch on what the TensorFlow team has been doing worldwide. So like Joanna just said, right, we have so many user groups, and you really can see that they are global. And as you heard this morning in the keynote, the TensorFlow team was really excited and really lucky to be able to go to many cities and meet many of these users and meet many of the companies and meet many of the startups that are using TensorFlow in so many different cities in the world. And of course, we're so excited that you're here today, one of our stops on the TensorFlow Roadshow in Santa Clara today. And we're really, really excited to, again, be able to see the use cases, and we'd love to share briefly some of the use cases with you. So first off, when we look at Asia and Asia Pacific, there's a really big, vibrant community there. And as Joanna just said, right, a lot of people in Korea, a lot of people in India, a lot of people in China, they're all using TensorFlow with two amazing applications. So in China, for instance, TensorFlow is actually not just active on our applications, but also the community is really active on our official TensorFlow WeChat channel. And this WeChat channel showcases a lot of use cases of TF Lite on mobile. Like you can see this one example of a video platform called ITE with image segmentation on mobile devices. So again, they're doing really awesome work, and not just doing awesome work, but also sharing, right, with all of the community on the WeChat blog. And we're really, really glad that we're partnering with them and really glad to see these use cases come up.
Yes, and Nicole and I were really fortunate that we were able to join the roadshows and really connect with the local communities worldwide. So, for example, at the roadshow in Latin America, we connected with Alerce, which is a startup in Chile, and they are trying to detect supernovas and galaxies through the uses of agile processes and machine learning. And this was really cool, and they use conventional neural networks to classify astronomical objects contained in a stream of about 200,000 images per day. The work that they're doing is so impressive, and it's absolutely worth sharing with the rest of the community. Another example, in Europe, we connected with IM, which is a library of photos that uses TensorFlow for object classification. And their algorithm scores photos based on their aesthetic quality, but also on the relevance to your brand's visual identity. And then every photo is automatically tagged with keywords just to make sure that the entire library is searchable. It's really impressive. And then they use TensorFlow Lite on mobile to make it easier and also more accessible for the users to use IM. And then lastly, in Africa, we met with many exciting startups trying to find solutions for problems at a global scale that were relevant to the region. But we would like to highlight the great work of Tabua Health, who leverages the power of machine learning and spectral analysis to really turn any smartphone into a powerful, non-invasive screening tool for pneumonia, asthma, and other pulmonary diseases. So they use convolution neural network for modeling spectrograms that were generated from audio analysis through their smartphones, and then the saved models, they're frozen and converted into TensorFlow Lite, and the converted model is then deployed to a mobile device to perform interference. So these were some of the cases that we connected with during the roadshows, and it was brilliant to see all these very innovative ways that the community is using and building around TensorFlow. So these were just a few pictures of our roadshows where we truly engaged with the community, and it's palpable, it's very tangible, the excitement that we see not only from contributors but also from users of TensorFlow. It's fantastic to see how many of these startups and other companies are truly impacting and changing the world, and this is all you using TensorFlow. So thank you for that.
Yeah, so like we said in the beginning, we wanted to do a brief overview of some, just a very small sample of some of the awesome use cases of TensorFlow, but then really dig into what is available for you, right? So one of the first pillars that we'll talk about is education. Now, why is education important for us at TensorFlow, and also we hope it's important for you in the community? Well, TensorFlow is, of course, as you are very heartily knowing, it's open source. But also another aspect of that open source nature is that we want to make sure learning resources are available to everyone in the world. And we really value not making just the product better for learners. So, for instance, TF 2.0, it's easy debugging, and the usability of Keras is designed for that better experience for learners. So not just the product, but also the educational resources. So I'd love to go into some of them in a bit more detail. This morning, you heard about our launch of the new Learn ML Hub on TensorFlow.org. This is a great tool because we heard people's feedback that they would like more curated resources on TensorFlow.org. They would like more paths of learning from whatever level of machine learning and deep learning knowledge you have into more advanced applications of TensorFlow. So we heard you, and we now responded with this new resource of Learn ML. So it's not just a compilation of curated resources, but it's also guided paths, whether you're a beginner on TensorFlow, whether you're more advanced, and which resources and what tutorials, what guides might be helpful. And also, if you're interested in TF.js, right, TensorFlow on the browser, we have a very detailed, very nicely organized learning resource there. And we hope that you'll progress through it in whatever stage you are. If you're more advanced with TensorFlow, you might still be interested in our MOOCs, our massive online multi-part online courses. As you probably already know, TensorFlow has great partnerships with both Deep Learning AI Coursera and also Udacity. And these courses are available, again, to everyone, right? So to everyone in this room, to everyone watching online. And we really hope that you'll take the stuff that we have in these courses, which is both from TensorFlow instructors and also renowned academic instructors too. And we really want to give everyone ample opportunity to learn TensorFlow. And as you heard this morning, there is a new specialization on Coursera for TensorFlow data and deployment, and really taking modeling, not just understanding how to build a model, but also deploying it in applications. And again, right, as you move up these steps of knowing TensorFlow, we really hope you'll check out our new and updated tutorials and guides. This is thanks to the amazing work on our TensorFlow developer relations team. They're constantly writing new documentation, new guides, new tutorials. And with the launch of TF 2.0, all of these new guides are available for you to check out TF 2.0 and really understand how to use Keras and really understand all the use cases. There's some really amazing detailed documentation here, so we really hope you'll take advantage of these resources that we provide. And finally, let's jump into how to get involved with contributing. So now you know TensorFlow, right? You're advanced in TensorFlow, you've deployed it to applications, you want to be contributing to the open source community. Well, one of the first ways that everyone kind of thinks about is contributing code. And we're happy to describe to you a way that we use at on the TensorFlow team to consult widely with both design docs, API designs, and also some of them are driven by community members, is the request for comments, or RFCs. So this is actually the main way we communicate changes to our APIs and receive design feedback. So we'd love to invite everyone here to take a look and also join. This is one example of an RFC. This is an approved RFC TensorForest estimator. And I would like to take this opportunity to, of course, thank everyone who has authored or reviewed an RFC. And we actually have 45 RFCs accepted to date, which is really an incredible number. And they have ranged from TFX to TF Lite, TFJS. And each RFC expands the usage of TensorFlow, right? It really helps the community, and it also is a great boon to the TensorFlow team. So we'd love to have you also propose designs. You can check out more about RFCs, and of course, talk to any of us about this also.
Sure. And also for bigger projects in which we have to work as a team, we've created the Special Interest Groups, the SIGs, which is a program that organizes the contributors into more focused streams of work. Everything started with the SIG build, and nowadays we have 11 SIGs, which is really impressive how the SIGs have also grown so much over the past few years. So all the contributors, you are very welcome to join the SIGs and really join the SIG that resonates more with the parts that you either enjoy or care the most about TensorFlow. Just an overview of our contributor ecosystem. As you can see highlighted in the darker orange, we have the SIG add-ons, the SIG build, I/O, networking, GVM, and micro, and Rust, which are community-led open source SIGs, and the others, which include Keras, Swift, MLAR, and TensorBoard. They are Google-led with an open design philosophy. So if you see a SIG that resonates with the work that you do, or if you care about the topic and would love to learn more, the SIGs have monthly or weekly calls, and you're very welcome to join as well. I would like to give you an overview of our open source community-led SIGs, and just briefly going through some of the key aspects of the SIGs. The SIG add-ons, it maintains important additions to TensorFlow and adopted some of the parts of TF-Contrib. This SIG is led by Sean Morgan and Tzu Wei Sang. The SIG build, we have one of the leads actually here with us today. Actually focus on building and package TensorFlow for different distribution environments, and is led by Jason Zaman and Austin Anderson. The SIG I/O, it focuses on supporting extra file systems and file formats for TensorFlow, and is an initiative led by Yong Tang and Anton Dmitriev. And as we all know, high-performance computing resources, they require lightning-fast interconnectivity, and the SIG networking focuses exactly on that, on building more network support for TensorFlow. This is an initiative led by Bayron Wee and Jerome Bedorf. And finally, the SIG Keras. We've added this SIG, the SIG Keras, to continue to improve the Keras API for TensorFlow. So those are some of the SIGs that you can join, but we also have, like I mentioned before, the other SIGs that are also Google-led, but with an open philosophy. You're very welcome to have a look at the SIG playbook at the tensorflow.org, where you'll find more information on how you can join the SIGs and the ongoing projects that they have right now. If you see that none of the SIGs that currently exist are a fit for you or for your work, if we see there's enough evidence and enough support from the community, you can also start and establish your own SIG. And if you head to GitHub, on our community resources. That's where you'll see how the SIGs operate, what are the resources and tools that are available for you to help you throughout this process. But also we have more information not only about the SIGs, but also our RFC process and our code of conduct. So I strongly encourage you to have a look after TensorFlow World. And today, I'm also extremely excited to announce that we've achieved another milestone with TensorFlow and our community. We have hosted the first Contributor Summit just on Monday and Tuesday for almost 100 participants. And it was a great way to really connect with the SIG leads and with the broader community, and to really understand how together we can move forward with the open source project, what are the strategic developments that we can implement in TensorFlow, what are the documentation needs, project management, community management. It was a great conversation that we had over 2 days. So I strongly encourage you to, if you didn't have the chance to participate this time, to have a look at the online resources that will be available afterwards. It was a great opportunity to connect with you all.
Awesome. So some of the SIGs, like Joanna mentioned, are led by what we call machine learning Google developer experts. And so I'd love to show you a little bit about what that means. So our ML GDEs are a global network of ML experts that Google works closely with, and we provide latest information to them. They give us feedback. It's like an awesome relationship. So we're really excited. We have 126 ML GDEs to date worldwide. And this year alone, these MLGDs have given over 400 talks worldwide, hosted over 250 workshops worldwide, and also written over 200 articles. And this is incredible because we actually know that these talks, workshops, and articles have reached a worldwide audience of 435,000 developers. So as you can imagine, TensorFlow, our team, we want to reach as many people as we can, but with the MLGDEs, we really just amplify that reach of impact that we can have in the world of teaching TensorFlow and really, really helping people around the world understand about TensorFlow. So we're really excited. We would love to tell you if you want to become a GDE. This is also a link to become a GDE. We also have a lot of links for connecting with other GDEs. And today, we would also love to welcome one of our GDEs up to the stage to give a brief chat with us. So please welcome Jason Zaman.
Hi, everyone. So I'm one of the community leads for SIG Build. We have a few members of Build around here. Thank you. And so Build's being the first SIG, it was formed 2 years ago, quite a while. So I've really seen the community grow a lot in that time. It's really nice to see, like, now we have so many SIGs doing all kinds of things. And it really started, like, I started Build because I saw problems when I was trying to use it, and I wanted to make it better. And, like, really the group has grown and done a lot of great things. I want to encourage everyone to get involved. You can join a SIG that already exists. You can find a thing you want to do, work on it, and find more people that are also interested, maybe start a new SIG. A lot of people around to help. These people are wonderful. And I'm also one of the MLGEs, so it's a great program. It's really nice to hear like from other MLGEs. They work on all kinds of cutting edge stuff, all kinds of different fields, stuff that I don't even know or hear about other than them, so really good, yeah, thank you.
Thank you. Thank you so much, Jason. And we're really lucky to have another MLGD in the audience, and please welcome Margaret Maynard-Reed.
Hello, everyone. I'm a machine learning GDE. I'm also the lead organizer of Google Developer Group Seattle and another group called the Seattle Data Analytics and Machine Learning. I became a machine learning GDE in 2018, and here's why I love being part of this amazing community. I get to collaborate with other machine learning GDEs and Googlers on various projects. For example, I get to write some tutorials that you will find on TensorFlow.org and some of the blog posts that were published on the TensorFlow Medium publication. And earlier this year, I helped organizing the Global TensorFlow Dog Spring with Paige, Sergey, and other machine learning GDEs and GDG organizers. It was an incredible experience to work on such a high-impact project which was even mentioned in the keynote this morning. So I speak about TensorFlow and on-device machine learning at various conferences, and I really enjoyed the opportunity to be able to preview Google products and provide feedback. So many of the machine learning GDEs are well-known educators, speakers, or O'Reilly book authors. It's really great to be able to learn from my fellow GDEs and Googlers. And once a year, we will gather together for our global GDE summit around the world, the GDEs from around the world. And we just had the summit a few days ago before TensorFlow World. So to become a GDE, machine learning GDE in particular, you need to be able to demonstrate both your community contribution as well as knowledge in machine learning. We would love to see more of you join our growing machine learning GDE community. Thank you.
Thank you so much, Margaret. This is fantastic. I'm sure I can speak for both of us, but I'm always so impressed by the fantastic and amazing work that our GDEs do. It's really nice to see how engaged the community is. However, there's many other ways by which you can contribute to TensorFlow. It doesn't have to be only through code. So if you are a coder, but you would like to learn or develop a new skill set, there's many other ways that you can get involved with TensorFlow. When it comes down to known code contributions, there are three main pillars that we normally encourage our contributors to join. Primarily on user support, which includes creating documentation, translation, training courses that really will help other contributors getting involved and onboarded within the project. In terms of community management, really through organizing events, meetups, and all the initiatives that get the community together and energized and excited about machine learning and TensorFlow. And then on the project management side, creating the tools and resources that will help advance our projects, but also keep the health and the sustainability of the initiatives that we do. Sometimes we work really on cross-functional teams on really building the use cases on how TensorFlow can be implemented in different ways. And then finally, I would like to highlight that we have a code of conduct in our TensorFlow community. So we apply this code of conduct to all the events and the initiatives that we do. And we would like to remind you that this is a safe space where you can truly be yourself as a contributor, and we welcome that diversity of ideas, opinions, and suggestions. So if you see that something is just not right, please feel free that you know that you can escalate those problems to also the community stewards. We're here for you. We are here to make sure that you feel engaged, that you feel heard, and that you feel that you belong to a community of excited machine learning experts, contributors, and users.
So we want to wrap up our conversation by revisiting the links and the different resources that we've given you in this talk. So again, after TF World, you're wondering how do we keep up with the latest news and the latest deep dives from TensorFlow? Well, these are the ways you can keep up with us. So of course, Twitter is very great for a lot of the latest announcements and updates from the TensorFlow team. Our blog is actually an amazing resource of a lot of deep dives, a lot of understanding specific use cases. You might be wondering how to use TensorFlow in a certain application, and the blog may actually have a guest post or a post from the TensorFlow team that can address that. So we really suggest you check out the blog. And YouTube, I think many of you probably already have seen the TensorFlow YouTube channel, but in case you haven't, it's actually a really awesome resource to learn TensorFlow. So we have a lot of videos that highlight, again, like our new announcements, right? Like how to use TensorFlow, how to use specific things like TF-Keras. We have videos about that. And one of our most popular videos is actually done by someone on our developer relations team, Lawrence, and it's the ML Zero to Hero video. And it's a great resource. So again, like if you haven't seen these social resources, we really highly suggest you follow, and that's how you'll get the updates from TensorFlow outside of TF World. And finally, these are some of the links that we showed earlier. We really want to emphasize again, TensorFlow, the community, would not be possible without everyone in the room, without everyone in our community globally. So we really encourage you, if you aren't in a SIG or in a user group, if you're interested, you can check out everything on our TensorFlow.org community links. You can check out the educational resources I mentioned also at the beginning. And we are so excited that so many of you are among us in the group today. So we'd really love to welcome you to also share with your fellow conference attendees what it's like being in a SIG, what it's like leading a SIG or being an MLGD too. So with that,
we have our call to action to you, which is join the user groups, join the SIGs, be part of the community, contribute code to TensorFlow, documentation, translations, educational resources, events. There's so many different and exciting ways to contribute to TensorFlow. So thank you for being with us today. It's been really a pleasure speaking to you about the many ways that you can get involved with the community, and I hope that we can continue these conversations. What do you think, Nicole?
Yeah, that sounds perfect. Let us know if you have any questions, of course, and we're so happy that you want to be a part of the TensorFlow community. Thank you.
Thank you.
Hey everybody, welcome to the ML and AI Sandbox here at I/O 2019. So in the keynote, we saw some amazing stuff that you can accomplish with on-device ML. And I'm here with TensorFlow Lite, showing developers how they can build that same stuff themselves. So we've got everything through from object detection to image classification and voice recognition. And we're showing people how they can deploy that down to devices that are really tiny and run for weeks on a single battery. So to really show you what's possible with TensorFlow Lite on device, we built this amazing experience called Dance-like.
Okay, behind me is Dance-like. It's a super fun application using TensorFlow Lite, which is TensorFlow's mobile and embedded systems framework for running machine learning. It basically teaches people how to dance, and so it does this by running pose segmentation on the GPU. We have a bunch of GPU-related ops that we just released for TensorFlow Lite, so you should check those out. It enables you to run super fast models. We're running 2 in real time and giving the user a heap of feedback which helps them dance better. So to go and build really interesting applications on mobile phones, embedded systems, and executing this all on device, you can go to tensorflow.org/lite. There's heaps of sample code, there's lots of documentation and tutorials, and you can go and build an amazing application like Dance-like and release it to the world.
What we're looking at here is a model called PoseNet. PoseNet is a model that's trained on images of human beings and is trained to predict their skeletal pose. This model here is actually running entirely in the browser with a library called TensorFlow.js. TensorFlow.js is a machine learning library for JavaScript that can run entirely in the browser and use your GPU through WebGL. Now, TensorFlow.js also runs in Node.js using the entire TensorFlow C++ binary and all of its hardware acceleration stories behind it. Piano Genie is a model that runs in TensorFlow.js entirely in the browser as well that generates MIDI notes as part of a piano performance. Now, this model is interesting because it brings a human in the loop and lets the human condition where the model is actually going to go. TensorFlow.js is open source and is available online on tensorflow.org/js, as are multiple more examples and demos of how to use it. Head over there today to start building machine learning for the browser.
So we take an old cell phone, we put it up in the trees, and it listens to all the sounds of the forest to pick up the sound of anything that indicates there's some danger.
Já tem um caminhão aqui para carregar as madeiras que estão derrubadas, né? E aqui está a nossa floresta sendo desmatada pelo madeireiro. Tá? No ponto de vista de vocês estão achando bom o que está acontecendo na nossa floresta? Não. Por quê?
Porque está acabando as frutas, não tem mais árvores.
E você, Isaac? O que você acha?
Estão cortando madeira, aí não chove muito aqui.
Quando eu era pequeno, tinha muita fartura. Agora já está para todo mundo ver, né? Os estragos da floresta que está feita. Já é uma floresta totalmente furada, né?
A floresta, para nós, é tudo na vida. A invasão traz a devastação, acaba com tudo que tem na floresta, acaba a floresta em si. A gente monitorava fiscalizando a pés, esbarrando com os invasores, aí nós tínhamos vários problemas, vários conflitos. Morreu parente da gente, morto pelos pistoleiros ainda. E isso começou a marcar na nossa vida. No correr do tempo a gente foi buscando o mecanismo. O entorno aqui, eu acho que nós temos 30% ainda que ainda falta nós dominar dessa parte da área.
Would it be easier for us to do that by focusing on the perimeter?
O Toffoli, quando ele veio a primeira vez, veio ouvir a gente qual era a nossa necessidade e a gente ficou se perguntando, será que de fato ele vai conseguir fazer alguma coisa porque nós estamos querendo?
The Tempe people are an amazing example of a people that's trying to preserve their forest. They are well organized, they're well educated, are not afraid to use different tools, new technologies. They're looking for collaboration, they're not looking for help. People on the ground in these places, they're the solution. They're the ones who can actually really fight off deforestation, but technology can play a really big part in helping them do it more safely and more effectively.
O Toffoli está trabalhando muito num sistema de monitoramento para que a gente possa ter esse controle e passar para as autoridades a necessidade que nós temos, ou melhor dizer, facilitar as nossas denúncias.
And all you have to do is just be kind of precise with this one here, because the antenna is both fragile and sensitive. You want to put the microphone on there. Yeah, that's good. Old cell phones are available to almost anybody all the time. And these aren't trash. These are actually really, really powerful little computers. They can connect to the networks that are there. They can record the sound. They can do all this great processing. The hard parts, of course, have to do with making it possible to power them and making sure they can actually pick up sounds from a great distance. But all these are things that you can do with pretty standard electronics.
Cool. Pronto? Pronto. Here we are.
Catu.
Catu.
The Tembe themselves have at most 30 rangers, 30 warriors that are able to sort of patrol the area and take responsibility for protecting it. And yet we're talking about an area that's huge. And that's where this ability for us to be able to listen to parts of the forest 24/7, it really increases the efficiency and the safety of the entire operation for them. And that's a really critical tool given what they're up against. No person could be able to detect the chainsaw at a kilometer away, given how loud and how noisy and how complex the sound really is. So we're actually using an open source machine learning tool, TensorFlow, that's able to detect a logging truck, the sounds of birds or animals or chainsaws in the forest. It's amazing what they can actually find that we cannot even hear. And it can send a real-time alert to the rangers, to the guards, to the chiefs, so they can decide how to respond.
O sistema vai acusar onde é que está tendo problema. Aí não tem aquele tempo de correr para estar fiscalizando meses e meses, como a gente fazia antes. Quer dizer, nós ter mais tempo para a nossa cultura, ter mais tempo para a nossa família, ter mais tempo para sobreviver. Um povo sem cultura não é ninguém. Então, nosso sonho é de ter nossa floresta em pé, preservada, que nós não deixe para os nossos filhos, nossos netos, os problemas que nós estamos tendo hoje. Nosso sonho é viver em paz, como antigamente, como nós vivíamos.
here we are, 5 o'clock, the last session of the day. How's your energy? Good? This is the talk you've all been waiting for. Zach Stone is the product manager for Cloud TPUs, and he's got an awesome talk for you about research projects in the cloud. Here you are, Zach.
Thank you very much. I'm delighted to be here today to talk to you about some of the fantastic TensorFlow Research Cloud projects that we've seen around the world, and to invite you to start your own, whether you're here in the room, watching on the live stream, or online watching this afterwards. Any of you are welcome to get involved with TFRC. Just very briefly, since I'm sure you've heard this all today, the context is this massive improvement in computational capabilities driven by deep learning. So deep learning, and specifically these deep neural networks, are enabling many new applications that are exciting in all sorts of ways, touching all kinds of different data, ranging from images to speech to text, even full scenes. And the challenge that many of you are probably grappling with is that these new capabilities come with profound increases in compute requirements. A while back, OpenAI did a study where they measured the total amount of compute required to train some of these famous machine learning models over the past several years. And the important thing to notice about this plot is that it's actually a log scale on the compute axis. So there are tremendous increases in the total amount of compute required to train these state-of-the-art deep learning models over time. And there's this consistent trend up and to the right that these new capabilities are being unlocked by the additional compute power, as well as lots of hard work by many researchers all around the world in this open community. So, unfortunately, these tremendous demands for compute to meet these new opportunities opened up by deep learning are coming to us just as Moore's law is ending. We've benefited for decades upon decades in consistent increases in single-threaded CPU performance, but all of a sudden now we're down to maybe 3% per year. Who knows? There could always be a breakthrough, but we're not expecting extraordinary year-upon-year gains from single-threaded performance as we've enjoyed in the past. So in response to that, we believe that specialized hardware for machine learning is the path forward for major performance wins, cost savings, and new breakthroughs across all these research domains that I mentioned earlier. Now, at Google, we've developed a family of special-purpose machine learning accelerators called Cloud TPUs. And we're on our third generation now, and 2 of these generations are available in the cloud, the second and the third generation. Just to give you a brief overview of the hardware that I'm going to be talking about for the rest of this session, we have these individual devices here, Cloud TPU v2 and v3. And as you can see, we've made tremendous progress generation over generation, 180 teraflops to 420 teraflops. We've also increased the memory from 64 gigabytes of high bandwidth memory to 128, which matters a lot if you care about these cutting-edge natural language processing models like BERT or XLNet or GPT-2. But the most important thing about Cloud TPUs isn't just these individual devices, which are the boards that you see here with the 4 TPU chips connected to a CPU host that's not shown. It's the fact that these devices are designed to be connected together into multi-rack machine learning supercomputers that let you scale much further and program the whole supercomputer across these many racks as if it were a single machine. Now, on the top here, you can see the Cloud TPU v2 pod spanning 4 racks. The TPUs are in those 2 center columns, and the CPUs are on the outside. That machine got us to 11.5 petaflops, which you can also subdivide every which way as you wish. And the TPU chips in particular are connected by this 2D toroidal mesh network that enables ultra-fast communication. It's much faster than standard data center networking. That's a big factor in performance, especially if you care about things like model parallelism or spatial partitioning. But now, with the Cloud TPU v3 pod, which is actually liquid-cooled, the picture wasn't big enough to hold all the racks. It spans 8 racks out to the side, and it gets you up over 100 petaflops if you're using the entire machine simultaneously. On a raw op-by-op basis, that's competitive with the largest supercomputers in the world, although these TPU supercomputers use lower precision, which is appropriate for deep learning. Now, I've mentioned performance. I just wanted to quantify that briefly. In the most recent MLPerf training version 0.6 competition, cloud GPUs were able to outperform on-premise infrastructure. What you can see here is the TPU results in blue compared with the largest on-premise cluster results that were submitted to the MLPerf competition. And in 3 of the 5 categories that we entered, the cloud TPUs delivered the best top-line results, including 84% increases over the next entry in machine translation, which is based on transformer, and object detection, which was an SSD architecture. Now, obviously, these numbers are evolving all the time. There's tremendous investment and progress in the field, but I just wanted to assure you that these TPUs can really deliver when it comes to high performance at scale. But today, we're here to talk about research and expanding access to this tremendous computing power to enable researchers all over the world to benefit from it and explore the machine learning frontier, make their own contributions to expand it. In order to increase access to cutting-edge machine learning compute, we're thrilled to have been able to create the TensorFlow Research Cloud in order to accelerate open machine learning research and hopefully to drive this feedback cycle where more people than ever before have access to state-of-the-art tools. They have new breakthroughs, they publish papers and blog posts and open source code and give talks and share their results with others. That helps even more people gain access to the frontier and benefit from it. So we're trying to drive this positive feedback loop. And so as part of that, we've actually made well over 1,000 of these cloud TPU devices available for free to support this open machine learning research. If you're interested in learning more right now, you can go to g.co/TFRC. I'll also have more information at the end of the talk. This pool of compute, the TFRC cluster, involves not just the original TPU v2 devices that we included, but we've recently added some of the v3 devices of the latest generation if you're really pushing the limits, and there's the potential for cloud TPU pod access. If you've gone as far as you can with these individual devices, please email us, let us know, and we'll do our best to get you some access to TPU pods. The underlying motivation of all this is a simple observation, which is that talent is equally distributed throughout the world, but opportunity is not. And we're trying to change that balance to make more opportunities available to talented people all around the world, wherever they might be. So we've had tremendous interest in the TFRC program so far. More than 26,000 people have contacted us interested in TFRC, and we're thrilled that we've already been able to onboard more than 1,250 researchers, and we're adding more researchers all the time. So if you haven't heard from us yet, please ping us again. We really want to support you with TFRC. The feedback loop is just starting to turn, but already I'm happy to announce that more than 30 papers in the academic community have been enabled by TFRC, and many of these researchers tell us that without the TFRC compute, they couldn't possibly have afforded to carry out this research. So I feel like in a small way, we've sort of grabbed the lever of progress here and we've tipped it slightly upwards, so the whole field is moving just a little bit faster, and we really thank you all for being part of that. I'm most excited, though, to share some of the stories directly of the individual researchers and the projects that they've been carrying out on the TFRC Cloud TPUs. And now, these researchers, they come from all over the world. I only have time to highlight 4 projects today, but the fantastic thing is that 3 of these researchers have been able to come and travel here to be with us in person. So you'll get to hear about their projects in their own words. We'll start with Victor Dibia here in the upper left. Welcome, Victor. Come on up.
Hi. Hello, everyone. Really excited to be here. My name is Victor Dibia. I'm originally from Nigeria, and currently I'm a research engineer with Cloudera FastForward Labs in Brooklyn, New York. And so about a year ago, I got really fascinated about this whole area of, the intersection of art and AI. And given my background and my interest in human-computer interaction and applied artificial intelligence, it was something I really wanted to do. Right about that time, I got the opportunity to have access to TFRC, and today I'm going to talk to you about, the results of those experiments and some of the research results I kind of had working on this. And so why did I work in this project? As a little kid growing up in eastern Nigeria, my extended family and I will travel to our village once a year, And one of the interesting and really, captivating parts of those trips was something called the Eastern Masquerade Dances of Africa. And so what would happen is that there's these dancers with these complex, elaborate masks. And, right as a kid, I was really fascinated. And so this project was a way to kind of bridge my interest in technology art and as a research engineer to also express my identity through a project like this. In addition to this, there's this growing area of AI-inspired art or AI-generated art. But one thing you'd notice in that space is that most of the data sets that are used for this sort of explorations are mainly classical European art, Rembrandt, Picasso. And so a project like this is a way to kind of diversify the conversations in that area. And then finally, for researchers working in the generative model domain, one of the goals here is to also contribute a more complex data set compared to things like faces or retail images. And it can be a really interesting way to benchmark some of the new generative models that are being researched today. So what did I do? And so, like all of us know, the best results, or most of the effort from machine learning projects comes from the data collection phase. So I started out collecting images. I curated about 20,000 images, and then we sold that down to about 9,300 high-quality images. And at this point, I was ready to train my model. And so the beautiful thing is that the TensorFlow team had made available a couple of reference models. And so I started my experiment using an implementation using disagans implemented with TensorFlow TPU estimators. And so the picture you see on the right is just a visualization of the training process for a deep convolutional GAN. And so it starts out from random noise. And as training progresses, it learns to generate images that are really similar to the input data distribution. And so starting out with the reference implementations, there are two interesting things that I did. The first was to modify the configuration of the network, modify the encoder and decoder parameters to let this thing generate larger images, 64px, 128px, and then write a custom data input pipeline that lets me feed my data set into the model and get it trained. And so the thing you should watch out for is to ensure that your data input pipeline kind of matches what the reference model implementation is expecting. It took me about 60 experiments to really track down that error and fix it, so it did take a couple of days to fix that. And so in all, I ran about 200 experiments, and at this point, this is where TensorFlow Research Cloud really makes a difference. And so something like this would take a couple of weeks to get done, but I was able to run most of these experiments once all bugs were fixed within about 1 or 2 days. And so at this point, all of the images you see here, they look like masks, but the interesting thing is that none of them are real, none of them exist in the real world. And these are all interesting artistic interpretations of what an African mask could look like. And so what could I do next? And so I started to think, at this point, I have a model that does pretty well, but the question is, are the images novel? Are they actually new stuff? Or has the model just memorized some of my input data set and kind of regurgitated that? And so to answer those questions, I took a deep semantic search approach where I used a pre-trained model of VG16 to extract features from all of my data sets and all of my generated images. And I built this interface that allows some sort of algorithmic art inspection, where for each generated image, I can find the top 20 images in the data set that are actually similar to that image. So this is one way to actually inspect the results from a model like this. So going forward, the best and the stable model I was able to train could only generate 64px images, but can we do better? So it turns out that you could use super resolution GANs, and this is just one of my favorite results, where we have a super resolution GAN from the Topaz Gigapixel AI model. And the other here's another interesting result. And what you probably can't see very clearly here is that there's detail in this super resolved image that really just does not exist in the low resolution image. And so it's like a two-step interpretation using neural networks. And so if you're a researcher or you're an artist or a software engineer interested in this sort of work.
Yeah, there we go.
Yeah, please go ahead. All of the code I use for this, it's all available online, and there's a blog post that goes around with it. So thank you.
Thank you very much. Thanks very much, Victor. Next up, we have Wisdom. Come on up, Wisdom. Thank you. There you go.
Hi, everyone. I'm glad to be here. I'm Wisdom. I'm from Togo. I grew up there, and I'm currently a visiting researcher at MINA in Montreal, doing research in grammar language learning, natural language understanding, under the supervision of Yoshua Benju. So since the past year, I've been interested in medical report generation. And so basically, when you go to see a radiologist, you get your chest x-ray taken, and the radiologist tries in a fraction of seconds to interpret the x-ray and produce a radiology report that has mostly these sections, findings and impression. And findings are written observations on different regions of the chest, so basically saying if there's an abnormality of that region or not. And the impression section highlights the key clinical findings. So because this happens very fast and radiologists can commit mistakes, the AI community has been thinking of ways to augment radiologists with AI capacity to provide a third eye. And we have disease classifiers that work very well for that. The problem with disease classification is you are going from the image to the labels. So where's the step where we generate a radiology report? And this is what I've been interested in. And you might like to try something like image captioning to generate the report, basically condition language model on the input image, and maximize the log likelihood. But this doesn't work very well on medical reports because there is nothing in this formulation that ensures clinical accuracy of the report that are being generated. And this is a big problem. And this is what I've been interested to solve, and I found inspiration in grammar language learning. So in this setting, you have a model that receives natural language instructions to achieve a task. And to correctly achieve the task, the model needs good natural language instructions. And I said, whoa, we can do the same thing for medical report generation. So rather than, or on top of maximizing the log likelihood, which we do in image captioning, we can also reward the language model based on how well its output was useful for a medical task, let's say classification, for instance. So here, the classifier takes the radiology report as input. And we can also add the image for superior accuracy. But what is interesting here is in the backward pass, we are updating the language model parameters based on how well the output was useful for classification. And that's a good starting point for accuracy because we are forcing the language models to output things that have enough and pertinent medical clues to infer accurate diagnosis. And I trained this model on Mimic CXR dataset, which is the largest to date with both chest radiographs and free text radiology reports. And to train this, I needed extensive amount of compute. And I started this project as a master's student in India, and I was training on my laptop. I know, yeah, that was painful. So I applied to TFRC to have access to TPUs, and I got it. So I had suddenly many TPUs for free to do a lot of experiment at the same time. And that was useful to iterate fast in my research because I needed to reproduce the baselines as well as optimize my proposed approach. So my estimated TFRC usage was 8,000 plus hours. I used V2 devices, V3 devices, and also got to try the V2 pods devices. So I couldn't leave you without some results of the model. So this is a case of hiatal hernia. And if you talk to radiologists, they will tell you the main evidence for hiatal hernia is the retrocardiac opacity you can observe with that green arrow. And in the red box, you see the ground truth radiology report of this X-ray. So the green one is a baseline I reproduced and optimized the best I could, but you can see that the model completely misses out on the key findings. And that's a consequence of turning on the log likelihood because you are optimizing, maximizing the confidence of the model, it will avoid taking risk and will tell you 80% of the time that your X-ray is fine. So the blue box is my approach. And you can see that by forcing the language model to output things that are useful for classification, the model finds the right words to use to justify this case of hiatal hernia. So I'm very excited to have presented this work very recently at Stanford. at the frontier of AI-assisted care scientific symposium organized by FFLE and Stanford School of Medicine. And I'm excited for what's next with this project, and I'm thankful to the TFRC team for providing the resources that we use for this work. Thanks for having me.
Thank you very much, Wisdom. That's great. Next up, we have Jade. Here you are, Jade.
Hi everyone, I'm Jade Abbott. I'm from South Africa, so I've come a very long way to be here. I work for a company called Retro Rabbit, but I'm not actually here today to talk about what I do at work, which these days is a lot of BERT stuff. I'm here to talk about my side project, and I've kind of picked up research as a hobby. And what we're trying to do is work on there's a lot of African languages, which I'll speak a little bit later, and very little research. So what we did here is we kind of developed, at least for 5 of the Southern African languages, developed kind of baseline models. This work feeds into a kind of greater project, which we call Masakana. Masakana means we build together in isiZulu. And in this project, we're trying to kind of change the kind of NLP footprint on the continent. So, the problem. We have over 2,000 languages, which is quite insane. Many of these languages are exceptionally complex, some of the most complex in the world. And in contrast, we've got almost no data. If we do have data, we have to dig to find it. And what's even worse is that there's absolutely no research. So if you're a beginner NLP practitioner, currently learning about machine translation or NLP on the continent, and you do a search and you're trying to find something in your language, there's nothing, right? You can look in some obscure journals and you'll find like maybe some old linguistic publications, and that's kind of the extent of it. And this makes it hard if you're trying to build on models and you're trying to kind of spur this research. If you look at this graph, you can see what is the normalized paper count by country at the 2018 NLP conferences. And if the more orange it is, the more papers we've got. And you see this glaringly empty continent in the middle there. And even at widening NLP workshop at ACL, they still, the graph still doesn't look that much different, and that's meant to be inclusive of more people from around the world. So what did we do? We said, I like to say we took some existing data that we scrounged around and found, and we took the state-of-the-art model and we smashed them together. They'd never seen each other, this model and this data. What we did was we then decided to actually try to optimize the NMT kind of algorithms, just parameter-wise, just to work better on these low-resourced African languages. And our goal for this is to spur that additional research, because right now there's nothing. Provide these baselines. And this is where TFRC came in. Like I said, this is my side project, so instead of having lots of money to do this, I tried, and I was renting GPUs from a cloud provider, and they were costing me an arm and a leg. I reached out to TFRC, and they were super, super happy to lend us these TPUs. We basically used the tensor-to-tensor framework to train up these models. We used government data, parallel corpuses that we managed to find there. One of the things that we found that was actually simultaneously kind of presented at ACL on a different language pair, English to German, we found that optimizing this byte pair encoding tokenization allows, like, these very complex low-resource languages, allows us to kind of handle their agglutinative nature. Now, agglutination is when we take those languages which you build up new words by just kind of adding on more words, or like switching little bits completely changes the meaning. That's agglutination, and then optimizing this parameter can make really significant differences in the BLUE score. And what was also great is we needed to submit something, I think, in 2 or 3 weeks to a workshop. And instead of taking days to run these experiments, it would take a couple of hours to actually build these models. So thank you to TFRC for that. So just come sort of results overview of the 5 languages we had. You can see in Northern Sotho, Setswana, and Setsonga, we have almost, and particularly in the case of Setswana, almost double the BLUE score. Bigger is better with BLUE. Where in Afrikaans is actually a European-based language. It's based on Dutch. That's preferred the older statistical machine translation architecture, and work better there. That unfortunately runs on CPU and actually takes a lot longer than than we wanted it to. And isiZulu is kind of an anomaly. It's a complex language, but we had very few sentences, and the sentences are also very messy. So in this case, the statistical translation performed slightly better. If you look at this little visualization, it's English to Afrikaans, but what's really cool is you can see the attention actually captured some of the language structures. Here we've got a particular instance where cannot in Afrikaans becomes 2 words, ni, and at the end you have to say ni again. It's called a double negative. I'm not sure why. And you can kind of see that it actually sort of does that less so on this screen for some reason. There's a yellow there. You can pick up cannot matches to can, ni, and ni. And those are the words, which is quite cool. Here we've got one of our sample translations. So we've got a source sentence, we've got the reference translation, and the transformer translation. Obviously, very few of you are likely to speak Setswana in the audience. So we've got a native speaker to actually translate it back to English, what the transformer generated. And you can see they're talking about sunflower fields and lands and flowering periods, and they picked up blossoming period. So you can see it's actually done really, really, really well despite having so little data. So yeah, so this is my call to action. I work on a project, as I said, co-lead of a project called masakana.io. You can go check it out. And our idea is to basically change this map. So this map is what our current representation of researchers across the African continent are currently working on languages from. And like I said, the idea is to spur research. So if you know a language from Africa, or even if you don't, and you're willing to contribute time or resources or advice to we've got a lot of very junior teams who don't have supervisors or people who work in machine translation, or even if you'd like to come do maybe a webinar, drop us a message. And yeah, thank you very much to TFRC for hosting us. And yeah, look forward to what else we can actually build.
Thanks so much, Jade. Thank you. Let me get the clicker too. Jade, thank you so much. Let's have a round of applause to Victor, Wisdom, and Jade for coming to represent their research. Thank you so much. It's really a pleasure to have you here. So there's one more project I want to show. Jonathan wasn't able to be here in person, but this is just fantastic work, and I wanted to showcase it. So Jonathan and his colleagues at MIT won the Best Paper Award at iClear with a paper called the lottery ticket hypothesis, where they're looking for these sparse trainable neural networks within larger neural networks. Now that had nothing to do with TFRC, but it was this really interesting idea. Many of the neural networks that we're used to have this tremendous number of parameters. They're very large, and one thing that the OpenAI graph earlier didn't show is that these neural networks are getting larger and larger over time. There's generally a correlation between larger model sizes and higher accuracy, as long as you have enough training data. But it takes more and more compute power, again, to train these larger and larger networks. So Jonathan and his colleagues asked this question: what if you could find just the right subnetwork in this much larger network that could perform the same task as the larger network, ideally to the same accuracy? And those networks are, somewhat whimsically called these lottery tickets. So at iClear, Jonathan used small networks, because that's what he could afford, to show some initial encouraging evidence for this hypothesis. But the real interesting part of this research, at least from my perspective, since I'm into big compute, is does it work at scale, right? And so to find that out, Jonathan got in touch with us here at TFRC to try to scale up this work. And he was kind enough to say at the bottom here that for his group, research at this scale would be impossible without TPUs. So let me share a little bit more about his work and then about his findings. So the lottery ticket hypothesis, as I mentioned before, is related to this broader category of techniques called pruning. And to be clear, there are many approaches to pruning neural networks, but most of these approaches take place after the networks have been trained. So you've already spent this compute time and cost to get the network trained, and then you modify the trained model to try and set weights to 0 or reduce the size of the model or distill it is another approach into a smaller model. But it's interesting to ask, could you just train a smaller network from the start? Could you prune connections early on, maybe at the very beginning or at least early in the training process, without affecting the learning too much? So like I said, this initial paper showed some very promising results on small networks, on small data sets. So with the TFRC Cloud TPUs, Jonathan took this to models we're all familiar with. ResNet 50, trained on ImageNet, and he found slightly different behavior, but was able to validate the hypothesis. So you can't go all the way back to the beginning. You can't prune all the weights, at least with current understanding. There may be further breakthroughs. But you can go almost back to the first epoch, cut the network down, and then train from there with a much smaller network without any harm to accuracy. In particular, Jonathan found that with ResNet 50, you could remove 80% of the parameters at epoch 4 and not hurt the accuracy at all. And you're training to something like 90 epochs or further. So this is a real compute savings. And there's these plots down below with ResNet 50 and Inception sort of showing you this rewind epoch and showing that the test error stays low until you get past rewind epoch 4 or 3. One thing I really appreciated about Jonathan's work is, in addition to carrying out these experiments and publishing them and sharing them with the community and inspiring other research, he built some interesting tools to help manage all the compute power. So what you're seeing here is actually a Google Sheet, so a spreadsheet that Jonathan wired up with scripts to orchestrate all of his experiments. So this was a fully declarative system at the end of the day. He could add a row to the spreadsheet, and behind the scenes his script would kick off a new experiment, monitor the results, bring them back into the spreadsheet, flag error conditions if anything had gone wrong. And at the end of the day, this spreadsheet had thousands upon thousands of rows showcasing all the different experiments that were, then searchable and shareable and usable in all the ways that a spreadsheet is. So I thought this was a great mix of sort of old technology and new. And this was a serious amount of compute. Jonathan estimates that he used at least 40,000 hours of cloud TPU compute on TFRC. So I hope that underscores that we're really serious about providing a large amount of compute for you to do things that you couldn't do otherwise and then share them with the research community. So it's not just about the projects that you've heard today. These are just samples of the thousands of researchers who are working on TFRC, and I'd really like to personally encourage all of you to think about your next research project happening on TFRC. And it can be an academic project, or it can be a side project, it can be an art project. As long as it's intended to benefit the community, as long as you're going to share your work with others, make them open, and help accelerate progress in the field, we'd love to hear from you. So if you're interested in getting started right now, you can visit this link below, g.co/TPUtalk, and enter code TFWorld. That'll go straight to us and the organizers of this event, and we're happy to make available, as a starting point, 5 regular cloud TPUs and 20 preemptible cloud TPUs for several months for free. The rest of Google Cloud Services still cost money, so this is not completely free, but the TPUs are the overwhelming majority of the compute cost for most of these compute-intensive projects, and so we really hope that this enables things that you couldn't do otherwise. And if you get to the limits of what you can do with this initial quota, please reach out, let us know, tell us about what you're doing, tell us what you'd like to do. We can't promise anything, but we'll do our best to help with more, maybe even a lot more compute capacity, including the access to pods that I mentioned earlier. So thanks again to all of you for being here today, for joining on the live stream or online. Thanks to our speakers for representing their work in person, and we'll all be happy to hang out here afterwards and answer any of the questions you might have for those of you who are here in the room. Please rate this session in the O'Reilly Events app, and thank you all very much. Hope you're enjoying TF World.